need to unmute this as well. Perfect.
Okay, great. Okay, so hello everyone and welcome to the third day of the Safari Live workshop. Today we will focus on data-centric and energy efficient computing. We have a long line of presenters scheduled for today, but now we're going to start with Geraldo. Geraldo has finished his PhD in April 2025, but he's still working and doing cutting-edge research with Safari. His current broader research interests are computer architecture, systems, and applications with a special focus on memory technologies and emerging applications. So Geraldo, please go ahead.
Thank you for the introduction. Welcome everyone for this Safari live seminar. We are going to talk about PIM stuff, and I'm going to give a brief introduction on the subject, focusing on an extended version of my PhD thesis, which is called New Tools, Programming Models, and System Support for Process Memory Architectures. So, Konstantina mentioned, I was a PhD student at the Safari Research Group, where I graduated in April, and I do research on several topics on computer architecture, including computer systems and process memory. So my pointer is a bit slow. Okay, so the overall topic that we are going to cover today, or the overall problem that we are trying to solve today, is that data movement bottleneck is a problem in computer-centric architectures. So data movement bottlenecks can create a problem in current systems for a myriad of different reasons. For example, maybe your application does not have enough data locality to make use of the cache hierarchies in your processor, or maybe your memory cannot provide enough memory bandwidth to keep the processing elements fully occupied, or maybe the trip latency to go back to main memory and to the processor is too high, and the processor cannot hide the latency for some application. We did some studies together with Google to show this effect of data movement bottlenecks in current systems. So in terms of energy, for example, we saw that consumer workloads like Google Chrome, for example, or video compression that is used for YouTube or Google Meets accounted for around 62.7% of the total system energy caused by data movement bottlenecks. And it's not only those systems. If you look at accelerators targeting machine learning models, we can see that depending on the model, some of the energy of those accelerators is also dominated by moving data around. So more than 90% for large machine learning models. Even though processor-centric architectures have evolved over the years to try to mitigate these data movement bottleneck issues for modern applications with techniques such as aggressive hardware prefetchures or deeper and deeper cache hierarchies, such architectures do not fundamentally address the data movement bottleneck problem. And you're still seeing such issues showcased in modern applications as we talk today. So one fundamental way of alleviating such data movement bottleneck issues is to do a paradigm shift for what we call processor-centric architectures to more memory-centric architectures, where we move data to we move computation to near where the data resides. And one classic example of memory-centric architectures is process memory. So compared to processor-centric architectures, process memory architectures have access to abundant memory bandwidth, a shorter average memory access time, and abundant per array parallelism. So we in Safari classify process memory architectures in two different realms. First, process and near memory architectures are those architectures where we add logic to the same die or nearby the memory arrays themselves. So here we can think about those architectures are similar to what you think about as current processors. So you have logic and you have memory. Those are manufactured separately, but then you integrate them together in the same package. And then as the closer that you integrate the computation to the memory arrays, more of the benefits of process memory that particular logic is going to benefit from. So the second way of doing processing in memory is what we call processing using memory architectures, which here we are going to use the analog operating principles of the memory cells themselves to perform computation. This is a bit different from what are used to develop as systems, because now you're not going to develop logic and memory separate. You're not going to think about them as two different things. We're going to we're only going to have memory, and we're going to operate this memory in different ways. And by doing so, we can implement operations such as majority of 3, and based on those, we can compose more complex operations as addition, subtraction, multiplication, so on and so forth. A brief overview of those architectures. Processing near memory architectures have been proposed in the literature for many, many years. So since the 70s, we have works proposing processing near memory architectures. Then we have a revival of them in the 90s, and then later on in the late 2010s. But now recently we have commercially available processing in-memory architectures hitting the market. For example, there is this French startup called UpMem that implements this near DRAM bank processing near memory architectures for general purpose computing. This slide is a bit not updated anymore because UpMem was bought recently by Qualcomm, and is unclear if you can still buy UpMem DIMMs or not. But so far, those architectures are already in the market and people have access to them. Other architectures or other memory companies such as Samsung or Alibaba is not, SK Hynix and Micron, that have their own processing near memory solutions as well, mostly targeting neural network models. So I'm going to give a brief background on DRAM, so I can introduce processing using memory architectures. So this is the third day of the Safari Live seminar, probably already familiar what we're going to talk next. So I'm going to try to move relatively quickly so I don't bother you. DRAM chip is organized as a hierarchy of components. In the top of this hierarchy, we have what's called a DRAM mat. A DRAM mat is constituted of DRAM cells organized as a 2D array, where horizontal lines of DRAM cells is connected through word lines, and vertical collections of DRAM cells connects through a bit line. So bit line shares a local sense amplifier, and word line shares a local row decoder. In the next level of the hierarchy, we have what's called a DRAM subarray, which is a collection of the DRAM mats. A DRAM subarray shares a global row decoder and a global word line that spans across those many DRAM mats, and a global sense amplifier, which is used to move data from the local sense amplifier down to the I/O interface and eventually to the memory channel. So prior works have shown that we can use this organization and the way that DRAM operates to perform different operations. For example, row colon shows that we can do in-DRAM row copy without the involvement of the CPU to copy one source row inside the DRAM chip to a destination row. The way that this works is by issuing back-to-back activations to the DRAM chip. So in the first activation, we open one set of DRAM cells in a given DRAM row. Here in this example, the source row, which is going to allow the DRAM chip to copy this data to the local sense amplifier. Then we issue another activate to the destination row, which connects those DRAM cells to the local sense amplifier. And since the local sense amplifier have latch amplified the data from the source row, this data is going to be copied to the cells from the destination row that has been just activated. So by doing DRAM row copy operations like this, row clone shows that we can reduce the latency of a 40 kilobyte row copy from 1046 nanoseconds using DMA engines to 90 nanoseconds, and significantly reduce the energy of such operation from 3.6 microjoules to 0.04 nanojoules. And this happens because we're not moving any data outside the memory chip itself. We are just operating the DRAM chip in a slightly different way. Ambit shows that we can use similar approach to implement in DRAM a majority of 3 operations. Here we are going to activate 3 rows at the same time. And when activating those 3 rows at the same time, the DRAM cells in those 3 rows simultaneously perturbates the local bit line. And since the circuitry of the locus amplifier is basically a differential circuitry, this is going to pull the voltage level to the majority of three, or the majority of the voltage levels stored in the three activated DRAM rows. So in this example here, the majority of blue, yellow, and blue is going to be blue. And the data is stored back to the DRAM cells themselves, the output data. Similar to row clone, Ambit shows that we can implement this majority of three operations in DRAM chips and significantly reduce the energy consumption of such operations from 137 nanojoule per kilobyte to as low as 3.2 nanojoules per kilobyte. So other prior works, also from Safari, has shown that we can further extend these operations to implement more complex operations. So now we can do in-DRAM row copy operations, and we can do majority of three as well as in Ambit. And I didn't mention here, but Ambit also shows how we can do not. And by having majority and not operations, we have a functional complete set of operations. So in theory, you can implement any other complex operations as needed by composing majority of three and not operations. And this is exactly what we do in this work called SimDRAM, which we propose a three-step framework that translates the required operation, for example, addition or subtraction, into sets of in-DRAM row copies, a majority of three or not operations that can be executed inside the DRAM chip itself. So I'm going to illustrate how we can do that by implementing an in-DRAM addition operation. So let's say that you have a RIP carry adder here that sums A, B, and carry in. And the first step of the SimDRAM framework is to translate this and or not version of this RIP carry adder into a circuit implementation that only has majority and not operations over there. And this steps is required so that because the main operation that we are doing in DRAM is majority of three and not operations. So after this translation is done, what the framework does is traverse this majority not graph that represents a RIP carry adder node by node, issuing triple row activations to the DRAM chip. So here in the example first, we activate the first, we issue triple row activations to represent the first majority gate, which takes as input A, B, and carry in. It produces as output the carry out value. And here in this example, we have A and B storing 1 and carry in storing 0. And the majority of this is going to be 1 stored in the carry out row. Then we move to each one of those majority gates one at a time. And in the end, we have in the carry out row as full of 1s, and in the sum row full of zeros. And since initially we have A and B storing 1 and 1, 1 plus 1 is 2, and then what we have here basically is 1 and 0, which is represents the 2 as well, the output of the addition. What I didn't mention here is that this process then is basically a bit serial process. So you issue these triple row activations bit by bit, as many bits as you have inside your data world. So for a 32-bit addition, for example, you would repeat this process 32 times. So basically, by operating DRAM chips like this, we are transforming the DRAM chip into a very wide bit serial SIMD engine. So very wide because we have as many operands as we have DRAM columns inside the DRAM subarray. Bit serial because we operate each bit individually at a time. And SIMD because we have single structure, multiple data model here, where you are doing the same operation, the same majority operation over as many data bits stored in the DRAM columns of the DRAM subarray. So prior works has shown that we can use such approach for implement operations in many modern applications. For example, as Transpin shows that we can use such approach to implement and accelerate neural network transformers. And also other works especially from our group, has shown that commodity off-the-shelf DRAM chips are capable of implementing such book bitwise operations by violating the DRAM timing parameters. I'm not going to get into details over here because the follow-up talk from Ismail is going to give more details on those operations. But basically, in summary, our work has shown that we can simultaneously activate up to 48 different rows in 2 neighbor subarrays, perform NOT operations up to 32 output operands, and implement 60 input and OR and NOR operations by violating DRAM timing parameters. And this is our experimental setup that we have in Safari. Ismail is going to talk more about all of this. So this is just to conclude. In conclusion, process using memory have this capability of implementing a majority of 3 of DRAM row copy operations inside the DRAM chip, and those operations are already capable of, at some extent, in commodity unmodified DRAM chips as they are today. So it's a very promising approach to accelerate applications that suffer from data movement bottlenecks at very low area cost. So, okay, even though those processing memory architectures, both processing near memory and processing use memory architectures alleviate data movement bottlenecks compared to processor-centric approaches, adopting such processing memory systems in mainstream architectures is still quite complicated due to a lack of, for example, workload characterization methodologies and benchmark suites targeting processing memory architectures, executing paradigms that can map applications effectively into the processing memory hardware, compiler supporting programming frameworks targeting processing memory architectures, and adaptive data-aware runtime mechanisms that can use the properties of data to accelerate pin execution. So in summary, the problem that we're trying to solve here is that the lack of tools, programming, and system support for process memory architectures limits their adoption in current and future systems. And this is exactly what I tried to solve during my PhD thesis, where we propose solutions to each one of those problems. We believe that we can effectively explore the inherent parallelism of process memory architectures and facilitate their adoption through the end-to-end hardware-software support, including identifying workloads, identifying characterized data movement bottlenecks, providing programming and system support for end-to-end process memory architectures, and enabling data-aware optimizations for efficient processing use memory execution, and finally designing programming frameworks to aid process memory programmability. So if you achieve that, we can enable large improvements in system performance and energy efficiency for future process memory systems. Into this end, we make 4 main contributions. The first one is DAMove, the second one is BIM-DRAM, the third one is Proteus, and the fourth one is DAPO, which I'm going to provide some information on in the follow-up slides. Starting with how we can identify and characterize data movement bottlenecks using the DAMove framework. So there are many tools and approaches out there that can aid one to try to identify data movement bottlenecks in a target application running in a processor-centric approach. So there are 2 examples here. The roofline model identify if application is memory bound or compute bound, and simple metrics as high less level cache misses per kilo instructions can give you an indication if that your application has high memory intensity. However, we saw in our work that those methods are not comprehensive enough in first identifying a variety of different data movement bottlenecks that your application might suffer from, and correlate such data movement bottlenecks with the most suitable data movement mitigation mechanism, either cache hierarchies, prefetchers, or processing near memory solutions. Therefore, our goal in this work is to develop a methodology that can basically identify different sources of data movement bottlenecks in applications and compare compute and memory-centric architectures in terms of alleviating such data movement bottlenecks. So to this end, we propose the DAMove methodology, which takes as input application source code and is input data sets. And in the first step, provides application profiling to identify functions in these applications that potentially suffers from data movement bottlenecks and dominates the execution time of that application. And then using a new simulator that we call DAMove Sim, generates memory traces that are used for in steps 2, for which provides a locality-based cluster to identify the spatial and temporal locality of that particular memory trace identified for the identified function, and also a scalability analysis that collects metrics that identify characteristics of the hardware running that application, such as arithmetic intensity. And based on the information from all of those 3 steps, we classify the application into 6 different classes of data movement bottlenecks and correlates each class with different data movement mitigation approaches. So give a little bit of background on each one of those steps. The goal of the first step is basically to identify functions in applications that potentially suffer from data movement bottlenecks. To do that, we use a profiling tool called Intel vTune to identify functions that have a high memory bound metric. This step is completely optional, so if the user already have a function in mind that he or she wants to profile, this step can be eliminated and go straight into that function. So we apply this first step to more than 245 different applications from different domains, including graph processing, deep neural network, physics, high-performance computing, genomics, and many others. And the output of this analysis is basically a selection of 144 different functions for more than 77,000 application functions that we divide into 2 main sets. 44 functions that we are going to use to train, or steps 2 and step 3 of our methodology, and 100 functions that we are going to use to validate that the data that the model that we came up with after the training process. Then we move to step 2, the locality-based cluster, where here we use a k-mean cluster to classify the spatial and temporal locality of these different application functions. So here, basically what we have are applications that have low locality in orange and applications that have high locality in blue. And intuitively, the closer that the application is to the bottom part of this chart, the most likely is application function to take advantage of deep cache hierarchies of aggressive hardware prefetchers, because these applications have low spatial and temporal locality. Then we move to the next step, the memory bottleneck classification, which goal is to identify a specific source of data movement bottlenecks in the hardware running the application. To do that, we use the MoveSim simulator, which integrates the CPU simulator called ZSim and our memory simulator called RAMulator. And in the work itself, we analyze 3 system configurations, but in this talk, I'm going to highlight only 2. The first configuration is a regular processor-centric view of the system, which have deep cache hierarchy and access to DRAM off chip. And the second configuration is of a processing near memory system that adds general purpose logic nearby the logic layer of a 3D stack memory chip itself. And doing this scalability analysis, we also vary several system parameters, such as the core count in the system, as well as the type of core that we have, either R for the core and another core for both host and pin cores. So based on this analysis, we classify this application into 6 different classes of data movement bottlenecks. Some of them are more obvious. So applications, for example, that suffer from DRAM bandwidth or latency bound, and some of them are not obvious. For example, applications that suffer from cache contention and cache trashing as we increase the number of cores and threads in the system. So the Move benchmark suite is available online, including our applications and simulator. So the benchmark suite and the Move Sim simulator is available online and has been used for many groups to try to study different aspects of processing near memory architectures. So I don't know if we have any question related to the Move. If not, I'm going to move to the next contribution, which is how we can provide programming and system support for end-to-end processing using memory architectures using MIMDRAM. So the main problem that we are trying to solve over here is that processing using DRAM systems suffers from 3 sources of inefficiency coming from the large and rigid access granularity of DRAM chips themselves. First, they suffer from SIMD underutilization. Second, they suffer from limited computing support, only being able to implement in-DRAM mapping operations. And third, they suffer from a challenging programming model due to a lack of compilers for processing using DRAM systems. So basically, the problem that we're trying to solve here is that by accessing DRAM at the row granularity causes those three sources of inefficiencies, and our goal is to design a flexible process using DRAM system that overcome those three limitations. So to this end, we propose MIM-DRAM, which key idea is to use DRAM fine-grained access for process using DRAM operations. So when accessing a DRAM row inside the DRAM chip, all of the METs inside the DRAM subarray are activated, even though only portions of the data inside those DRAM METs might be read from a follow-up read access from a DRAM column access. This generates issues for regular DRAM chips, since you are wasting energy doing those coarse-grained row activation. So prior works not necessarily related to processing memory, and later on today we are going to have a talk detailing these more details, propose to use fine-grained DRAM access to reduce this energy waste by segmenting the global word line and allowing one to access individual DRAM METs doing a DRAM row access. So this basically allows you to only activate the portions of the DRAM row that have the data that's going to be accessed by a DRAM read access in the follow-up request, which can improve system performance. And again, Ataberk is going to talk about sector DRAM that implements this idea later on today in this seminar. But here we are going to use this idea of fine-grained DRAM for processing using DRAM execution, so which provides us three main benefits. So the first benefit is that it improves SIM utilization, because you're going to only issue triple row activations, which I explained in the background, to the DRAM METs that have data that you want to operate on top of. And this also provides another benefit, that for the unused portions of the DRAM METs in the DRAM subarray that we are not going to activate, we can issue other types of processing using memory operations. Hence, using this DRAM subarray now not only as a SIMD substrate, but a substrate that implements multiple instructions over multiple data at the same time. So you can have multiple independent instructions operating in different portions of the DRAM subarray, each instruction in a different DRAM MET. Second, we can implement in DRAM more complex operations, such as in DRAM reduction, by using the internal interconnects already available inside the DRAM subarray that allow us to move data across different DRAM METs inside the DRAM subarray. And third, there is this nice feature of the DRAM METs that they usually have as many DRAM columns as SIMD lanes in modern vector ISAs. So inside the DRAM MET, we have around 512 different DRAM columns, and this is on par with, for example, AVX 512 instructions. So we can use basically the infrastructure that is already available for identifying vector instructions for processor for vector ISA instructions down to our process using DRAM operations. So based on this key idea, we propose MIM-DRAM, which is a hardware-software co-design process using DRAM system that enables fine-grained process using DRAM computation at low cost and low programming efforts. So MIM-DRAM is composed of both hardware and software components, which I'm going to briefly introduce next. So on the hardware side, we propose some modifications to the DRAM subarray to allow us to access different DRAM METs in a DRAM subarray with some isolation transistors, row decoder latch, and a MET selector. We also implement some low-cost interconnects that allow us to move data across neighboring DRAM METs inside a single DRAM subarray, which is going to be used for implementing the in-DRAM reduction operation. You also implement in the memory controller control unit, which is responsible for scheduling and orchestrates the execution of multiple processes using DRAM operations transparently from the user. So this control unit is basically has a scheduler, a scoreboard, and several processing engines that identify which instructions are currently running at the processing on the DRAM substrate, and keep ordering for such instruction streams. So on the software side, we propose 3 LLVM compiler passes that are responsible for code identification, code scheduling, and data mapping, and code generation. So in the code identification part, we use LLVM's auto-vectorization engine to identify in loops of applications code that can be vectorized. Then the vectorized instructions are used as input for the code scheduling and data mapping pass, which is responsible to identify which instructions can be executed, needs to be executed at the same DRAM maps because they have data dependency between them, or which instructions can be executed concurrently over different DRAM maps because they have data independency. And then this path annotates the instruction stream with some metadata that's going to be used by the hardware later on to identify such data dependency and data independency between instructions. And then the final pass is responsible for code generation for the process using the operations. So in the paper, we have many more system support that you adapt for MIM-DRAM, including instruction set architecture, execution and data mapping, data coherence, address translation, data location and alignment, and metadata translation. So we evaluate MIM-DRAM using the Gen 5 simulator, using 12 workloads for 4 main benchmark suites and some application mixes as well. We evaluate both single applications and also multi-program workloads. So in terms of energy efficiency, compared to a GPU, CPU, and MIM-DRAM, we see that MIM-DRAM significantly improves energy efficiency by basically fully leverage the symmetry parallelism inside the DRAM substrate. We also compare MIM-DRAM to other processing in-memory solutions like Drizzle and Fulcrum. In terms of performance per area, we see that MIM-DRAM significantly improve on top of such architectures. We have many more results in your work, but we invite you to check our paper for there. Is there a question?
I have one question about the segmented word line. So will this impact TRES for regular DRAM operations? Because now you have additional parasitics in the path.
So it should impact TRES. You mean for just if you segment the word line? Yes. No, so TRES is mostly dominated by the bit line capacitance load, right? But we are not changing the bit line, right? Just the word line. And so basically, so if it does, because the only thing that we are adding to the critical path is that isolation transistor. But again, that's not the critical path of the TRES of the timing anyway, right? Is this how long the bit line is? That would impact more.
So the opening of a row is not impacted significantly because the time that takes to open the row is dominated by charging of bit lines.
Is discharging by, yeah, that's the primary timing for the TRES.
Okay, thanks.
I believe that in the paper we have some analysis actually on how much TRES is impacted by the isolation transistor in the critical path. Mm-hmm. There is a number in my mind that is like 0.011%. I don't know if that's the proper number, but yeah, there's that number in the paper.
Thank you.
But thank you for the question. Any other question related to MIM-DRAM? Okay, if not, I'm going to move to how we can enable data-aware optimization for efficient processing using memory execution with Proteus. So again, apparently I really like to identify 3 problems in anything. So still process using the DRAM system suffers from 3 main issues caused by naively using a bit serial execution model. So first, they suffer from a rigid and static data representation, leading to subpar performance in the presence of narrow values. Second, they suffer from a throughput-oriented execution with low latency tolerance, failing to reduce the latency of a single processing using DRAM operation. And third, they suffer from scalability challenge for high precision process using DRAM operation, especially for quadratic scaling bit zero algorithms. So I'm going to illustrate a little bit more each one of those 3 issues. I start with the rigid and static data representation. So it's well known that applications store values in what's called narrow values. So very narrow values are data elements inside your application with a small dynamic range that is stored in a large data format. So for example, let's say that we have an integer, a here, that stores the number 4, so 100. But the minimum number of bits that you have to represent a number in C, for example, is 8 bits, right? So all of the 5 most significant bits of such data word here is going to be all zeros, while only the 3 less significant bits are going to have is going to store the dynamic range of the data format itself. And this happens for several applications. And if you want to do processing using DRAM operations on top of those applications in a bit serial manner, those most significant bits in the operation that I have going to call inconsequential bits are not going to contribute to the output dynamic range. So I'm going to basically compute the first 3 bits. So in the example here, I'm going to add 4 with 2, which is 6. And the output is also stored only in the last 3 least significant bits. But since we are operating in a bit serial manner, we are going to still keeping activating the rows containing the 5 most significant bits, which is going to generate an increase in latency and energy efficiency for such narrow value execution. So we did some analysis for real-world applications to try to quantify what is the minimum required bit precision in real applications to see if these narrow values actually were observed in the fields. And here in the y-axis, we have the required bit precision, defined as the minimum number of bits required to represent an input operand. And we have in the plot several distribution blocks, which shows the bit precision distribution, and where the whiskers extends to the smaller bit precision and to the largest bit precisions. And what we see from those 12 applications is that those applications display significant variation in terms of the amount of narrow values that they have. And the bit precision can be reduced on average from 32 bits to from 20 bits. But we see that actually, if you look at the data itself, it can even be further reduced by as low as 2 to 3 bits for some applications. So the main first idea for us to reduce or to improve the performance for our bit serial processing using the DRAM engine is to identify dynamically those narrow values when you're issuing triple row activations to the DRAM chip itself. And based in this identification, you can skip those inconsequential bits, which allow us to save latency, reduce latency, and reduce energy consumption for such operation itself. So then we move to the second problem, the throughput-oriented execution with low latency tolerance. And the main issue here is that since we need to operate on each bit at the same time, any operate with data width of more than 1 is going to suffer from what we call inter-bit dependence. So for example here, let's say that we have this addition operation again, and now you're operating over 2 bits. So you want to add 2 plus 2, and the result being 4. So when you issue the activations, we see that first we operate on bit zeros of the operation, then the carry is generated and then can be propagated through bit 1, and then we operate serially over the bits 1 of the input data word. Basically, this inter-bit data dependence serialize the computation because all of the bits of the data word is stored inside a single DRAM subarray. The key idea to break this inter-bit beta dependence is basically to scatter the bits across different DRAM subarrays. Because as we can see here in this graph, even though we still have this inter-bit dependence from the carry that is generated from one bit to another, we have several other majority gates that are independent of each other if we solve this inter-bit beta dependence first. So basically, the key idea here is to scatter the different bits of a data word across different DRAM subarrays and leverage subarray level parallelism to operate bit-independent operations concurrently doing the process using DRAM execution. So, for example, what this allows us to do as well is to use some fast inter-subarray interconnect network proposed by prior work to copy intermediate data generated in one DRAM subarray to another DRAM subarray. So let's see how this reduces the latency. So first, again, we operate the majority gates for bit 0 in your DRAM addition operation here in subarray 0. Then you generate and propagate the carry generated from bit 0 to bit 1. And once this carry propagation and generation is solved, we can compute all of the other majority gates from bit 1 and bit 0 at the same time in 2 different DRAM subarray, hence saving execution cycles. Third, how to solve the scalability challenge for high precision computation. So the main issue here is that bit 0 operation scales linearly or quadratically, depend on the type of the operation with the bit precision of the operation. And once you are in a high bit precision, for example, 32 or 64 bits, it's very hard to hide the latency of process using DRAM instructions. So our approach here to try to solve this issue is to use alternative data representation formats for high precision processing using DRAM operations. In particular, you're going to use the redundant binary representation, data representation, which is a positional data representation format, which represents 1 bit using 1 data word with 2 bits that can take any value from -1, 0, and 1. So in this example here, we represent the value 3 with 4 bits, 0, 1, 0, and -1. And the property that this alternative data representation format provides is that first, it limits the carry propagation to at most 2 places, and second, its latency independence becomes latency independence in regards of the bit precision, because again, this is a redundant data representation format. So basically, using those 3 main ideas, so the first one being narrow values for process using DRAM operation. The second one is using subarray level parallelism to break the interbit dependence during the operation. And third, using redundant data representation format for high precision computation, we propose Proteus, which is a data-aware hardware runtime framework that dynamically and transparently from the user chooses the in-DRAM implementation with precision and data format based on the input data for processing using DRAM execution. So Proteus is composed of 3 main components: a parallelism-aware microprogram library, a dynamic bit precision engine, and a microprogram select unit. So first, the parallelism-aware microprogram library is a collection of hand-optimized implementations of different processing using DRAM operations, which each one with different trade-offs in terms of performance and bit precision. Second, the dynamic bit precision engine aims to identify dynamically the dynamic range of evicted cache lines belonging to target processing using DRAM operation. And it also stores inside some table inside the memory controller what are the largest data values identified in each one of the memory addresses that are going to be later on used for processing using DRAM execution. And then finally, the microprogram selection unit uses that identified data format to calculate what is the required bit precision for the target operation, and also probes the parallelism-aware microprogram library to identify what, based on that target bit precision, what is the most appropriate microprogram or sequence of in-DRAM row activations for that particular bit precision that leads to either the best performance or the best energy efficiency for the target operation. So we have many more details in our paper, but I'm going to move to the evaluation. So again, we use 12 workload for 4 benchmark suites, and here we compare 2 main metrics: CPU normalized performance per area and energy reduction. So in terms of performance compared to the GPU, CPU, SIMD-RAM, Proteus only with dynamic bit precision engine enable, Proteus end-to-end design significantly improves performance per area by mostly, which performance mostly comes from this dynamic identification of narrow values inside the application. We observe similar results in terms of energy analysis, in terms of energy compared to the CPU, GPU, SIMD-RAM, Proteus only with dynamic precision engine enable, Proteus end-to-end design significantly improve energy efficiency again compared to those 3 main systems, again, mostly coming from this reduced bit precision execution. So again, there is many more details in the paper which I invite you to check online. Is there any question related to Proteus? Okay, if not, let's move to the last contribution, which is DAPA, which is a framework for processing in-memory programmability. So basically, the problem that you're trying to solve here is that there is a programmability barrier when you're trying to program general purpose processing near the memory systems, which requires the programmer to manually split the input data across different computing engines in the processing memory chip, transfer input data from main memory to the processing in-memory chips, manually handling caching inside the processing memory scratchpad memory, and also transfer the output data from pin chips to main memory. So I'm going to give an overview of how this looks in terms of code, and this is how you would program general purpose processing in memory system, such as the upmem system. So the programmer needs to write code to first align the data to the boundaries of a DRAM bank, collect input parameters, distribute those parameters across the different DRAM banks, launch the computation, collect results, and manage the scratchpad memory inside the pin chips, and finally orchestrates the computation to move data from the scratchpad memory to the processing engines and write it back. But in the end, the user only wants to do a very simple operation most of the time, even though it has to do all of this bookkeeping coding for something very simple, such as a vector addition operation. So basically, the problem that we are trying to solve here is that programming such general purpose processing near memory systems leads to non-trivial efforts, since the programmer needs to have knowledge of the line header and manually generate code for fine-grained data movement inside the processing near memory chip. And our goal is to ease the programmability of such systems by allowing the programmer to write efficient pin code without any logic of the hardware resources on the underlying system. To this end, we propose DAPA, which has the main idea of using intuitive data parallel programming interface for pin programmability. So DAPA automatically distributes and gather input data and gather output data, handles memory management and parallelize works across the different pin cores using a three-component framework. The first component is a data parallel pattern APIs. The second one is a data flow programming interface, and the third one is a dynamic template-based compilation. So first, the data parallel pattern API is a collection of predefined functions that implement high-level data parallel pattern primitives. So this idea of using parallel pattern primitives and also skeletal-based programming are quite common abstractions for parallel architectures, for example, GPUs or multi-threaded systems. And those parallel patterns are, for example, things as parallel map, reduce, filter, window, or grouping primitives. So we use those 5 data parallel pattern primitives to expose an interface for the user. And the user can combine those primitives to describe more complex data transformations over the input data itself. Then DAPA exposes a data flow programming interface to the user, which defines a pipeline, which is a collection of data and transformations that's going to be applied on top of the input data. So the pipeline has several stages, where each stage represents a different data parallel pattern API. And data flows sequentially across each one of the stages inside the pipeline. Finally, DAPA has a dynamic template-based compilation, which dynamically translates each one of those stages in a pipeline to the binary of the target application. To do that, we use a templating engine that uses a basic upmem code templates to generate upmem code. And on top of that, in the back end, we implement several optimization transformations to improve performance for this generated code. One of the main transformations is allowing the CPU and the pin cores to concurrently execute on top of a given computation. So I'm going to give an example of how a programmer, for example, can use this DAPA to implement a simple vector dot product operation. So the first step is to identify which data parallel patterns is required for the target operation. In this case here, is required a map and a reduce operation. And then the programmer uses the C++ API for the data parallel for the data flow programming interface to instantiate each one of those different maps, the stages for the map and the reduce operation. And note here that in the DAPA codes, the programmer there is no information regarding to the hardware. So there is no manually moving data, code to move data across the pin cores, or either to launch or distribute code, distribute data across the pin cores itself. And then in the third step, the dynamic template-based compilation extracts the required information from the data flow programming interface to populate the code template from the UpMem architecture, generate the binary, execute the data, and copy output data to be processed for the follow-up stage, one at a time. So we evaluate DAPA using a real mapping system with 6 workloads from the print benchmark suite. So in terms of performance, we see that for some applications, DAPA can significantly improve performance because of its concurrent parallel execution of host and ping in a given application. And in terms of programmer complexity, we see that DAPA significantly reduces lines of code compared to hand-optimized UpMem generated code, since it abstracts away hardware components. So compared to prior frameworks for processing memory programmability, in particular SimplePIM, DAPA have a higher abstraction level, supports more parallel patterns, and also enables for further optimizations as collaborative host and ping execution. So you conclude that DAPA improves on the state-of-the-art frameworks for processing memory programmability. So this basically concludes my 4 contributions. Is there any question related to DAPA? So basically, what we try to solve here in this work or in this thesis is system integration challenges for processing memory architectures, where we propose solutions to identify and characterize data movement bottlenecks with using that move. We provide programming and system support for end-to-end processing using memory execution with DRAM. We enable data-aware optimization for efficient processes using memory execution with Proteus, and we design programming frameworks to aid pin programmabilities with DAPA. Even though this covers several of the issues that we discussed earlier for ping adoption, there is still several research questions that needs to be addressed, and actually some of them are going to be discussed here in this seminar today. For example, as how we can address a security reliability challenge of ping architectures, how we can design and define virtual memory space for host and ping, how we can design lightweight coherent solutions for process memory architectures, and how we can assess ping benefits for emerging memory technologies. So basically, this is still a great time to do research on process memory architecture. There are a lot of nice problems that needs to be solved in the future. And this basically concludes my talk. I'll be glad to take any questions. Just on time. Thank you very much.
So thanks a lot, Geraldo. And now, according to our schedule, we have a coffee break, and we will be back at 10:30 with Ismail.
Okay. So let's get started. I'm Mohammad, a senior researcher and lecturer in Safari Research Group. It's my pleasure to introduce you Ismail. Ismail is a PhD student, second year in Safari Research Group. His current broader research interests are in computer architecture, processing memory, and hardware security, focusing on understanding, enhancing, and exploiting fundamental computation capabilities of modern DRAM architectures. So stage yours, and we are looking forward to your talk.
Thanks a lot, Mohammad. Can you? Yes, I can. I guess you can hear me. Yes. So hello, everyone. Today I'm going to talk about a topic of what we call understanding computational capabilities of off-the-shelf DRAM chips. This talk will consist of two papers. First one is the next one. Let me go through. Yep. A functionally complete Boolean logic and real DRAM chips, experimental characterization and analysis. This paper published in HPCA 2024. And the next paper will be about, again, computational capabilities of DRAM, which is published in DSN. So let's start with this one. So our motivation was processing using DRAM can elevate performance and energy bottlenecks caused by the frequent data movement between main memory and computing units. And prior work showed that existing DRAM chips can perform 3-input majority and 2-input and/or operation in existing real DRAM chips. However, this proof of concept demonstrations on off-the-shelf DRAM chips do not provide functionally complete operations such as NAND or NOR, NOT operation, and/or operation with more than 2 inputs. In this study, we conduct an experimental characterization on 256 DDR4 chips from 2 major manufacturers. And we observed that off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input and NAND or NOR operations with very high reliability. And second, data pattern and temperature only slightly affect the reliability of these operations. So here's the outline of my talk. I'll start with a brief background. So as you already know from Geraldo's talk, today's computing systems are processor-centric and all data is processed in processor at a great system cost. In order to perform a computation, we need to move the data between computing units and main memory. And prior work showed that more than 60% of total energy is spent on this data movement. And processing in memory is a promising paradigm to elevate such problems. And there are 2 main approaches. First, processing near memory, PIM, which the logic is added near memory arrays or the logic layer of 3D stacked memory. And the second one is processing using memory, which uses analog operational principles of memory cells to perform computation. And let me give you a brief background on DRAM organization as well. So DRAM consists of multiple DRAM chips, DRAM module. And inside the DRAM chip, we have multiple DRAM banks. Inside the DRAM banks, we have multiple subarrays and sense amplifiers. Within a subarray, we have 2-dimensional array of DRAM cells. And each a row of DRAM cells called DRAM row, and they are connected through word line, and a column of DRAM cells are connected to sense amplifiers via bit lines. To achieve high-density DRAM chips, open bitline architecture is widely adopted in modern DRAM modules. In this architecture, each subarray's bitline are connected to 2 rows of sense amplifiers, one above and one below the subarray, and this results in neighboring subarrays to share a common sense amplifier. During an activation, which is a major DRAM operation that we'll talk about real soon, another bitline in a neighboring subarray is also involved to serve as the reference of the sense amplifier, which is bitline bar in this example. After a successful activation, the bitline and bitline bar have a complementary value as the sense amplifier consists of 2 back-to-back inverters. And let's take a look at major DRAM operations. The memory controller first needs to activate a row to access a data in the DRAM, and which will the DRAM fetch the row's content into sense amplifiers. Then column accesses are serviced from the sense amplifiers upon a read or write request. And finally, subarray, or generally bank, needs to be precharged to get ready for the next row activation to access a data from another row. So Our goal in this study to understand the capability of off-the-shelf DRAM chips beyond just storing data and rigorously characterize the reliability of this capability. And in this study, we experiment to demonstrate that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays, can perform NAND operation with up to 32 output operands, and can perform up to 16 input AND, NAND, or AND NOR operation. And let's look at how we characterize real DRAM chips. So we use an FPGA-based DDR4 testing infrastructure developed from DRAM vendor that enables us to have a fine-grained control over DRAM command timings and temperature. And we tested 256 DDR4 chips from 2 major manufacturers covering different die densities and revisions, basically different DRAM architectures. In this study, we focus on 2 neighboring subarrays, here denoted as subarray X and subarray Y, which share a common component sense amplifiers. We perform our experiment using this command sequence activate row A, precharge, activate row B. And we carefully sweep row addresses row A and row B, and timing parameters between each command in this command sequence, and where the row A and row B are in the neighboring subarrays. So let's move on to our first analysis, multiple row activation in real DRAM chips. So our key observation is activating 2 rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So here's the same pictorial example where subarray X and subarray Y are neighbor subarrays, where when we respect the timing parameters between each command in this command sequence, we will activate only a single row at a time. However, if we greatly violate these timings, we observe that we can activate many rows in these 2 neighboring subarrays. So this is because of the hierarchical row decoder circuitry that we try to uncover in the next paper. So to rigorously characterize and understand which and how many rows are simultaneously activated, we sweep row A and row B addresses to cover all rows in these 2 neighboring subarrays. And these are our key results. First, off-the-shelf DRAM chips have 2 distinct sets of activation patterns in neighboring subarrays when 2 rows are activated with violated timings. First, exactly the same number of rows are activated in each subarray. We observe that we can activate up to 16 rows in both subarrays at a total of 32 rows. And twice as many rows in one subarray are activated compared to its neighbor subarray. We observe that we can activate up to 16 rows in one subarray while activating up to 32 rows in its neighboring subarray, a total of 48 DRAM rows. And our key takeaway is off-the-shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays. And there are much more results and hypotheses in our paper. Please check out if you would like to get more details. So now let's move on to our second analysis, the NAT operation. So in this NAT operation, we will use this multiple row activation neighboring subarrays. Yes.
Sorry, I have a question. So regarding these rows that you can keep them activated simultaneously, so how long can they kept activated? So because we violate some timings, and then probably because of some decoder circuitry, we can activate several rows.
Yes.
But how long we can keep them activated?
As long as we want.
As long as we want, okay.
Yes. Until we send in a precharge command. So what we do here is that, let me go back. So here we violate the timings, right? So the real thing that why we violated is that, so we activate row A and then we issue precharge and again violate and activate row B. So the low delay is because of we want to activate them very quickly, simultaneously, and we need this precharge command to trick DRAM. So basically, DRAM thinks that, so DRAM has a finite state machine, you can think of like that. DRAM thinks that it got a, let's say, precharge command already, so it can activate another row. So it's in a state that I'm activating a row, but internally we are activating many more rows. So in order to close the rows, or DRAM thinks that in order to close a row, we need to issue a precharge command. So it's in this state. So in order to close the rows, we need to issue the precharge command, which will close the bank.
Okay, yeah, I understand that. Maybe a follow-up question.
Yes.
Probably is actually my misunderstanding about how these things work. But the decoder circuitry, I thought that the output of that decoder is not stable yet, and that's why we can activate several rows together. But at some point, the output will get stable in the steady state, and then we might have only one activated.
So what we observe is that our hypothesis that you don't need to violate this, let's say the first activate the precharge. You can even, in order to activate multiple rows, you need to only violate precharge to activate row B, which is the second one.
Yeah.
So what we do here is that you activate a row. I will show you later, maybe over there it will be more clear, but shortly, so we use that there are some intermediate signals that follows a path and activates a word line, but there are many more intermediate signals that are not necessary. DRAM is using that like hierarchically because it wants to activate very quickly. So we are leveraging those unnecessary intermediate activations, intermediate signals. So basically, there are some nodes that are asserted, but they're not connected to the final output. So, and then when we violate this, there are more intermediate signals. And when you follow the path, you will activate another row. I think this will be clear in the second part of the presentation.
Yeah, but I got what you mean. Sounds good, thank you.
Yeah, thanks. Any more questions? No? Okay. So for NOT operation, the key idea is here. So assume that here we have two neighboring subarrays, and for this, just sake of this example, we have two cells. They're connected to, they share a common sense amplifier here. SRC, source, DSC, destination, and SRC has a value of A, stores a value of A. So here, the key idea is really to use the NOT gate in the sense amplifier. We want to connect the rows in neighboring subarrays through a NOT gate. So how we do that? By simultaneously activating both of them. In theory, if you activate source, what will happen is that it will share its charge to its bit line. Essentially, after you wait for TRS, it will become a voltage value of A. Since you have the sense amplifier as a NOT gate, in the bit line bar, you will have the negated value, the purple one, as negated A. So if you can somehow activate destination without, let's say, disabling the sense amplifier or precharging the bit lines, you can store the destination, the negated value of A in the destination, because of you already have the value in the bit line bar. So I will explain to a bit more detail on how we do in real DRAM chips. So here, a bit more detail, we have again source and destination. Assume that both are essentially have a voltage value of ground. You can think of logic 0, and bit lines are precharged. Precharged means they're at VDD over 2. So we issue activate command. What happens is that it will connect the source to bit line, and then when we wait a nominal timing parameter, it will drive the bit line to ground, and sense amplifier will drive the bit line bar to VDD, right? And then if we violate the timing, precharge the activation destination, what will happen is that we will connect the destination to bit line, and then since we violate the timing, we interrupt the DRAM to complete this precharge process. The sense amplifier is still enabled. And then also destination's bit line is still at VDD. So as a result of waiting a nominal timing parameter of TRAS or less, you will get the negated value of source, which is VDD, written to destination. I hope it's clear. So again, similarly, we sweep the row addresses to cover all subarrays in all two, let's say, neighboring subarrays. And we also sweep DRAM chip temperature to 50 degrees Celsius, 95 degrees Celsius. As a side note, after DRAM nominal timing parameter, nominal temperature for DRAM is up to 85. So we would like to also understand how what will happen if we go a bit extreme to 95. So to evaluate the reliability of NOT operation, we introduce a technique, we introduce a metric called success rate for a DRAM cell, which is the percentage of trials where the correct output of a test operation is stored in the cell. So assume that we have this NOT operation and we tested 4 times, and half of them for this cell is incorrect results and half of them produce correct results. And success rate for this cell is 50%. So we tested a total of 10,000 trials. I don't know how many millions of DRAM cells from more than 200 DRAM chips. And this analysis provides us 2 key takeaway lessons. First, off-the-shelf DRAM chips can perform this NOT operation and can use this NOT operation with up to 32 destination rows. And second, temperature has a small effect on the reliability of NOT operation. So let's take a look at our first results. In the x-axis, we have the number of destination rows. And the y-axis, we have the success rate distribution across tested DRAM cells. And here, what we observe is that there is at least 1 DRAM cell, actually much more DRAM cells, that can perform the NOT operation with 100% success rate, meaning every time we test, and out of 10,000 trials, we observe the correct results. There is no single incorrect results in those cells. And we conclude that off-the-shelf DRAM chips can perform NOT operation with up to 32 destination rows. So maybe one side note here is that, as you can see, from left to right, when we increase the number of destination rows, this reliability reduces. So the hypothesis is that now sense amplifier needs to drive 32 cells at once instead of just 1 at most, right? So actually, it's not just 32. In order to drive this 32 negated value to 32 cells, you need to activate 16 rows in the upper subarray. So in total of 48 DRAM cells. So, but sense amplifier for this real DRAM chips is designed to drive just only 1 cell. So we believe that this sense amplifier is not for those we observe low reliability. Their sense amplifiers are not designed, and they're weaker to drive this 48 cells at once. So the next one is impact of temperature. So we use destination cells that can perform NOT operation with more than 90% of success rate at 50 degrees Celsius, because to maintain the reasonable experiment time. And here are the results. In the x-axis, again, we have the number of destination rows. In the y-axis, we have the success rates, and each colored box for each X labels represents a different temperature. From left to right, temperature increases 50 degrees Celsius to 95 degrees Celsius. There is only, I guess, one notable changes in 32 destination rows, and we observed that when you increase the temperature from 50 degrees Celsius to 95 degrees Celsius, there's only 0.2% of variation in average success rates. And we conclude that temperature has a small effect on the reliability of NOT operation. So now this is, let's move on to our last analysis, end-to-end OR and NOR operations. And in this analysis, we will use both 2 observations that we have. So the key idea is we manipulate the bitline voltage to express a wide variety of functions using multiple row activation neighboring subarrays. So assume that we have, again, 2 neighboring subarrays, and they have, each of them have 2 cells. A and top subarray cells store A and B, and the lower subarray, bottom subarray stores X and Y. Now, if we activate these 4 cells simultaneously, bitline at the bottom subarray becomes the function of voltages in X and Y, basically the average of X and Y, and the top subarray's bitline becomes the function of voltages in A and B. And with a, let's say, good simplification, they become the average of the activated cell's voltage value. And sense amplifier will compare the voltage at the bottom bitline to the voltage at the top bitline to figure out which one is higher. So let me show you the basic intuition to perform two input and then operation using this key idea. So for this example, we have two subarrays, reference subarray at top and the compute subarray at bottom. And in the reference subarray cells, we have two cells in each. We store VDD and VDD over 2. So as a side note, again, VDD over 2 can be done in real DRAM chips using a technique called frac DRAM from prior work. And in the compute subarray, we have X and Y. And assume that we issue this multiple row activation sequence, activate, precharge, and activate with greatly violated timings. And when we issue this command sequence, we activate these 4 cells in 2 neighboring subarrays. Those are our assumptions. So what happens, what really happens is that assuming, let's say, there is no bitline capacitance to make things very simple, the bit line, when we activate these 4 cells, what happens is that in the reference bit line, the reference bit line becomes the average of VDD and VDD over 2, while the compute subarray's bit line becomes the average of X and Y. And after this charge sharing, sense amplifier to amplify the difference, it will compare the top bit line's voltage to bottom bit line's voltage. So now let me go through the truth table of let's say 2 input and an AND operation. So in the first row of truth table, X and Y are ground, and logically they're 0. What happens is that the compute subarray's bit line becomes ground, while the reference subarray becomes 3 VDD over 4, the average of VDD and VDD over 2, right? So after the charge sharing, sense amplifier will compare the voltages on the bit lines. Since 3 VDD over 4 is higher than ground, the cells in the reference subarray will be stores 1, while the compute subarray cells will store 0. So for X is 0 and Y is 1's case, the average voltage on the compute subarray becomes VDD over 2. And this is still lower than 3 VDD over 4, right? The compute subarray, as a result of this, compute subarray cells will still store 0 and reference subarray still store 1. And for 1 and 0, it's the same. Again, we have VDD over 2, which is lower than 3 VDD over 4, and the result is exactly the same as before. However, when we go to the last, let's say, row of the truth table where X and Y are both 1, what happens is that the average bit line becomes VDD now. So now the sense amplifier will compare it, and since the compute subarray's bit line has higher voltage than reference subarray's bit line, compute subarray cells will store 1, while reference subarray will store 0. When you take a closer look, that's actually the AND operation in compute subarray cells, while an AND operation for the reference subarray cells. Any question for this one? I'm sure it's, but yeah. Okay, so the many input case where we want to, for example, do 4-bit, 6-bit, 8-bit, it's really you manipulate the voltage in the reference bit line. So we particularly select VDD and VDD over 2 to perform 2 input AND operation here. For example, in order to do 4 input AND operation, what you need to do is that you will have 3 VDD and VDD over 2. This is because we want to distinguish between all 1 and the others. So for more details, you can check the paper for example, 2-bit OR and NOR operations, and actually how we generalize it to many inputs. And again, the characterization methodology is the same. We sweep the row A and row B addresses to cover all rows in 2 neighboring subarrays. And we have 3 key takeaway lessons from this analysis. First, off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations. And they can perform it with very high reliability. And data patterns slightly affect the reliability of AND, NAND, OR, and NOR operations. So here's our first result. In the x-axis, we have the number of input operands. Basically, the leftmost is 2 input operations, and the rightmost is 16 input operations. And the y-axis, we have the success rate distribution again. And the hue, each colored box will represent a different operation. So as we can see here, that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input and OR and NOR operations, and they can perform these operations with a very high, more than 94% success rate. And one maybe thing that I would like to explain here is that there are two interesting things. As you increase the input operands, you get higher success rate. This is because what we observe is that for each operation, the edge cases, all zeros and all ones are the deal breakers actually, where you get almost a random result. But so for 2 input, it's just you have 4 input patterns, right? All zeros, all ones, 1, 0, and 0. So it's the occurrence is, let's say, 1/4 for all ones. But when you go to 16 input, you have 2 to 16 input patterns, and having all ones in the input patterns is just 1/2 to 16. Very low, let's say, a possibility. That's why we observe higher success rates when we just go with the all random data patterns. Yes.
So if you open a larger number of rows, would you not have a problem with driving the results back to the larger number of rows?
So the question
is there a counterbalance effect here? Yes, I am.
So you're saying that when you use larger, let's say, rows to perform this input operands, now sense amplifier needs to derive the 32 values, right?
Yes.
Yes, normally that should be the case. I agree. But here, the sense amplifier actually first needs to distinguish the results, right? And the issue, what we see is that, so when you go to the extreme, this, interestingly, we still get very good results. So this is one reason is that we use, so first we do the NOT operation, and we have, let's say, a very bad cells, right? So in order to do this, you need to use the specific end-to-end data pattern, end-to-end activation pattern, 16-row opening in the both sides. So interestingly, when you have the symmetry, sense amplifier can somehow deal with that better than having, let's say, end-to-end activation pattern.
I see.
So that's why we also use end-to-end also. So you can use end-to-end to realize the 16 to 32 as like 16 input as well, right? So
I see.
It's just, let's say, adding more redundancy.
Mm-hmm.
But I guess that the most important point here is that whether sense amplifier can determine the difference between the, let's say, the voltage differences between the bit lines. After that, when you wait long enough, so we also test, it's not in the paper, but we also test that if you wait a bit longer, not just 36 nanoseconds, but 45, for example, you get a better result.
That makes sense.
Yeah.
Yeah,
So
you have more time to drive the cells.
Yeah, you have more time to drive, but we didn't rigorous analysis here. That's a good question.
Thank you.
Yes. So I can repeat it, actually. Mohammad is putting a lot of effort. That's why I'm waiting. Yes.
How do you deal with the fact that after a NOT operation, basically the result is on the other side? For example, if you want to calculate NOT B and A.
Yes. So the question is actually from the previous operation, the NOT operation. How so? Let me rephrase it maybe to audience. So you have the A value in one subarray, and when you do NOT operation, now the negated A value is there in another subarray. How are you going to move the data from there? That's one of the issues actually. So there are you can deal with that with modifying the DRAM chips. For example, if you enable Lisa, where you can actually move the data between subarrays, you can just perform Lisa operation. Another way of doing is that you can just write like say double, twice. So when you write the one subarray, you need to write another subarray as well, so that you will have the negated value and the same value at the subarray. So I think this is one of the issues that you can, let's say, one of the issues when you use real DRAM chips. But I believe with just redundancy, if you want to use real DRAM chips, I'm not suggesting that, but maybe with just little modification to using, for example, Lisa, could solve this problem and enable you to perform everything in DRAM. Okay, thank you. But it's a good question, yes. One more thing that I can add is that now you're using the half of the rows, because subarray uses half of the rows, right? So half of the rows are connected to other subarrays, half of the rows. So when you do this operation, you're just working on half of the rows. But the other half are connected to our other subarray, right? You can actually, not in one shot, but in two shots, you can just do both operations as well. But those things, those things are a bit complicated for, let's say, the system, right? For example, you can just use SIMDRAM out of the box right now, because it just uses the same subarray. But now you need to modify things. You need to orchestrate your data. You need to put your data in a way that you can work on it. But yeah, those are the issues for, I believe, the system integration, the part, and leveraging this FCDRAM4 as substrate. Yes. Any more questions? Yeah, thanks. Those are really great points. And yeah, now the next is impact of data pattern. So in the x-axis again, x and y-axis are the same. The only thing changes is that the hue shows the data pattern, all ones and zeros and random. All ones and zeros means that you, in a row, you just write all ones or zeros, and random, you just randomly initialize the rows. Why we do this? To understand bitline to bitline interference. If you have all ones and all zeros, it's just a bit perfect when you look at that. But if it's random, they can interfere each other more, right? That's our hypothesis, at least. So, but we observed that for just NOR operation, the average success rate, it's just there's less than 2% of variation across all tested number of input operands. And this trend is consistent across all tested operations, AND, NAND, OR, and NOR. And we conclude that data pattern slightly affects the reliability of AND, NAND, OR, and NOR operations. So there are a lot more things in the paper, detailed hypothesis and key ideas to perform NOT and many input AND, NAND, OR, and NOR operations, and how the reliability of ETH operations are affected by the location of activated rows. I believe this is a bit interesting. The temperature for AND, NAND, OR, and NOR operation, the DRAM spit rate, chip density, and die division. And we discussed the limitations on off-the-shelf DRAM chips. And the paper is available on arXiv and also available on GitHub. And let me conclude for just this talk, this part of the talk. So we demonstrated off-the-shelf DRAM chips can perform functionally complete operations, up to 16 input AND, NAND, OR, and NOR operations. And we characterize the success rate of these operations with many DRAM chips. And we highlight two key results. First, off-the-shelf DRAM chips can perform NOT and 2, 4, 8, and 16 input AND, NAND, OR, and NOR operations with very high success rates, and data pattern and temperature very slightly affect the reliability of such operations. So conclude that we believe these empirical results demonstrate the promising potential of using DRAM as a computation substrate. So that concludes this part of my talk. Do you have any questions? Yes.
Thanks. Okay, maybe I missed it, but I didn't get why for a smaller number of operands you get a lower success rate. What's the reasoning there? Is it because you have less redundancy?
So you're asking that when you increase the number of input operands, you get higher success rate. What's the reason for this? So let me explain once more. So the issue is that we initialize the data with random, and just we check the results, right? And also we traversed hopefully all the input space. So the real issue is that you can check the paper. We have a more detailed analysis over there. The real issue is that for AND and NAND, when you have all ones in the input patterns, because somehow sense amplifier cannot distinguish between all ones. For example, when you have all ones, you have 16 VDD in one side and 15.5 VDD on the other side. So for sense amplifier, the margin is pretty low. It's not just 0.5 when you, let's say, not simplify things. So that's why sense amplifier struggles in those when you have all ones. So if you use just 2 inputs, you have just 4 input patterns, right? All ones is just one of them. So occurrence of all ones is 1/4. But if you go 16 input, the occurrence is 1/2 to the over 16. So that's why you get higher, let's say, success rates. So there are some methods to increase this success rates in the next paper that will talk. Actually, also can be applied for the FCDRAM, the functional complete Boolean logic paper that we discussed.
Okay, so like this explanation holds for all the experiments, because like in all the experiments you showed, you get a better success rate if you increase the number of operands. Yes. That's the case. Okay.
Yes.
And my other question was, so now we can perform, let's say, AND and NOT and so on. But I was wondering, for example, if you want to perform a comparison, of course, you can do the AND and then you have to check if all bits are 1. But I was wondering, can you do that still in DRAM without modifying the circuitry, or do you still have to move the data to the CPU, perform the comparison, and bring it back?
What?
Like an equality comparison, let's say. You want to compare 2 rows. Is that possible in current of the shelf DRAMs?
So you're asking that can you compare 2 values using this, let's say, real DRAM chips?
Yes.
So not just directly, because first thing is that you cannot understand if it's equal or not. The second thing is that you can only understand, so sense amplifier only understand what is higher. So if you have the result in one side, so assume that you have A and B, somehow you put your data in a way that you can compare them. That's also another issue. It's just understand if A is higher than B. So you will get that. You won't get the exact comparison. You just get just A and B. If it's A greater than B. And another issue is that it won't work for just binary operations, because so we do it bit serially, right? So when you go bit serially, the bit index now with it's not binary. It's just the voltage value you have. For example, you have 1 0, which is 2, and you have 0 1, which is 1. So if you put them in the bit serial way, DRAM cannot understand which is higher, because for DRAM's perspective, both are the same thing. You have just VDD over 2 in one side, VDD over 2 in other side. So you need to do something different over there. But yeah, that's a bit challenging and a bit limited applicability, because you need to do a lot of things to just compare just 2 things. Thanks. Yes.
So you made a statement that said the sense amplifier just performs a comparison between voltages. Would that mean that if you have, let's say, VDD by 4, let's say VDD by 5 on one end of the sense amplifier and VDD by 4 on the other side of the sense amplifier, it would still pull the side with VDD by 4 to 1?
Yes.
Okay, so then this means that you can easily enable comparison operations, right?
So first, if they're too close in real DRAM chips, as we also observe, you can get just random values, and which is also Quack range shows, right? So when you have very close to, let's say, if your terminals are very close, you will get just random values. That's one of the issues. And the second is, as I said, you can just get the result of if A is bigger than B. That's just the comparison that you will get if they're distinguishable, the voltage levels are distinguishable.
Okay, thanks.
Yeah. Okay. What time is it? Okay, I have 20 minutes, so I'm gonna a bit speed run. Not that much, but a bit. So the second paper is simultaneous manual activation of shelf DRAM chips, experimental characterization and analysis. Here I'll skip some parts really and focus on some parts that I believe are a bit important, like row decoder circuitry and multi-row copy. I'll explain it a bit in detail. So the motivation is still the same. Processing using DRAM is a promising paradigm to elevate data mode bottlenecks. And up until that point, off-the-shelf DRAM chips can perform 3-input majority and in-DRAM copy operations. Our goal is here in this to analyze and understand the computational capability beyond that of prior works and the robustness of such capability under various operation conditions, pretty similar to previous one. And for this one, we test 120 DDR4 chips from 2 major manufacturers, and we observed that we can actually perform not just majority of 3, but majority of 5, 7, and 9 operations and copy 1 DRAM row to up to 31 different rows at once. And the second is one of the important findings, I believe, is storing multiple redundant copies of majority's input operands, which we call input replications, drastically increases the robustness of these operations. For majority 3, we observe that you can achieve 30% higher average success rates. And the third, operating conditions, we tested temperature, voltage, data pattern, and timings affect robustness of in-DRAM operations by up to 12%. So, and the code, we open source our infrastructure and it's artifact evaluated. So in this study, we leveraged simultaneous manner of activation in the same subarray in one subarray, and we observed that we can perform majority of X, where X is higher than 3, and we can, using this multiple row activation, we can increase the robustness of majority of X operations and copy 1 row's content to multiple rows. So the key observation for multiple row activation is the same. You activate 2 rows in quick succession to simultaneously activate many rows. So in this study, we try to reverse engineer what's going on over there. So we try to reverse engineer the row decoder circuitry that one specific DRAM chip has, but it's just a hypothetical way of doing it. So we believe that simultaneous manner of activation is possible due to hierarchical DRAM row decoder design. So this is your typical DRAM subarray, and what happens is that when upon an activation, you send a row address right. What happens is that row address comes to row decoder, and row decoder decodes it and assert a specific word line. So, and in our, let's say, reverse engineering efforts, we hypothesize that there is, in one specific DRAM chip, there is 5 stages of decoders, and this is hierarchical. So there are multiple, so these stages are connected to each other in a way of a tree. I will represent those approach in a second. So what happens is that you serve the row address, some parts of the row addresses to each stage, and you, let's say, decode them in parallel to, let's say, efficient and do it in fast. So we can visualize this hierarchical row decoder circuitry as a tree. So you can think of that there's a master word line at first, and each, let's say, depth of the tree is the stages, basically. And since we do it in parallel, you can think of that they are connected to each other. So there are, let's say, one root, and there are, let's say, nodes, and the leaves are the word lines, basically. And these are, let's say, the nodes are the decoder outputs. So let me give you an example what happens when we activate a row in this visualization. So you issue and activate the row A. So essentially, you would like to activate word line A. So what happens is that we decode the row, DRAM decodes the row A address and asserts the corresponding signals. For example, stage 1 is the 3rd node, and the stage 2 is the 2nd node, and the stage 5, which is multiplied a lot of times in the, let's say, visual space, it's just 1. So, and then DRAM follows the asserted node path from root to leaf. You can think of that there are AND gates between each end of the outputs to the next decoder's input. So it resembles a let's say, asserted node's path. And as a result of that, you assert a word line. So, and then when you precharge it, you deassert everything. And then what happens when you try to activate many rows? So back-to-back activate commands with violated timings asserts many more signals. So it's the same as, so assume that we activate row A and then we violate the timings. So what happens is that first we keep, since we interrupt the precharge command, you keep the previously asserted signals active. So DRAM thinks that they're deactivated, but since you violate it now, they're still active. And then you're allowed to issue another activation command, which is activate row B. Now you issue activate row B, this row decoder circuit will decode row B as well and assert many corresponding signals to, let's say, activate word line B, right? Now you have more paths, right? Now you follow the newly asserted node's path, and as a result of this, you activate multiple rows. I hope it's clear. So this is how we, let's say, visualize it in a logical way. So in a physical way, we hypothesize that there's a 5-stage of decoder, 2 to 4, 2 to 4, 2 to 4, 2 to 4, and 1 to 2. And we actually have a, let's say, A3, we had an actually A3 paper that we write. So we had a CSV, and then we tried to reverse engineer one by one, each bit, what's going on. And we asserted signals over there to reverse engineer it and follow the path. And after that, and we try to, let's say, though that was very low level, right? Like decoders and gates, and it was very hard to explain things. And then we move to this, let's say, tree visualization. I believe you have a question, Mohammad.
Yes, I have. So this makes things quite clear now. Do we have latch at each, steps of this recorder?
What is?
Do we have latches?
Latches. I believe so.
Because otherwise we couldn't.
How are you going to store the data, right? So actually in each output, we believe there's a latch. We also visualized it in the paper, but I didn't put it here for the high level abstraction. But yeah, you have latches to, let's say, keep the value, right? Because you assert the word line, and we believe that, like, just to keep the word line open, you need to, let's say, keep these nodes asserted all the time until you issue precharge. In order to do that, you just have latches. But they could have something else, I don't know.
Mm-hmm. Thank you.
Yeah. Yes.
Do these hierarchical decoders also exist at the subarray level? Like at the sub-word line level? Yeah.
You mean?
So yes, you have the global row decoder?
So actually, in the paper, that's a bit more clear. So we believe that there's a global row decoder that decodes the subarrays. And then inside the subarray, you still have a row decoder, which is, let's say, not that, it gets some parts of the, let's say, row addresses. So here, you can think of that this root is actually the subarray enabled signal, or subarray, the bit that in the row addresses that enables the subarray. So something like that.
I see. Yeah.
Yeah. And this also explains that why you can activate 2 subarrays, and in a way that, right? So you just change the row addresses, but still the lower parts of each subarrays are affected, right? So that you activate many more rows. So that's how it happens in our assumption. But we don't know. We didn't, let's say, image the row decoder inside the DRAM and try to reverse engineer. It's just brute force reverse engineering, I will say. And Yahya did a lot of reverse engineering for this one. So there are a lot more discussions on how we do this and why we do this and why this happens and why we stop at 32. Basically, maybe I can give you that. So for that specific chips, we observed that we can activate up to 32 rows. So the real result was that actually we had just 5-stage decoder. It's just 2 to the power of 5, which is 32. If you had more stages, you would activate more rows with just 2 activation commands. Yeah, that's it. So there were, as I said, there are more things that we uncovered, like majority of X, the robustness of how we increase it. But I'm just gonna give the key insight for multi-row copy operation and show one result for the sake of time. So the key idea for multiple row copy is that I believe it's straightforward. You simultaneously activate many rows to copy one row's content to multiple destination rows. So for row clone, which is proposed in 2013 and showed in Compute DRAM in 2019 that it is possible in real DRAM chips, that what happens over there is that you activate source, which will fetch the content to sense amplifier, right? And then you activate destination. And as a result of this, similar to NOT operation, but in same subarray, you copy the data from source to destination. For multi-row copy, the only difference is that you have now multiple destinations. So you activate source again, now fetched into sense amplifier, and then you activate the destinations again. As a result of this, now you copy source to multiple destinations. And so this is the robustness of multi-row copy. In the y-axis, we have the success rate, and the x-axis, we have the number of destination rows. From left to right, number of destination row increases. These are odd numbers because, so we activate 2, 4, 8, 16, and 32 rows normally and simultaneously. So since you already activated source, you have, let's say, -1, let's say, number of simultaneously activated rows -1 destination rows. So we observed that interestingly, it's very robust. The average of the success rate average is more than 99.98% across all tested number of destination rows, even with 31 rows. And we conclude that off-the-shelf DRAM chips can copy one row's content to up to 31 rows with a very high success rate. So the the extended version is available on archive. And the work is open source and artifact evaluated, got every badges in the artifact evaluation, and you can download our code from GitHub and start testing your DRAM chips right away. And that was this paper, and also concludes my talk. And I'm happy to answer your questions if you have any.
Any other questions?
I have one more question. One more question.
Yes.
So with the commodity of the shelf DRAM chips, you cannot get, let's say, 100% reliability. And let's say, assuming that we have the correct hypotheses for the row decoder, which is hierarchical in nature, do you have any directions on how we could redesign the row decoder to get, let's say, better accuracy? So, given that you provide, let's say, 2 addresses, the 2 addresses that you want to.
I think the success rate is more dependent. So I think dependent on everything that we touched here, like row decoder design, the sense amplifier, the process variation that you have, and the bit line, let's say, the capacitance, how long your bit line is. And so if you would like to get 100%, first we need to understand where the error comes. If it's coming from the specific columns every time, whether it's coming from, let's say, not specific, but just randomly. If it's randomly, you can think of that maybe the row decoder circuitry, since we are not, let's say, fine grain over there. It's just in the DRAM bender, what you can get is the 1.5 nanosecond interval. So you can just go with that 1.5 nanoseconds, 3, 4.5. You don't have a lot of choice over there. For example, if we had 1.8 nanoseconds, maybe everything was perfect, that you don't need to change anything. But to be able to claim or hypothesize those things, I believe we need to test more rigorously to understand where those errors are coming from.
Okay. Yeah, I think what you said about trying to image the row decoder would be one way to first make
Yeah, but-
sure?
Yeah, you need to also do it in, let's say, live, right? So you need to issue the act, but you need to also observe. I'm not sure if it's possible.
Yeah, that's probably not possible.
So you can do it offline. You can do it
Mhm.
imaging offline because you need to, let's say, cut the chip in a way that to image that. If you cut it, I'm not sure if it will be alive.
All right. Thanks.
Yeah. Okay. Any more questions?
Okay, thanks a lot, Ismail, for your excellent talk. And I think we can move on to Nisa's talk.
Thank you very much.
Okay, the next talk will be given by Nisa. Nisa is a third-year PhD student in Software Research Group at ETH Zurich under the supervision of Professor Mutlu. She is interested in security, reliability, and safety, robustness of memory systems, and designing effective and efficient solutions to address robustness issues. So, the stage is yours. Feel free to start whenever you're ready.
Thanks a lot, Mohammad. Okay, so in this part of the workshop, we will revisit system security in the context of processing in memory. Let's start with a brief self-introduction. I'm Nisa. I'm a PhD student in Software Research Group, and I'm broadly interested in memory system security and also in processing in memory architectures, which I will talk about in this talk. So I will present one of our recent works called Revisiting Main Memory-Based Covert and Side Channel Attacks in the Context of Processing in Memory. And this work was presented in DSN last month, so it's pretty new. And yeah, so let's get started with the brief executive summary. So processing in memory architectures alleviate data movement bottleneck by bringing computation closer to where data resides. And these architectures and techniques are being adopted in real products because of their large performance and energy benefits. However, no prior work analyzes and evaluates the security of PIM architectures against timing, side, and cover channel attacks. In this work, we make the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to two main reasons. The first one is that these architectures and techniques provide direct main memory access to user space applications, which is a key building block for high throughput main memory-based timing attacks. And second, defenses against these attacks are either highly costly or they're inapplicable to PIM architectures. And we introduced Impact, which is a set of high throughput in-memory processing-based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact provides high leakage throughput by first eliminating expensive cache bypassing steps used in many main memory-based timing attacks and leveraging the intrinsic parallelism of PIM operations. In this work, we have 3 case studies. We first built 2 high throughput cover channel attacks leveraging different PIM architectures, and then we demonstrate a side channel attack that leaks private information of concurrently running victim applications with low error rate. And lastly, we talk about and we discuss and evaluate 4 different countermeasures against impact and eventually conclude that mitigating impact incurs high performance overheads. And this highlights the need for low-cost mitigations against impact for robust future systems. Impact is artifact evaluated and open sourced, and you can access all our data and source code from this link. And this is the outline of my talk. I will move on with the motivation and the problem. So we talked about the data movement bottleneck. Let me recap again. Today's computing systems are processor-centric, which means that all data is processed in the processor at a great system cost. This is because when we want to do a computation, we first need to fetch the data from the main memory and then do the computation. And after that, we need to send the results back to the main memory. And this leads to spending more than 60% of the total system energy on data movement. Processing in memory architectures alleviate data movement bottlenecks by moving computation closer to where data resides. And such architectures can be implemented by first adding logic near the memory arrays in what is called processing near memory, or by using the analog operating principles of the memory cells to perform computation in what is called processing using memory. A set of PIM architectures are already implemented in real products today, and some of which are shown in the slide as examples, and many more are expected to be adopted in the near future because of the large performance and energy benefits. Therefore, it is very important to investigate the security aspects of such techniques and implement countermeasures to avoid potential widespread security vulnerabilities that their deployment can cause. However, no prior work analyzes and evaluates the security of emerging PIM architectures against timing, covert, and side channel attacks. In this work, we will focus on main memory-based timing channel attacks, where an attacker exploits the shared main memory structures to leak data or create covered communication channels between two attacker processes. A prime example of this is DRAM row buffer-based attacks, and I will explain the attack with an example in the slide. Here we have a DRAM bank with multiple DRAM rows, all connected to one row buffer, which acts as an in-DRAM cache. To access the data in one of these DRAM rows, we first need to open the DRAM row, which copies the content of the row to the row buffer, and then perform read and write operations from this row buffer. And the memory controller starts the next accesses to the same row with lower latency because the content is already in the row buffer. However, if we want to access another row in this DRAM bank, the memory controller first needs to close this row and then open the new target row, which brings the data to the row buffer. And this takes some time, so an access to any other row that is not open already is served with higher latency. And these two different latency values create two distinct states which are observable from the user space applications. So an attacker can exploit these different states of low latency or high latency based on the row buffer state to create covered channels to send messages in between two processes by encoding each bit of the message with high or low latency. Or an attacker can exploit this again to spy on other victims that are concurrently running in the same system using the same main memory in what is called cross-CPU attacks, for example. And in this work, we make the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to two main reasons. First, these architectures provide direct access to main memory, which is a key building block for high-throughput main memory-based timing attacks. And second, defenses against these attacks either incur high performance overheads or they are not applicable to PIM architectures. Let's now talk about the first reason. Here we have a system with a core and a main memory, and we have our attacker. The attacker wants to leak information, and it does so by timing a memory access. To do so, it first sends a request to the main memory, reads data stored in the address A, and gets the data back. And by timing this sequence, the attacker can leak information of 1 bit, for example, based on the row buffer state. And to leak even more information, the attacker needs to repeat this process and access main memory a lot of times and then measure these access latencies. And this is why high throughput attacks require reliable and fast access to main memory such that it takes less time to do these operations. And in compute-centric architectures, this is difficult because we have our deep cache hierarchies between the core and the main memory. These deep cache hierarchies filter memory accesses such that the attacker's accesses are served from the cache hierarchy because they exhibit high locality and they don't access the main memory itself. And therefore, the attacker cannot observe the row buffer states. And these deep cache hierarchies also incur additional latencies. Even if the memory request goes to the main memory, it does so after a lookup in the cache, which incurs additional latency by doing so. And this is why attackers manipulate the caches to access main memory with a higher probability. So they either use eviction sets, which basically creates many accesses to the many memory requests such that it evicts one target cache line from the caches, and then the next accesses to that cache line goes to the main memory, or by using specialized instructions like cache flush instructions in, for example, CL flush instruction. And after these steps, the attacker can access the main memory and observe the row buffer states. But this comes at the cost of a higher access latency because of the extra memory request that it needs to generate. When we look at the PIM architectures, this is different because these architectures provide user space applications with fast and reliable direct main memory access. First, let's look at the processing using DRAM. So processing using DRAM techniques operate on bulk data that is stored in the DRAM and do the computation inside the DRAM such that they fundamentally bypass caches completely. And when we look at the processing near DRAM cases, the compute units that are implemented near the memory, they are very lightweight and they are very simple computational units, and they usually have small caches or even no caches are implemented due to thermal dissipation limitations, such that an attacker can execute their code in these compute units and have direct access to main memory. Let's look at why this is important by looking at the impact of direct memory access on leakage throughput. Here we are simulating a system with increasing analysis sizes, and these sizes corresponding to real systems that is written over there. And as we go to larger analysis sizes, the eviction latency increases because it's more costly to access the caches and evict something from the caches. And on the y-axis, we have the throughput in terms of megabits per second, and we evaluate two different attacks. The first one is called the baseline attack, which is the state-of-the-art row buffer-based cover channel attack with cache eviction sets, basically creating a lot of memory requests to evict one target cache line. And in the second attack is called dynamic memory access attack, which is the same attack, but this time it bypasses the cache hierarchy completely without paying the extra latency cost. And this is the throughput results of the baseline attack. And as you can see, as we go to larger LLC sizes, this throughput reduces a lot because of the higher cost of eviction. And this is the throughput of the direct memory access attack. And it is significantly higher than the baseline attack due to not paying the cost of cache eviction. And second, the throughput is consistent across increasing LLC sizes because this attack bypasses caches completely, regardless of the LLC size. So we conclude that direct memory access attack maintains its high leakage throughput regardless of the LLC size, in contrast to the baseline attack. And now let's move on to the other reason. Defenses against these attacks either incur high performance overheads or they are not applicable to PIM architectures. Again, we have our system with an attacker, and the defense team here has two options. So a defense can first fundamentally eliminate the timing channel, for example, by using closed row policies such that the row buffer state is not observable or it does not leak any information because it will be always closed, or having constant time memory, meaning that all requests will have the same latency, but it will be the worst case latency. And as we show in the paper, this incurs high performance overheads because of the increased memory access latencies. And these defenses all have very high performance overheads. And the second option as a defense is to restrict the use of the timing channel, for example, by restricting the cache flash instructions such that the attacker cannot reliably access main memory whenever it wants to, or by detecting attacks based on cache statistics and taking mitigative actions after that point. And the key idea of this method is basically the attacker would have a high cache miss rate because it would target the main memory in most of its memory requests, and then this requires missing in the caches. And after that, the defense can understand there's an attack going on and can either stop it or take other mitigative actions. And when we look at the PIM architectures, these are not applicable because PIM architectures provide direct access to main memory by either bypassing the caches completely or basically allowing the attacker to execute code in near memory compute units that have direct access. And this is why these defenses that restrict the use of the timing channel with cache management methods are inapplicable to PIM architectures. And this brings us to impact. Impact, we introduce impact, which is a set of high throughput in memory processing based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact provides high leakage throughput by first eliminating expensive cache bypassing steps, and second, leveraging intrinsic parallelism of PIM operations. In this work, we have 3 case studies. 2 of them are covered channel attacks based on different PIM architectures, processing near memory and processing using memory. And lastly, we have a side channel attack, a genomic privacy attack based on processing near memory architectures. Before moving on to the case studies, I want to first talk about our evaluation methodology. So we evaluate these systems using simulations. And these are the architectures that we assume as baseline for processing near memory and processing using memory. These architectures are basically coming from seminal works that are very important. So it's very important to assess their vulnerabilities. However, they are not right now widely available for our use. And we use these system configurations to simulate a modern system that supports these architectures. And we compare our attack, specifically the cover channel attack, and we compare it to the state-of-the-art row buffer-based cover channel attacks. And all of these are open source and available in this link. Okay, now let's talk about the first cover channel based on processing near memory architectures. In this case study, we assume a PIM-enabled instructions-based processing near memory architecture, which introduces compute units called PCUs on the host side and on the memory side. And a management unit manages these PCUs and decides where to execute an operation based on its locality characteristics. Here we have a PIM instruction, which does addition. It adds Y to the data stored in the address X. And the management unit decides if this operation benefits from the cache hierarchy, it decides to execute it on the host side. And if it benefits from reduced latency, this instruction will be executed on the memory side. Yeah. So our attack's key mechanism offloads attack instructions to a memory side PCU to eliminate expensive cache bypassing steps. And let's look at an overview of the attack. Here we have our DRAM with a lot of DRAM banks, and each of these DRAM banks correspond to one PCU. And we have our sender and receiver processes in the system. And these attack processes, the sender and receiver, prepare for the attack by first collocating their data in the same sort of DRAM banks as shown in this example. This requires no sharing of real data, so they don't share any real data. They just allocate pages in different DRAM rows that are located inside the same set of DRAM banks. And as a start of the attack, the receiver first initializes the row buffer states by executing a set of PIM instructions, each corresponding to one PCU that corresponds to one DRAM bank. And this results in bringing the receiver's data to the row buffers. And after this point, the sender wants to send this message, and the sender splits this message into M-bit batches. M here is the number of banks that will be used in the attack. And then the sender transmits M bits at once by mapping each of these bits to one PCU that corresponds to one DRAM bank. And based on the value that is assigned to each PCU, the sender can execute a PIM instruction, for example, to send a logic 1 value, which results in bringing the sender's data to the row buffer. And if the bit assigned to a PCU is 0, it executes a no-op operation, which results in no change in the corresponding DRAM bank, such that we change the row buffer state where we want to send the logic 1 value. And if we want to send the logic 0 value, the row buffer state stays the same. And to receive this message, to decode this message, the receiver executes the same instruction sequence as the initialization, but this time it measures the access latency or execution latency of these PIM instructions. So in this example, for bank 0, the receiver measures a higher latency for this operation because the row buffer state has changed and the sender's data is in the row buffer. And then the receiver needs to bring his data to the row buffer again to do the operation. And this results in a higher latency. And in the last bank, the sender is transmitting a 0 value and the receiver measures a lower latency. And after this point, the receiver can decode the message completely. And we validate this proof of concept attack by sending a 16-bit message using 16 DRAM banks. Here on the x-axis, we have the bits of the message that we want to transmit. And on the y-axis, we have the latency measured by the receiver in terms of cycles. So these are the latency results. And as you can see, the latency values corresponding to logic 0 values are much lower than the latencies we observed for the logic 1 values that corresponds to row buffer conflicts. And looking at this, at the end of this proof of concept validation, we conclude that the receiver can successfully determine the transmitted bit values by detecting the row buffer conflicts using PIM operations. And next, we look at communication throughput by using one sender and one receiver process using 16 DRAM banks across increasing LLC sizes. And we conclude that this attack type provides a high communication throughput of 8.2 megabits per second by eliminating expensive cache bypassing steps. And I will put this number into context after we talk about the second covered channel by comparing it to the state-of-the-art attacks. If there are no questions, I will go to the next. Yes, please. There is one question.
Okay, so I'm not super aware of this hardware works, or like the security works, but I was wondering, so how did it work for the previous protocol? Do you have to like, do you come up with a protocol and then design an attack based on it, or that protocol of the sender and the receiver is already used in practice? So yeah, basically my question is if this protocol of the sender and receiver splitting the message into m-bit batches and sending is a protocol that is being used already in practice, or if you come up with this protocol?
So a similar attack is done with row buffer conflicts prior to this work. Okay. That has the same like benefits with parallelization using like different DRAM banks. It's not exactly like this. In the prior work called DRAM, they multiply the sender and receiver pairs in each DRAM bank to send separate DRAM bits. Sorry, not DRAM bits, separate bits of the message inside these like DRAM banks. This is slightly different, and it is basically adapted to work in PIM architectures. And what we show in this work is that even though the underlying timing channel existed before, we are showing that PIM architectures amplify its effect. So basically making them more critical in terms of like communication throughput, which I will compare it against the prior work in a second.
Thanks.
Okay. If there are no other questions, I will continue with the next covered channel. Okay, so now let's talk about our second case study, which is a covered channel based on processing using memory architectures. And in this part, we assume a processing using memory architecture that provides user space applications with row clone, which enables bulk data copy and initialization operations. Let's remember how DRAM operates to understand the baseline better. Here we have our DRAM bank with multiple DRAM rows again, and one of them is called source or SRC. And if you want to access the data stored in this row, the memory controller first needs to activate or open this row, bringing its content to the row buffer. And after that, if you want to access another DRAM row, the memory controller first needs to close or precharge this row, writing the content back to the cells, and then perform the other activation to another row called destination in this case, or DST, which brings this data to the row buffer. So this is the baseline operation of DRAM. And prior works show that by violating the sequence, by removing the precharge in between, we can copy the content of one row to another row in the same DRAM bank. This is how it works. So the first activation copies the content of the source row to the row buffer. And by removing the precharge and issuing the activation after the first activation, DRAM copies or like writes the content of source to the destination cells. And this effectively copies the source row's content to the destination row inside the DRAM module. And we assume a system that supports two copy operations that exploit parallelism. The first one copies ranges across all banks. Here we have a copy operation from range A to range B. And the core translates this into multiple operations, each corresponding to one DRAM bank that copies range A to range B corresponding to those in those DRAM banks. And in the second copy operation, we assume we can selectively copy with a mask operation, meaning that we can send a bit vector as mask, and then the core then translates this copy operation into multiple, again, copy operation, but this time it selects which DRAM banks will execute this copy operation. And this is the baseline system that we assume. And let's look at the attack overview. So here again, we have our DRAM with multiple DRAM banks, and inside these DRAM banks, we have receiver rows, 2 receiver rows that the receiver can do row clone operation, and we have 2 sender rows that the sender can also do copy operations with. And again, they do not share any actual data, or they do not collocate in the same DRAM rows. And the receiver starts the attack by first initializing the row buffer states with multiple row clone operations and brings its data to the row buffers in all of these DRAM banks that will be used in the attack. And the sender wants to send this message, and the sender transmits this message by using the message as the bit vector for the mask copy operation. What it does is basically, it uses each bit to determine if row clone operation will be executed in one of the selected DRAM banks. And here, for example, for bank 0, this results in copying the sender's source to the sender's destination row, bringing the sender's data to the row buffer, and in the other DRAM banks, the mask bit is 0, such that it results in having no change in the row buffer states. And the receiver, after this point, receives the message by sending a separate row clone operations again. And for example, in bank 0, the receiver this time measures a higher latency for its row clone operation because its data is not in the row buffer. And then for the other, this is like a basic row buffer conflict. And in the other banks, the receiver measures a lower latency because the data is still in the row buffer. And we validate this proof of concept by again sending 16-bit messages using 16 DRAM banks. And this plot is very similar to the one I showed you before. On the x-axis, we have the message bits, and on the y-axis, we have the latency measured by the receiver. And we can see that the receiver measured a higher latency that corresponds to row buffer conflicts when the sender is transmitting a logic 1 value. And we conclude that the receiver successfully determines the transmitted bit values by detecting the row buffer conflicts using row clone operations. And we evaluate the communication throughput by using one sender and one receiver process using 16 DRAM banks across increasing LLC sizes. And we conclude that impact with processing using memory architectures, it provides a high communication throughput of 14.8 megabits per second by also exploiting intrinsic parallelism of processing using memory architectures or operations. And now let's look at the comparison against other covered channel attacks. So here again, we, yes, please.
I have a question about the timing attack. So would one way to solve this be always perform a pre-charge after doing a row clone?
Yes, so for row clone based attack, it would solve the problem because we would pre-charge it after each row clone operation such that the row buffer state will always be like empty, or it will always be like a row buffer miss. Mm-hmm. And then it is difficult to observe the latency difference.
Right. Is there any benefit to keeping the row buffer open after row clone though?
So after you copy the source's content or like the content that you want to copy, if you have other memory requests that wants to access that row, having it open would be beneficial because you would have lower access latency. But we did not really looked into like applications exhibiting that behavior. It's like a design choice in a sense. But it's one option that the systems can use to have the benefit of having row buffer hits after copy operations.
Okay, I see. So the main thing you rely on here is to make sure that the row buffer is open so that you sense a lower latency when you send requests to the same bank.
Yes.
Okay, thanks.
Okay. Okay, then let's continue. So here we will see the cover channel throughput comparison against state-of-the-art attacks. And again, we are simulating a system with increasing LLC sizes, and you can see the LLC sizes on the x-axis. And on the y-axis, we have the leakage throughput in terms of megabits per second. And we evaluate different types of attacks. First, we have drama-based attacks, which is the state-of-the-art row buffer conflict-based attack. Here we have two different types of the same attack, one with cache flash instructions and one with eviction sets. And next we have an attack, the same row buffer conflict-based attack, but this time it uses DMA engines to directly access the main memory and bypass the caches. And lastly, we have the impact attacks that we just talked about. So these are the throughputs, leakage throughputs of the impact attacks. As you can see, they are consistent across LLC sizes. And next we have the drama-based attacks, leakage throughputs. And as you can see, as we go to larger LLC sizes, their throughput reduces a lot because of the eviction or cache access latencies increasing. And next we have the leakage throughput of the DMA engine based attack, which again has a consistent leakage throughput across increasing LLC sizes because it bypasses the caches, but it is also much lower compared to the impact or, for example, drama CL flash attack. And this is basically due to the OS related overheads, such that the DMA engine has more overheads that dominates the overall latency of the attack and bottlenecks the throughput significantly. And again, we conclude that impact-based attacks achieve high leakage throughput across all LLC sizes, and they also outperform all state-of-the-art main memory-based attacks across all LLC sizes. And next, we compare impact attacks to each other by comparing the latency of the sender and receiver routines. And this is the sender routines latency in terms of cycles. And as you can see, when we have impact PUM or like row clone based impact, the sender latency is really lower than the other attack case. This is because we exploit the parallelism by using copy operations that translate into many other operations that corresponding to different banks. And when we look at the receiver routines, they are roughly the same because the receiver needs to poll each DRAM bank to determine the bit values one by one. And we conclude that impact PUM's sender routine takes less time, and this translates into higher throughput. And this is because of the parallelism of PUM operations. Okay, lastly, we have our genomic privacy attack based on processing near memory, which I will just talk about the highlights in the interest of time. Here we target a very important application called DNA read mapping, which is a fundamental task in genomics. Here we have our DNA and sequencing machines gives us DNA fragments by analyzing this DNA. And after this point, the read mapping tool creates a full genome or tries to create a full genome, taking these fragments and trying to sort them in order using a reference genome. And this task is used in many applications like biological research, forensics, drug development, or personalized medicine. And as you can imagine, this application read mapping is very privacy sensitive because the data that we deal with is extremely privacy sensitive and you don't want to leak any information on your DNA. So it would be really bad to attack it. And let's look into the read mapping with more detail. Basically, you can think of this as a string matching problem. We have our fragments, and then we are trying to order it to have a full genome. And prior works use hash table based methods to do so. And these hash tables are huge. This is why they are distributed across DRAM banks such that we have more parallelism. And prior works also show that this task can be accelerated with processing near memory architectures. And this creates an opportunity for us to create an impact attack. And I will spare the details, but you can find them in the paper. But we conclude that an attacker can successfully characteristics of the DNA sample with low error rate by leveraging PIM operations. And you can check our paper if you are more interested in more of that. Okay, so this concludes the case studies that I will talk about. And finally, we can talk about how to mitigate impact. So in the paper, we looked into existing mitigations to row buffer conflict-based attacks, such as bank-level partitioning, closed row policy, constant time memory. And we show that they are very restrictive, and they're also highly costly because of the additional overheads coming from increased memory access latencies and so on. So we looked at a more low-cost solution and proposed adaptive constant time DRAM, in short ACT, which key idea is to only employ constant time memory when there is high interference in a DRAM bank. So what it does is it counts the row buffer conflicts within a part of the execution time and then compares it to a threshold and then decides to enforce constant access latency in the next time window. And by doing so, we can reduce the channel capacity, but this does not fundamentally mitigate impact completely because in the default latency parts of the execution, you would still be able to leak some information and have your attack, but at a reduced rate. And after evaluating this, we also saw that reducing the channel capacity to be comparable to the state-of-the-art attacks still induces a very high performance overhead. And this again shows that mitigating impact incurs high performance overheads and more research is needed to find low-cost solutions for future robust systems. Okay, so we have more details and analysis in the paper, starting with the genomics side channel attack with more operational details and more analysis about the throughput and the accuracy of the attack. We have mitigations for impact, discussing and evaluating 4 countermeasures with more detail again. And we have discussions on other potential PIM-based attack vectors or applicability of impact to complex PIM architectures and future DRAM devices and restricting access to PIM operations. And many more are available in the paper. Impact is open source and artifact evaluated, and you can check our GitHub repo and play with it and have fun with more attacks. And let me conclude my talk. So in this work, we have the key observation that PIM architectures create opportunities for critical main memory-based timing attacks due to 2 main reasons. First, that these architectures provide direct access to main memory, which is a key building block for a high throughput main memory-based timing attacks. And defenses against these attacks are highly costly or they're not applicable to PIM architectures. And we introduce Impact, which is a set of high throughput in-memory processing-based timing attacks that leverage direct and fast main memory accesses enabled by PIM architectures. Impact provides high leakage throughput by eliminating expensive cache bypassing steps used in many main memory-based timing attacks and leveraging the intrinsic parallelism of PIM operations. We talked about 3 case studies. We demonstrated 2 covered channel attacks leveraging different PIM architectures, and they all achieve high throughput communication. And we showcased a side channel attack that leaks private information of concurrently running victim applications with low error rate. And lastly, we talked about 4 different countermeasures against impact, eventually concluded that mitigating impact incurs high performance overheads. And this concludes my talk, and I would be happy to take any questions.
Thanks a lot, Nisa. Any other questions from the audience? Okay. Then, thank you so much for your excellent talk. And I think we can conclude the morning session of the workshop. I think we have lunch break until 1:30, right? And then we will get back. Thank you so much.
Thank you.
It should work. Is it working? Checking. Yes, this is on. Should be hearing you. Because I can see, I can hear the feed. Yeah, yeah. Okay. This thing is fine. No. Okay. Maybe I'll just. Let the video file. That's it. Yes. I have 1 hour, right? Yes, I think 2:30. Then after meal, any is there.
I could see it before, but now I can
Maybe we can share
answer again.
share the whole screen. Do we share the whole screen?
No.
That's true. Okay.
Is it up now? Is it again gone?
Yeah, if you see on Zoom, YouTube.
If you're seeing in Zoom, it should be coming to it. Yeah. Okay.
Okay, welcome back, everyone. It's my pleasure to introduce you Rahul. Rahul is a senior PhD student working with Professor Mutlu at Safari Research Group in ETH Zurich. His research interest lies in high-performance microarchitecture and memory system design with a focus on autonomous learning-based techniques. Previously, he had contributed in various capacities to Intel Processor Architecture Research Lab and AMD. So Rahul, the stage yours. Feel free to start.
Thanks, Mohammad. Okay, everybody can hear me, I guess. It's coming there. Okay. And I hope you are alive after the lunch break. And I hope I'm not going to bore you to the death. Okay. Okay, so today my talk is going to be titled on mitigating the memory bottleneck with data-driven and data-aware microarchitectures. So hopefully this is also going to be very much close to my thesis title eventually. So yeah, that's something that maybe it's a dry run of my thesis defense. Who knows? Okay, so that's me. I'm a senior PhD in Safari. I have a Safari research group working with Professor Onur Mutlu. And previously, as Mohammad mentioned, I was also working in Intel Labs and AMD. If you want to learn more about my research, that's a website that you can follow. So my primary research interest lies in high-performance microarchitecture, memory subsystem design, and today I'm going to discuss more about data-driven and data-aware microarchitecture design. Now, you might be thinking, what exactly is these two terms, right? So data-driven, data-aware. So let me break it down a bit more. So as we know that today's computing is heavily bottlenecked by data, right? So from large-scale recommendation systems to emerging applications like genome sequence read mapping, in many cases, data is often the performance and energy bottleneck found in these workloads. But then as the architecture stands today, they are very terrible at exploiting this vast amount of data and metadata that are available to us to make autonomous and adaptive decisions. In some sense, we think of it in this way that the architectures are taking human design driven decision, like we as a human designer, what we ask them to do, as opposed to taking data driven decisions. At the same time, these architectures are very terrible at understanding and exploiting characteristics of and semantics of the application data. So in a sense that these architectures are component aware, that are taking component aware decisions as opposed to taking data aware decisions. So the goal of my research thrust and some of the works that I'm going to discuss over here, the goal of these works, the overarching goal is that to design and develop intelligent architectures that can learn from vast amount of system data as well as metadata to make autonomous data-driven decisions, as well as they can exploit application data characteristics as well as semantics to make data-aware decisions. And towards that, we have made some key contributions. I'm going to talk briefly about 3 works in today's discussion. Pythia, which is a reinforcement learning-based data prefetcher. Hermes, which is a perceptron-based object load predictor, and Constable, which is a safe dynamic load elimination technique. So if the time permits, I'm going to go in detail with all of these 3 works, and then I would be happy to take questions if you have any. Okay, so for some reason, the animation is broken, clearly. But let's start with Pythia, the first work. Okay, so Pythia is essentially, it's a data prefetching work. And as you know what a data prefetcher is, just a primer, the data prefetching is a speculative technique that predicts what memory addresses the program might be demanding next, and prefetching the data before the program demands, so that when the program demands it, you would already find this data into faster on-chip cache hierarchy, right? And then we started analyzing all prefetchers. We started asking this question, why these prefetchers do not perform well when they don't perform well. So it apparently stands out there are 3 key reasons why they don't perform well. First, they use one sort of program context information to learn what patterns that they are trying to find inside the program addresses. And if you use one context information for prediction, that significantly limits what you can predict. The second observation that we had is that these prefetchers often lack inherent system awareness. For example, what is the memory bandwidth usage? What is the energy consumed by the system? What is the cache pollution faced by the system? And the third observation that we also saw, that these prefetchers have significantly lack in silicon customizability. What do I mean by in silicon customizability? Means that, let's say, once you design a prefetcher, that design gets etched into the processor, and then you typically end up having the same algorithm getting repeatedly used without even having any benefit of customizing inside the silicon. So in this work, we try to address all of these 3 key problems, and then we came up with Pythia, which is a I'm going to discuss more about Pythia, which is a reinforcement learning-based hardware prefetching solution that can autonomously prefetch using multiple program context information as well as system-level feedback. I'm going to give example what these 2 feedback essentially means. And then most importantly, it can also be customized in silicon to use different program context information or prefetching objectives on the fly to make better prefetching decisions as we go. Okay, so before going into more into Pythia itself, so let me give you a brief rundown of what reinforcement learning itself is. So reinforcement learning, it's an algorithmic approach to learn to take the best action in a given situation to maximize a numerical reward. So every reinforcement learning system essentially comprised of 2 entities, the agent, and agent stays inside an environment. The agent senses the environment, which gets information as a part of state. Sensing that state, agent takes an action, and for every action, agent gets a reward from the environment that essentially justifies whether the action is good or not, right? Now, the agent internally stores, or one form of reinforcement learning, the agent internally stores something what we call a Q value for every state action pair. You can think of Q value as a numerical reward that gives you an expected return for taking an action in a given state. So basically, you can visualize in this way that the higher the Q value, the more reward that you can expect if you go for that action for that given state, right? And given a state, a greedy agent would select the action that provides the highest Q value, hence maximizing the long-term expected return as it goes, right? So as we found out that this visualization of reinforcement learning can be very much applicable for prefetching use case. So in this case, the prefetcher itself acts as a reinforcement learning agent, which is situated inside the processor and memory subsystem. So the prefetcher can actually sense as many information from the processor and memory subsystem. For example, features of memory request to the address A, let's say, what program counter information it's going, generating the memory address, what is the memory address location it's going to, many other information that we can figure out, which all of these would be used as a state information. Using the state information, the prefetcher is going to take some prefetching action, which can be as simple as that, I'm accessing, your program is accessing address A. From what offset from this address A, you are going to issue the prefetch request to. So that's the action, right? And for every action, the prefetcher would also receive a numerical reward that essentially justifies how good your action was. If you get a positive reward, then you know that, okay, that prefetch was, let's say, good. And if you get a negative reward or let's say something else, then you know how to tune itself to become good. So that's a whole overview of how we formulate Pythia as a reinforcement learning agent. Now let me give you a brief rundown of what individual these three pillars are. What is the state information? What is the action? What is the reward for Pythia? So as it stands, the state information can be any k-dimensional vector of features, and each individual feature is essentially encapsulating the program control flow information. For example, let's say what program counter, like what instruction, the load instruction, what is the PC of the load instruction, or maybe what is the branch PC of that you have encountered. Maybe the last three pieces that you have encountered. So essentially, you can construct some sort of information that gives you what path of execution the program is following, and then you are trying to make a prediction that what it's going to prefetch next, right? So that's the control flow examples. And then you can also think of some data flow examples. For example, let's say, what is the cache line address that you're prefetch that's triggering this prefetch instruction, that prefetch event? Or maybe what is the physical page address that this demand is going to, so that you are triggering a prefetch request. The delta between two cache line accesses, meaning it's not just the address itself, but let's say the sequence of address and what is the gap between these two successive accesses, right? And then you can think of many other chain information like last 4 deltas, last 8 deltas, or maybe any combination of these two, right? So that's what your feature is. So whatever that feature you can throw at it, it can learn from the substrate, the Pythia substrate can learn from it. Okay, so that's what the state is. What is the action? As I said, the action would be as simple as if your program is accessing a demand request to address A, then what would be the offset from that address that you are going to issue the prefetch to. So you would be issuing the prefetch to cache line A plus O. Okay, now if you can quickly calculate by yourself. If you have a machine that has 4 kilobyte of page, 64 byte of cache line, then you can come up with 127 actions in the range of -63 to +63. You can do the calculation. But note this, that zero offset is also a valid action for Pythia's case. So zero offset essentially means that Pythia actively tries not to prefetch anything. So that's and I'm going to show some examples. It's why that might be the case. Let's say if the bandwidth consumption is high, then Pythia can actively trade off prefetching something, not prefetching anything rather than prefetching something inaccurate. Right? So that's when it might become in handy. Yes. I
have a question.
Yes.
Can you clarify again? Maybe I think I have missed it. Regarding these upper and lower limits that to ensure prefetch do not cross physical page boundary.
Yeah. Okay. So that's a good question actually. So why do we want to stay inside the physical page boundary, right? So the two reasons, broad reasons why. So first reason is that if we are designing a prefetcher at not in the L1 cache level, but then L2 or LLC level, like anything that is beyond L1, then the designers typically tend to stay inside the physical address space to generate the prefetch request. Why? Because if you generate the prefetch address in the virtual address space, then you need to translate before you can access the main memory or any other cache levels, right? You need to translate the virtual address to the physical address, which the translation subsystem probably is accessed beside the L1 cache. So that's why the designer actively choose for going for physical address space prefetching rather than the virtual address space prefetching. So that's why we want to stay inside the physical page boundary. The other problem can arise that if we still go cross page in the physical address space, that's still possible, then it might introduce side channels for security violations, right? So you might be accessing a physical address that does not belong to your process, and then that might not be a direct security threat, but intelligent folks can use this as a side channel. So that's why we tend to limit the prefetching inside the physical page boundary. And if we are getting limited, then this is what the calculation looks like. That makes sense? Yeah. Okay, I mean that's a good question, but then this also gives me a segue to say that, okay, if you want to go for cross-page prefetching, and there are let's say prefetchers inside our community that goes cross-page prefetching also, then you essentially need to have a broader set of actions to Pythia. And broader set of actions also means not only just the storage overhead that you need, but also it means, let's say, more exploration that you need to do for the state action space, which might actually lengthen the training time, but something that we can easily accommodate also in the current infrastructure. Okay, then the last piece of the puzzle is the reward, which is the most critical piece of, let's say, reinforcement learning agent. So it essentially defines the objective for Pythia. And what do we mean by objective? It essentially encapsulates two key metrics. First, what is the, let's say, the usefulness of the prefetch request that you generated? Like, was it accurate? Was it not accurate? Was it timely? Was it going out of page? Like anything and everything that you can think of that justifies the usefulness of the prefetch can be used as a reward. And then the second thing that it encapsulates is a system level feedback. Like, for example, you are generating a prefetch request under what memory bandwidth usage situation? What is the cache pollution? What is the energy? So in theory, Pythia can be used for any system level feedback information into account. But then for the sake of today's presentation and the sake of the paper also, we considered the memory bandwidth usage as the prominent system level feedback information that we incorporated. But as I said, like, it can be extended to have some other feedback also in that same, let's say, reward structure. So how do we define the reward structure? So we have 7 distinct reward levels. So these are the reward levels. For example, let's say accurate and timely, then accurate but late, and then loss of coverage, and then you have some rewards for the inaccurate prefetch as well as the no prefetch. So each individual reward levels is essentially some numerical value that we set at design time, but then they are no way to be fixed also in the runtime. So you can actually configure these reward levels at runtime using simple configuration registers. And in the paper, we have demonstrated that if you set these values in a different level, you are actually sending different objectives to Pythia, and it would get automatically tuned based on that. So for example, let me give you one example. So let's say if I'm putting more reward for, let's say, inaccurate in the low bandwidth situation as compared to the high bandwidth situation. So what I'm telling Pythia is that if the bandwidth usage is high, then it's better to go conservative and not generate any inaccurate prefetch rather than generating something inaccurate. But then the other case that if the if bandwidth consumption is low, then you can probably trade off, inaccuracy for a bit of more coverage. So you can go greedy, right? So essentially, if you play around with these two levels, like what would you do when your bandwidth is low, and how would you trade off between accurate and the no prefetch, you can actually see two different design points for Pythia. Okay, so and in the paper we have lots of these analysis, which I'm not going to go into detail, but I hope you got the gist. Yes, Rakesh.
Thanks. So in Pythia, did you kind of observe that the RL agent's learning is more sensitive to the state features, or is it more sensitive to the reward?
Okay, yeah. So in our experience, it was more sensitive to the reward. So you can quickly give a different, let's say, objective to Pythia, and that impacts your performance even much more than what the features are, right? So that's our experience though. But if we design, let's say, Pythia-like system for some other use cases, that might not be the case. But regardless, reward is going to be one of the cornerstone how exactly we are tuning the agent. Yes.
Thanks.
Okay. Any other question? No. Okay. So then let's yes. Question.
Maybe it's on the technical side a bit, but like if a prefetch is useful, this you might learn down the line. You might not learn it immediately.
Mhm.
How do you make sure that this goes back into the reward function at some point?
Okay, so the question that you ask is the following, that whether the prefetch is useful or not, this information comes in a delayed fashion. So how exactly you accurately assign that the decisions that you have made in the past is actually correct, right? That's a good question. Yeah. So to address this issue, what we did is essentially we have something called an evaluation queue. So evaluation queue means that whatever prefetch decisions that Prithia is generating, we are actually putting into this queue. And so this is a simple FIFO queue, right? So you put something in the back and then it goes and retires from, where it gets popped out from the beginning, right? Or from the front. Now, what happens is that while the residency, during the residency of an entry inside this queue, we essentially keep on checking whether there is a demand request that's already arriving for this prefetch request. If that's the case, then we know that, okay, this is the prefetch request that sees a demand. So that means you know that this is an accurate prefetch, right? And then once it hits in that entry, you also know that, okay, under what feature you have actually made that decision. What was the action that you have taken? So that entry, think of it in this way that, okay, what state, what action generated this prefetch candidate? And now you're seeing that this prefetch candidate is getting used. So that means you know that, okay, this state and this action was correct. And you can also, like in the paper, we have mentioned that you can also have this evaluation queue even more intelligent, saying that, okay, I'm also populating when this prefetch line got filled into the cache and when the demand actually is arriving. So if the demand arrives after the prefetch fill, then you know that the prefetch is not only accurate, but also timely, right? Because it was fetched into the cache and then the demand arrived. But something other can also happen that, okay, you have the demand arrived, but then the prefetch is not filled. So that means you know that it's an accurate prefetch, but it's probably untimely. So you can put the reward accordingly, and the reward would be given to that state and that action itself. So that basically, let's say, puts the blame or the reward to that specific state action pair that we have taken. But at the same logic, that if you have not seen any demand arriving to that request before the request gets dropped from the queue, then we are considering that, this request is not used. So that means it's probably, inaccurate. So that's the logic that we have. Can we make it better? For sure, we can make it better. But eventually this evaluation, if it is mimicking what the prefetch would have seen inside the cache, then you are essentially doing or giving the correct feedback. Does it make sense? Yeah. So this is how we essentially handle the delayed reward thing. Yes. Any other questions? These are good questions. Okay. If not, let's quickly look into the evaluation. So this is, we kind of evaluated for multi-core systems, right? So on the x-axis, you have different number of cores. Y-axis, you have the geomin speed up. Higher is the better. And these are the performance number that we can get from multiple, let's say, prior prefetches in the architecture, in the literature. And this is what Prithia behaves, right? So as you can see that it enables a different parrot optimal front, right? So irrespective of whether you are seeing single core or multi-core, as big as 12 core, we are seeing a decent performance improvement across the board. So that's the first observation. Now, the second observation is that if you evaluate Prithia across multiple DRAM bandwidth configurations, so this is an only single core, but then we are scaling different memory bandwidth, right? So this is how the performance of prior works behaves. And then as you can see that the more you go on the left side of the x-axis, the less DRAM bandwidth that you're extracting. And as you can see that even prior works, they're producing much more performance when you have ample memory bandwidth. But then if you limit the memory bandwidth, then it starts underperforming. And even it underperforms, but then the baseline, where baseline is the red one bar, right? So you should not go below that. That's the whole point of having prefetching. I mean, at least you should not be harming performance. And this is, and all of these bandwidth configurations are not like taken out of the hat. These are like, per core main memory bandwidth found in actual commercial processes, right? So you can expect the processes to behave like this when you have full load, all the cores are busy on these processes, right? And this is what Pythia behaves. So as you can see, like again, it's kind of a different Pareto optimal front. If you have ample bandwidth, that also gives performance benefit, moderate, but it gives benefit. But then it shines when you go even more conservative systems, heavily bandwidth constrained, and then it performs much better than the prior works. Okay, so that's essentially the key takeaways that I want you to have. There are lots of many other implementation details, the overhead, how exactly we can make sure that these entire reinforcement learning based structures can work, and what sort of computational complexity or area overhead that we are looking at. And if you are interested, definitely check out the GitHub repository. Everything is open source, and you can just try it out by yourself. There is a chisel modeling also of this in prefetches, just to give you an understanding of how let's say area intensive or let's say circuit intensive this structure can be. And there are more talk lectures if you're interested. I'm just putting all the links over here. And yeah, so that's essentially what Pythia is from let's say prefetching side. But then that gives me some sort of a segue to go into applications of RL in multiple other systems, right? So you can think of reinforcement learning as a very primitive way of, or let's say very methodical way of learning dynamically to take actions in actual systems, right? So one example can be, let's say, intelligent data placement and prefetching when you have disaggregated memory, right? So nowadays we have let's say unified memory protocols, like memory access protocols like CXL. Right? So you have lots of memory nodes attached to the CXL protocol, and then lots of compute nodes also can access many of such memories, right? So in that cases, how exactly you would justify, let's say, incoming data, where exactly you want to place it? Do you want to place it in the local node? Do you want to place it in the remote node? Which remote node that you want to place it? When you want to prefetch it from the remote node to the local node before the access? Many use cases you can think of it in the reinforcement learning inside the system design, as well as you can think of adaptive routing in the interconnect, and not just thinking of reinforcement learning as a mechanism to deploy online, but you can also use reinforcement learning offline to deduce multiple stops for you. Like for example, automated design space exploration for high performance interconnect topology design. Right? So you can literally use this tool to automatically come up with the topology that reduces, let's say, a given matrix that you are throwing it off. So all of this you can think of as a way to formulate reinforcement learning, and it can be useful in those cases. Okay, so that kind of closes the Pythia part of the lecture. Do we have any other question? If not, then I would quickly go to the other part. Okay, so the question is, can we do better? Pythia is good. It does. At that time it was, there are prior works, there are after works that have also improved upon Pythia. But the question that we always keep on asking, well, can we do better, right? So that brings me to the animation is broken. That brings me to the second part of the lecture, which is Hermes. So in this work, what we actually saw is that it's good that you have a very decent hardware prefetcher deployed, and then that hardware prefetcher is saving lots of memory requests from going to the off-chip. That's what the hardware prefetcher should do. Makes sense. But then what we saw is that 50% of the off-chip requests that was going to the main memory would still go to the main memory even after you have very sophisticated prefetcher like Pythia. So what it essentially says that half of your memory requests are successfully prefetched, but then half are still there. So what to do with this half, right? So these halves are actually causing problem for the processor itself, right? Now, if you look into that half and break it down, what we saw is that 70% of that half, so it's like 70% of the 35, it's like 35%, right? So 35% of all these loads, they're actually causing instruction like blocking the instruction retirement of an out-of-order processor, which actually creates a problem. Right? So if they are blocking the instruction retirement, that means your performance is dropping, right? So what can we do for these candidates? So what we saw is that if you look into the load requests that are still going to off-chip, even after you have a sophisticated prefetcher, what we saw is that on-chip cache access latency is not something that you can neglect. Okay. In fact, 40% of the stalls caused by these off-chip loads can be eliminated if you can simply remove the on-chip cache access latency out of the critical path. So what am I showing over here? So the thing that I want to show you is the following. So in the traditional way, you would access L1 cache, L2 cache, LLC, and then you would go to main memory, right? Now, the thing is that if you can predict that this thing is going to miss the entirety of the cache hierarchy, you can technically access DRAM much earlier. And if you do this, what exactly you are doing? You are trying to parallelize this latency, and you're saying that, okay, I'm taking this on-chip cache access latency from the critical path. So that means your cache lookup can happen in parallel with the DRAM. And eventually, if you are correct, then you would already be seeing the request at the DRAM level, right? So you would return it much earlier. So that's what the whole observation that we had in the paper. Now, the thing is that the caches are getting bigger, and so you would expect this L1, L2, and LLC latency to be also going bigger across generations. So this is one figure that I have from 2007, which was showing the trend in bigger capacity on the left side and the bigger hit latency on the right side. And the same trend also stays in today's time. I mean, this is a fun fact that I keep on saying for whenever I present this work. So we actually started when using this golden cove as a configuration when we started evaluating this work. That was back in 2021. By the time I presented this work in Micro, that Raptor Cove came up from Intel's perspective, that already increased the L2 cache, and I'm plotting L2 cache over here. And then by now we have another generation which again increased the L2 cache size, and then every generation of L2 cache size increase, it's one cycle latency increase also. You might be thinking, okay, maybe one cycle is not that big of a difference, but that actually comes into the critical path, right? So any cycle savings is going to give you performance benefit. So all that I'm trying to make you understand is that this problem is going to get exacerbated in the future, right? So what can we do about it? The idea is that, okay, we can improve the performance if we just simply take out these on-chip cache access latency out of the critical path. So let them grow for the legitimate reason, but at the same time, you also predict and do some speculative access. So that's what Hermes says. It essentially predicts which load requests are going to go off chip. And for those predicted requests, it would start fetching the data directly from the main memory while also concurrently accessing the cache hierarchy. Okay, so that's what the key idea is. So let me just give you a pictorial overview, and I hope that this is going to solidify the idea in your mindset. So this is a traditional view of the cache hierarchy inside the core, and then this is what the access looks like, right? So the core generates a memory request from here. It looks into L1 data cache, that's the latency, L2 cache, that's the latency, that LLC, that's the latency, and then it eventually arrives at the memory controller. Memory controller sends it to the off-chip memory, off-chip DRAM, and then that's the memory access latency, right? At some point in this timeline, your latency tolerant limit of the ROB would be hit. So that means the rest of this time, the processor would be stalled, right? So you cannot actually process anything. You cannot commit any instructions from the reorder buffer, and that's the performance bottleneck. Now, what Hermes does, it essentially employs a perceptron-based load off-chip load predictor, which we named as Poppet, inside the core, okay? So what Poppet does is the following. So once the code generates a memory request, it simply consults Poppet that, okay, tell me whether it's likely to go off chip or not. If Poppet says that, it's probably going to go off chip. So then what happens? You simply wait for the translation to finish, because core is generating, remember this, core is generating address in the virtual address space, right? So you don't have a physical address yet to start accessing the DRAM. So you need that address translation. Address translation typically happens beside the L1 cache lookup. So you wait for that to happen. Once you know what's the address, the physical address is going to be for this memory request, you issue a direct memory request to the memory controller. And the memory controller is kept, starts getting the data from the DRAM. Now, if your prediction is correct, the request that's actually looking up the cache hierarchy would eventually look up all the caches and arrive at the memory controller. At this part, it's just simply going to wait. It says that, oh, you know what? A request for that address is already going on from the DRAM. So you just simply wait over here. Once we get back the data from the DRAM, which happens at this point, you would just simply return back the data to the core. So what you did, you essentially said, oh, you parallelize this main memory access time with the L1 and L2, with L2 and LLC lookup latency. And that essentially gives you the stall cycle saving, which gives you the performance benefit. Okay, hopefully this is clear. And if you have any question, then I can take it now. Okay, so if not, then, and then just to close this feedback loop, once the data goes back to the core, then you know that, okay, whether your prediction was correct or not. If the prediction is correct, you're going to train it one way or the other. That's the whole idea. Now you can quickly visualize that the entirety of the proposal relies on how accurately you can predict. Why? Because just to give you a perspective, finding which load requests are going to go to the off chip is like finding a needle in a haystack. So even when, let's say, decent estimates and on all the simulations that we did, you would see 5% of all the load requests that your processor is generating would eventually go to the main memory. So 5% means 1 in 20. Which one in that 20 you need to accurately identify, and then you can get any benefit from this. Otherwise, what would happen? So let's say this is not supposed to go to off chip, and then you actually made a prediction that to go off chip. What would happen? You are just simply accessing DRAM, right? You are accessing DRAM even though you should not have accessed. So that increases not only the wastage, the bandwidth, but also it increases the energy consumption because DRAM accesses are costly, right? So that's a problem. So you need to find that needle in the haystack very accurately to make this work. So for that, we have some sort of a, let's say, perceptron-based off-chip load predictor, and that ties up to this machine learning-driven architecture, like how exactly we can use it. So what we do, we have a multi-feature hash perceptron model in this case. So multi-feature hash perceptron, just let me very simplify it. So what we do, we have, let's say, every individual feature has its own feature weight table, okay? So how we make the prediction? So let me give you a rundown. So once a core generates a request here, right? So the memory request gets generated. You extract some features from this memory request. What are the features? So I'm giving you one example feature here, like PC plus the cache line offset that it's going to. You can think of many other features, and in the paper we have lots of other features, explained. So you extract these features, you hash down this feature value, and then use that hash value to look up the weight table. So the weight table is giving you some sort of a weight value. So weight values are 5-bit signed integers that can go from -16 to +15. Okay. So -16 means, you think of it in this way. -16 means it has a negative correlation to off chip. So that means you have, whenever you see this feature coming up again, you are very well sure that it's not going to go off chip. +15, on the other hand, means that you have a very positive correlation. That means whenever you have seen this feature, you very well know that it's going to go off chip. Okay, so these are like a biased correlation. But if you have feature weight values to be on the 0 side, so that means there is a good chance that it would, with that same feature, you have seen, let's say, 50% of them going off chip, 50% of them are not going off chip. So that's why you ended up in the middle. So any feature that is biased in the 0 zone, you know that they are not correlating. If the features or the average value of the features on the other extreme end, then you know that that feature actually conveys some meaning for this prediction. Okay. So in this case, let's say, you have some feature value. One feature is saying -4, another feature is saying 12, another feature is saying -5 as a weight. Okay. What you do, you just simply sum up all the weights. You get 3 as this case, and then you pass it through the activation function. Activation function is as simple as, let's say, whether, is it higher than some predefined threshold? If it is yes, then you predict that, okay, it's going to go off chip. Yes. How do you determine the threshold? Yeah, that's a good question. So in this case, what we have, the threshold is, we did study on the, let's say, test traces, right? We said that, okay, these are the test traces I'm going to see. And given what threshold value, how exactly their accuracy and the coverage is changing. And we have this analysis in the paper. So if you change the threshold value, you would see that at some point your accuracy would drop, but then your coverage would also increase. Like everything, you would keep on saying that, okay, it go off chip. So that means your coverage means whatever would actually go off chip, you predicted to go off chip, that's fine. But then you would also start predicting multiple other things that won't go off chip to be off chip, right? So there would be a sweet spot on where if you set this threshold value, that would give you the inflection point that, okay, you have good accuracy, you have good coverage also. But what you're alluding to, and if you're alluding to this thing that, okay, this is like a very like a strict thing. I mean, you did some analysis on some fixed set of traces, how exactly it's going to correlate for all unseen traces. You are absolutely correct in that sense. So we can actually, go for adaptive threshold value also. So there are, techniques in the, maybe we can figure out other techniques to change this threshold as we go along the, training, right? So, yeah, that's a good question. Yes.
I think you partly answered my question with the follow-up that you mentioned. But so in this work, you use this offline. You don't do online modification of these thresholds. Based
so
on
right now sorry, go ahead.
So based on the workload that you see, do you online modify the thresholds or no?
No. So right now, this threshold, the activation threshold, is something that we set it at the design time, and then it kept it fixed. So the weights, on the other hand, is dynamically learned, right? So they are changing, but then the threshold is something that we are not changing. It's set at design time.
Well, in that case, you don't need to modify the threshold for different workloads, right?
Because
the weights are trying to fit against the prediction that the perceptron is making.
That's you're saying that threshold would also likely change from workload to workload.
I'm saying that you don't need to, because the weights are being modified on runtime based on the workload's, let's say, access pattern.
Yes, the weights are changing. Yes.
Yeah, so then you don't need to modify the threshold, right? The threshold can be some arbitrary value. Or is there something that you explore, for example?
Yeah. So what we did is the following, right? So we set this threshold based on some test workloads that we have, and then these test workloads are not part of the full set of workloads that we are evaluating, just to be sure that, okay, we are not overtraining or overfitting for those workloads, right? But then I'm pretty sure the more workloads that you are going to see, the more you are going to see the changes in the threshold, right? So maybe the threshold would be going on the bit on the positive side, bit on the negative side. And that also does not, alleviate this fact that maybe for specific workloads, you can also tune the threshold in a specific way, right? So for that workload, if you set the threshold much negative, it would start quickly predicting that, okay, these are going off, these are not going off.
So the time to make the correct prediction can be better.
Exactly. So this threshold works well for the workloads that we have seen, but is this the best that you can do? Probably not. So you can extract more out of it.
Yeah. Then another question is, you likely train, I'm guessing that this is done for the region of interest of some specific workloads, right? The estimation of these thresholds and the weights, at least the ones that you start with.
Yes.
What happens when you go outside regions of interest, or when you're transitioning from workload 1 to workload 2? Because that really decides how quickly you transition and start making correct predictions when you transition to the second workload, right?
Yeah. So okay. So let me summarize this question. So the question actually is about how quickly you can learn from this, right? So there would be some sort of a, let's say, warm up. Initially, the perceptrons are probably going to make random decisions, right? And that's true. That's what would happen for sure. So initially, all the weights would be initialized to 0, and then you would start incrementing. And I'm here to show like how exactly you would change the weights, but then initially you would make wrong decisions, and then it would saturate at some point. When exactly it would saturate, or how long does it take to saturate? That's a question. I would say it's a bit hard to put it into a perspective. So what I can say is the following. So we have analyzed other prediction mechanisms to do this sort of prediction. Okay. So those competing prediction mechanisms are also evaluated in the same methodology, that you have this many warm-up instructions and this many simulation instructions. So those prediction algorithms are also warming up for that specific amount, right? So, and once the warm-up finished, and then we are simulating, we saw that this prediction is better, right? So one way to visualize this question can be that how small we can make this warm-up to still see a benefit coming from perceptron. So we have done this study in Pythia. Pythia is a reinforcement learning agent, and there is a legitimate concern that, okay, it may actually take time to spit out something meaningful, right, as an action. We have not done this study, I guess, over here, but we can do it. The infrastructure is open source. So you can literally reduce and keep reducing the warm-up phase as low as, let's say, 2 instructions warm-up. You cannot make it 0 because of the simulation would break down, but you can make it 1, let's say. So 1 meaning it's instantaneous, right? And then you keep on comparing against all prior walks and then say that, okay, if all of them are also instantaneously starting to make a prediction and Hermes is also starting instantaneously, what's the benefit, right? So hopefully that can actually give some sort of understanding that how quickly Hermes can saturate.
Sure. Yeah. Thanks.
Does that make sense?
Yeah, it does.
That's a good question. Yes. Okay. Any other question? If not, then I'll just quickly show this is the prediction part. Okay. Now comes the training part. What happens in the training? And just note this, that training is happening online. It's not that something that we train this network offline and then deploy it online. No. So this prediction is happening online, and then training would it's not back propagation, but the training would also happen online. So let me just give you one example, how the training happens. So let's take this example as a consideration, right? So you did this prediction, and then you predicted that it would go off chip. Now, eventually you realize that, okay, it's not going off chip because it was hitting on the cache. Then what do? You know that, okay, the activation shouldn't have happened. So that means your sum of the weights should be lower than the threshold, right? You got it higher than the threshold. That's why you predicted on the other direction, but it should be lower. So what you do, that means the cumulative weight should be lower than the threshold. That's what I said. So what you do in this case, can someone guess what you would do? Just random guess. In this case, what would happen? Exactly. So what you do, you just simply, reindex all these weight tables, saying that, oh, we use this feature for the prediction. You reindex all the weight table, you just simply decrement the weight. So decrementing the weight essentially means that, okay, I want to go in that direction. So you would change the weight to go into that direction. So in a stochastic gradient descent language, you would actually identify, okay, what is the error, and then you would propagate that errors, some gradient to those weights. In this case, we don't have any gradients or whatsoever. It's just a simple increment and decrement operation, just to keep the infrastructure or the logic easy. But you can make more complex, let's say, weight update algorithm also to make the changes. But I hope this is understandable. Okay, so with that, let's see some sort of evaluation. So this is what Hermes compares on top of Pythia as a prefetcher, right? So what you are seeing here is that Hermes as a speculative technique, it's not maybe as competitive as Pythia by itself, right? So, but the good part is that you are getting almost half of Pythia's performance benefit with only 1/5 of its area over it. So that means you are getting more bang for the buck with the the additional area that you are adding on top of the existing complex architecture. Okay, but then the good part is that if you have Pythia on top of Hermes on top of Pythia, that additionally brings performance benefit. Now, all of these nuances we need to put into a perspective, and I'm going to show you some experiments over here. So this is what the bandwidth graphs looks like. So and on the x-axis, again, you have different bandwidth, and on the more you go on the left side on the x-axis, you have less bandwidth, and the y-axis you have the speed up. Okay, so the higher is better. You should not go below 1. The more, as I said, the more traces that we would throw at Pythia, you would also see that there are negative outliers. But the more important part that I want to highlight over here, and that's something that you should also be looking at, that there is an inflection point over here. So what that inflection point means, it means that if you have ample bandwidth, aggressive speculation techniques like Pythia is really good, right? So it would extract high performance. That's what over here is. But then the more you make it conservative, right? So the more it becomes conservative, then let's say even a small speculative technique is also fine. Because that speculation, which is giving you benefit, would actually start killing you when you don't have the headroom to breathe. Now, if you have both of these, and this is what I mentioned, that in the bandwidth constraint environment, Hermes might actually be even, like by itself is even better than Pythia. Now, the obvious question is, if you add both of these together, what happens? Obviously, that changes the Pareto optimal front of the Pythia. That makes sense. But if you quickly see this, that is this following the best curve that your orange bar and the blue bar is? Probably not. So it's not actually following, let's say, the best of both worlds. So something that you can think of, let's say, multiple different types of speculations are going on. How exactly you are going to coordinate, that might also be a challenge. By itself, it can, but is this the best? You can think, be the judge of yourself. Okay? And we did lots of other studies. I'm not going to go too much into detail, overhead analysis, more performance numbers. You can just find it on the paper. And then, yeah, so this is what the summary is. As I said, like off-chip prediction is a different sort of speculation than just the load address prediction employed by prefetches. And we showed that it can either be applied by itself or it can be combined with prior techniques to provide additional performance benefit. And Hermes is the predictor that we designed. It has decently high accuracy, decently good coverage, as well as low storage overhead considerations, performance benefit on top of a aggressive baseline system, as well as high performance for bandwidth. And then, yeah. But then if you look into the accuracy and the coverage numbers, these are not something that you can think of not to be improved upon. Obviously, you can improve upon on the top of this. If you are interested, definitely check out the paper and then the artifact. You would have, all the workload traces, all sorts of prefetches that we implemented, all sorts of off-chip predictors that we implemented out of the box. And if you want to make, predictor by yourself, you can easily do it. So there are base classes, and then all you have to do is simply extend the class, implement your train function, predict function. You would be good to go, and you would see, matrix like this out of the box. Like how many of them are true positive, false negative? What would be the precision of it? What would be the recall of it? Obviously, this is one example. Not all of them are this good of a precision and this good of a recall, but if you can improve upon, that's something that you can take a look at. Okay, so yeah, so there are more lecture talks over there, and lots of other things that you can also think of in using off-chip prediction, like you can prioritize requests that are going to going through the memory hierarchy, like in the cache queues as well as on-chip network routing. All of this you can prioritize if you know that these are going to go off-chip. Better instruction scheduling, maybe other ideas on performance in fairness systems, and also. And then if you take a look at a broader view of the memory hierarchy, so it's not exactly inside the memory systems that we know of, but if you look into the broader view of the hierarchy, so like this is what the triangle is, right? So you would start with the register, then cache, main memory, let's say, disaggregated systems like CXN memory, network attached memory, SSD, hard disk, so many levels of memory hierarchy that you can think of. Now, if you start looking at the broader view, you can quickly start asking this question that, okay, where exactly your data resides? And can you predict it much beforehand? And if you can, technically you can actually reduce the latency if you can predict it accurately. Okay, so with that said, this is the end of second part of this. I probably have some more time to quickly go through the third part. If we have any question for the second part, I can take it now. Any question? Yes, Vlad.
Okay, so I had two questions.
Yeah.
The first one is for Pythia. I saw you model it in Chisel, right? Which is like a hardware description language. So does that mean that work is also synthesizable? Because I'm wondering how feasible it is to synthesize such RL-based models. I assume you just, I don't know what kind of hardware structures you add or how complex it is to add. I assume you do it in the paper, but it wasn't discussed in the presentation. So do you think it's feasible to synthesize it on real chips?
Mm-hmm. Yeah, so Pythia's feasibility of synthesizing in the real chip, is that the first question? Yeah, so I think we need to put it into a perspective, right? So Pythia by itself is not a small structure. So in the paper we have shown it's 25.5 kilobyte of storage, which is, let's say, almost on the size of L1 data cache, right? So it's not cheap. But then Pythia is also situated beside L2 cache, which is even bigger, right? So let's say 2 MB L2. So if you put it into this perspective, probably Pythia is, let's say, the storage over is not that big. And regarding the feasibility or the implementation, so when we did this Chisel implementation, we were more interested in two aspects. So first of all, whether it can be clocked into the expected frequency or not, that's one thing, because you put more complex logic, let's say floating point multiplications into the hardware that you need for let's say Pythia. But then if it takes a lot more cycles to make that prediction, then by the time it actually makes the prefetch prediction, your opportunity is over, let's say. So we were more interested in that aspect, one thing. And the second thing is we also have some sort of, let's say, area analysis coming from the design compiler, like how big of the area that you're looking at for Pythia. Our analysis showed that it's let's say doable, right? But then again, I would say take it with a pinch of salt, because this is like a very, let's say, high level modeling, not essentially integrated to the actual hardware, right? So if we want to integrate to the actual open source, let's say, processor, I truly believe that it would be, but we need to go more detail into that than what we have as a Chisel code right now.
Okay, so basically it's like model solitary, right? It's not already integrated with let's say with RISC-V or something.
Yes.
It's just, okay.
Yes.
Okay, this makes sense. And the other question was, so you showed Pythia plus Hermes, like the performance benefits they can give, but I assume when you compute the overhead, you only compute the overhead for Hermes. So I was wondering, how's the overhead when they are combined? Do they add up, or can you reuse some structures? I assume they add up, right?
I mean, right. Our evaluation, we have not done anything to, let's say, explicit coordination between these two, right? So it's just, in our evaluation, it's just simply having two techniques added on top of each other, right? So both of them are active at the same time, right? So in that sense, the overhead that I'm suggesting over here in Hermes is purely coming from Hermes. It's not coming from Pythia itself. But yeah, I mean, you can probably do other coordination, and then that coordination probably add additional overhead on top. But hopefully that overhead is also going to give you benefits, right, of equal proportion.
Thanks.
Does that make sense?
Yeah.
Okay. Anything else? Yes.
Are there any issues with coherence in this?
Are there issues in coherence in this? That's a good question. Yes. So the view that we had, let's say the evaluation that we did, is for a single socket system for where the coherence is managed in the LLC level, right? So in that case, it's fairly easy to implement. There is no coherency issues included, and then we have had this analysis in the paper also. So what do we mean by this? So you are not going to, even if your speculative request is fetching the data from the DRAM, it's not going to pull it into the cache hierarchy unless somebody is actually pulling it from the cache hierarchy. So the request would actually stay in the memory controller, and the demand request which is flowing from the cache hierarchy would need to arrive at the memory controller to get the data. Otherwise, the data is not going to feed back to the cache hierarchy. So, but the fact that your demand request arrived at the memory controller means that the coherence protocol ensured that the data is not present in any on-chip cache hierarchy. That includes not only the private cache, but also private cache of some other cores, as well as the shared cache, right? So in this simplistic view, or the, let's say, nominal view of the system of a single socket system where your coherence is managed at the LLC level, it's not like having Hermes in this aspect is not going to have any issues from coherency aspect. But how exactly it would work for multi-socket system where your, let's say, coherence is managed at the DRAM level, let's say, that's something that we can explore more in the future. And I'm pretty sure that there are options to be explored on this direction. Yes. Okay. Okay. So that brings me to the last part, but then I'm also out of time. So maybe I'll quickly go through a bit, and then we can go through more in detail probably later. Is it fine if I take, let's say, 10 minutes? Okay. Thanks, Lenny. Mohammad, is it fine if I do it? Okay. Okay. So now let's go to the third aspect of the work that we are talking about. Enough with the data-driven part. Let's go to the data-aware part. Okay. So data-aware part, we are going to discuss on Constable, which is a safe and dynamic load elimination technique. So let me give you some background. So load instructions, as we all know, that they are the key limiters of the instruction level parallelism because of two reasons: data dependence, meaning a load is stalling other data dependent instructions from executing, because unless you have the data, you cannot execute the dependence. And then there is a second form of dependence, which we call the resource dependence, meaning the load instruction stalling other load instructions for execution contention, resource contention. For example, let's say address generation unit or maybe load port, they are contending with each other. Okay. Now in the literature, we have lots of techniques that addresses load load data dependence, and then most prominent ones are value prediction as well as memory renaming, which essentially says that, oh, I'm going to mitigate that load data dependence by speculatively executing a load instruction so that you can break this dependency between the load instruction and its dependent ones, right? You can speculatively execute the dependent instructions even without executing the load, right? Even before executing the load. But then they do not mitigate the resource dependence. Why? Because these predicted load instructions, they still need to be executed to verify the speculation. Right? So that's the whole form of speculation, that you need to verify this. And just because they are getting executed for verification means that they are also taking resources which otherwise could have been used for some other instructions. Make sense? So now life would have been much easier or much better if we can safely break data dependency without even executing certain load instructions. And that's the whole hypothesis we started off with. And the question is that, okay, I mean, how can we even do this? Right? So you're breaking the data dependency using some sort of speculation, but then you're also not verifying what exactly is going on. So let's start with by identifying some load instructions that are, let's say, repeatedly generating the same things again and again. So that's what we are trying to target here. So load instructions that are repeatedly getting the same data value from the same load address throughout the workload. Okay. So in some essence, both the operations of these instructions, the address generation and the data fetch operations, both are producing identical results across all dynamic instances. So they are the prime candidate for breaking their data dependency without even executing them. Why? Because they're getting executed in the same way again and again. So we call these loads global stable, and then we started analyzing workloads to see what fraction of loads are actually like this. And we found out that a good fraction, like 34.2, meaning almost 1 in every 3 load instructions are global stable, meaning they're getting executed in the same way again and again throughout the workload. Then the question is, why do these loads are even there? You might be asking, oh, maybe you compile it with not with full optimizations. Compiler can actually get rid of many of these loads. That's not the case. We have done analysis in the paper, like why do these loads even exist in well-optimized workloads? And increasing architectural registers is also not going to solve this issue from the get-go. And as well as we have lots of deeper characterization study. I'm not going to go into detail, but there is a paper which you can go through. Okay, now I said like, okay, a significant fraction of the loads are global stable. Then the question is, do they limit ILP? Even when you have speculative techniques like value prediction, memory renaming, and all of these things. The question is yes. So the answer is yes. So let me just visualize here. So in this whole pie chart, I'm showing all the execution cycle where at least one load port is an execution resource, one load port is utilized in an aggressive out-of-order processor that already has memory renaming and value predictor implemented. So these are like very aggressive speculative processes, right? High performance processor. And all of these cycles is somewhere at least one load port is utilized. Now, if you break down this utilization cycles and then you try to understand, okay, who is utilizing that port? We saw that almost 1/4 of those cycles, it was a global stable load that took that port, while another non-global stable load is waiting for that same port. So think of it in this way, that you and your friend both wants to go to the same and stand in the same queue, but then you actually went to the queue and your friend is waiting for his turn to be there. Even though you have a ticket, probably, you don't have to go to the queue. Right? So this is what is happening. So somebody actually took the port, even though they are getting executed in the same way, while someone else who needs that port for this execution is simply waiting. Can we do something for this? The answer is yes. If you get rid of this global stable loads from taking that port, that means you can actually free that port for someone else to take. Right? So that's the advantage. What sort of performance benefit that you would get? If you ideally eliminate such loads, you would get 9.1% performance benefit. Just to put it into perspective, if you value predict that same amount of load, you would get 4.3%. And then these numbers might look very small, but consider this, that these numbers are coming from a very aggressive out of order processor. And then like the simulation is happening in a industry gate simulator. So these numbers are high. Okay. And then I'm going to put even in that aspect that, so what the first takeaway is that if you ideally eliminate both the data fetching as the data dependence as well as resource dependence of these loads, you would get double the performance headroom than just simply if you predict the value of this load. Okay, so that's the first takeaway. The second takeaway is that if you have like you might be asking, okay, maybe this 9.1 is not that big of a headroom. If you have double the load execution capability of that same processor, and double load execution capability comes at a very high cost of implementation. Like you need double the load execution ports, double the queues, everything. And that comes with area as well as power over it. That also gives you 8.8% performance headroom. So what essentially you're looking at, if you ideally eliminate all of the instructions that do not need those ports, that actually gives you almost the same benefit or even the higher benefit than double execution capability, right? So that's the benefit that we are looking at. Okay. Now, the thing is that these execution resources are not easy to scale. As I said, like this is what over a generation, like over 14 years of Intel processor microarchitecture. And then this is what the trend in the load execution port is. And this is what the trend in the other resources is. Like this is what reorder buffer size increase. This is what the total execution port also increase. So what you can clearly see that load execution resources are not scaling in the same way that other execution resources are going on, right? So why? Because they have inherent area limitations. They have power limitations, right? So the whole idea that we are trying to visualize here that, okay, since these resources are not that easy to scale, can we mimic that benefit by some other way? So that's the whole point of the goal of this paper, that, okay, let's improve the instruction level parallelism by not only mitigating the data dependence, but also the resource dependence. And that's what the constable is. It's essentially a purely microarchitectural technique that can do both by some microarchitectural understanding. So let me just give you the brief overview of the key insight, and then I'm going to skip through the implementation details. So this is what let's say the dynamic instruction stream is, right? And then the highlighted instructions are essentially the same instruction appearing 2 times, right? Let's say think of in like you have a loop and executing 2 instructions. Now, yeah, as I said, like the 2 successive dynamic instances of the same static load instruction, let's call them LD1 and LD2. Now, if the source register of this instruction is not modified between these 2 instances, then you know for sure that LD2 is going to see the same address as LD1, which means that the address generation of LD2 can be skipped. Similarly, if you can guarantee that no store or snoop, store meaning the store from the same core, snoop meaning store from some other core, has appeared to the address that is touched by this load instruction, the first one. If that's the case, then you know for sure that the LD2 is going to see the same data as LD1. So it means LD2's data fetching can also be eliminated. So if you can guarantee these 2 conditions, you know for sure that LD2 the execution of LD2, meaning the address generation and the data fetch, both of them can be skipped. And that's what essentially Constable does. These are the key steps. I'm not going to go into too much detail. So Constable essentially first dynamically identifies load instructions that have a history of fetching the same data from the same address. And once it identifies, then it starts monitoring its source address and the location, the address location. So it would say that, okay, as long as my source register is not getting touched by someone else, as well as long as my address is not getting stored upon or let's say snooped upon, then I can safely eliminate the execution of this load instruction. Okay, so that's the whole idea. There is more information in the paper. I'm not going to go much into detail. If you're interested, definitely go check out. And these are the methodology that we use for evaluating this work. It was evaluated with 90 workloads and then compared against multiple comparison points as well as configurations with SMT and without SMT. And you can easily understand that this sort of resource contention would be even higher in simultaneous multi-threading enabled systems, because then two threads are literally competing for the same resource inside the code, right? So that's we have also shown over there. So this is what the performance number looks like. So ETH is the state-of-the-art load value predictor, and Constable is what we are proposing. As we can see that Constable by itself is providing performance benefit on top of the value predictor. But if you add Constable on top of the value predictor, then that gives you additional performance benefit, right? This is the no SMT systems where let's say resources are congested, but not that heavily congested as SMT. Now, if you move into a SMT system, then you would start seeing the more benefit from elimination, right? So by itself, Constable actually performs much higher than, let's say, the value predictor. Like if you look into these Okay, so if you look into these numbers for the no SMT system, which was 5.1% and 4.7%, and if you go into the SMT, then you can see that value predictor probably stays almost on the same ballpark, but then Constable gives you more benefit. Because why? Because you are reducing congestion in a congested system, right? Now, if you add both of them together, that adds additional benefit. Okay, now, obviously, if you eliminate execution of instructions, then that would also give you resource efficiency. So in this case, we are showing the L1 data cache access reduction as well as reservation station allocation reduction. Both of these eventually transitions to a reduction in the dynamic power that I'm just quickly going through in this case. The key takeaway that I want you to have is that by eliminating instructions, you are not only improving performance and even in very heavily congested situations, but also you are getting power benefit because you are not executing instructions in those cases. Okay, and then there are lots of more details of the evaluation itself, like how heavy-handed solution it is in terms of the area overhead as well as the power overhead by this mechanism itself is causing. There are lots of other information in the paper, which I will be happy to point you to the paper. Okay, so I think I have question. Yes.
Yes, I have. So how fundamental is to have these loads that they are loading from the same address and with the same value? I mean, are they because of, I don't know, not well optimized code or at some point you cannot avoid it?
Yeah. So that's a good question. Maybe I can. Okay. Let me come out of this. Maybe I can quickly show one example, and that's actually a good example, thing to discuss. And I'm glad that this question came up. Okay, do we see it in the? Just give me 1 second. Zoom. Wait. Share desktop 2. Do we see it in the Zoom? It's fine. Yeah. Okay. So let me give you one quick example of how fundamental this thing, and it's actually valid to understand this part. Okay. Okay. Let me try once more. Share. Is it fine? Okay. So I'm just going to give one simple example to just motivate that this may be more fundamental than what we kind of believe it to be, right? So think of this as a code example, right? So this is coming from a spec workload called Leela, okay? And this is you can see like this is a random variable. It's a singleton random variable is RNG, and then you have a get RNG function. You all write code like this, right? So you have sRNG, you get RNG. If it's not initialized, then you are going to initialize. Otherwise, it's not. You just simply return back the same thing, right? So that's a global scope variable, and this is a function to access that variable. And then this is what the compile code looks like if you compile it with full optimization O3 using GCC, the latest version of GCC that we can get a hands on at that time. And I want you to focus on this like seemingly harmless if statement, right? So what this if statement does, it's essentially loads a value from the memory, and then it tests whether this value is 0 or not, right? Now the thing is that the way that we write the code, we are going to initialize it only once when the this entire simulator starts. Simulator means like this workload starts. Once you get the RNG variable fixed, that RNG variable gets fixed forever throughout the entire scope of the workload, right? Now, the very fact that we have this statement inside the code gives us this sort of load instructions. That load is, by virtue of our programming practice, it's a global stable load. We're not going to change this. Now the question is, can compiler change or optimize this code? Now think of it yourself. So what compiler needs to do to optimize this instruction? It needs a register, right? It needs a register to load this only once and keep it in that register forever, right? But then since this is a global scope variable, so that means if you're assigning a register there, either you are losing the register throughout the workload, or you need to be very much careful to save this register and then restore the register when you are going to use that value. So what compiler does instead, it simply has a like an IP relative or the PC relative load, and it just simply loads that value. And this sort of code is not actually present only in one workload. You would see like any sort of simulator workloads that you would see in the wild, like game simulators, processor simulators, you would have lots of variables like this. You have configuration variables, and every point of time, you're just checking the configuration variables. Oh, this is this. Internally, it's actually mapped to some global scope variable loads. Every time you are going to access that load, it's going to give you this sort of load instructions, and then the load instruction would stay stable. So these are fundamental in that sense. So the way that you can actually eliminate this sort of load is you would have technically multiple architectural registers that can afford to have these loads converted to a register reuse. But then would you go for those many registers? Probably that's not the case. So that's I mean, in the paper, we have multiple other examples also. I'm not going that much into detail, but then you can go through other examples and then, see, and then we made the case that, okay, why this is one example, and then these other examples also, why that's the case. And then it's going to stay over there. Okay, so hopefully that answers the question.
Yeah, sounds good. Thank you.
Yeah.
I think there is also a way to maybe change the paradigm.
Possibly, yes.
Yeah, to maybe avoid it to begin with, but
yes. So then there has been some works in the literature like how to fake registers, right? So those sort of techniques can be useful in this case. But this what we did in this study is just to show to the community that first of all, these sort of loads are abundantly there in even off-the-shelf binary, and you are executing these loads without even knowing. That's one thing. The second thing is that even if we increase the architectural registers, and then many people would actually immediately believe that, okay, maybe you are seeing this load because you are running on x86. x86 has 16 architectural registers. Maybe this thing is not going to be present in ARM sort of ISA, or maybe RISC-V sort of ISA, which already has multiple architectural registers. That's also not the case. We have done the study that if you increase the architectural ISA from 16 registers to 32 registers, recompile the binary with full optimization, you would still have this loads. And these loads, as the fraction goes of all the loads, they don't bulge. Like you would see reduction, but that reduction is not significant. So you would still have these sort of problems. And that's something that we probably need from a compiler perspective. We can also take a different dig. This is one different dig from microarchitectural perspective that we can do something.
Yeah, thank you. Thank you so much.
But this is a good question. Okay, so I'll just quickly finish and then I'll give it to Lenny. I'm taking too much of time. Wait a sec. So I was finished over here. So I'll just quickly summarize. Just give me 1 sec. Share desktop. I think the desktop 2 is not going to work. Is it working? Maybe it would go back again. Did it go? Oh, yes. No, it's blank. Yes. Okay, the system is no, the system is behaving predictively. At least we can predict, I guess. Okay, so this is what the key findings are. So we just made the case that okay, large fraction of dynamic loads are global stable. Essentially, it means that they are fetching the same data from the same address repeatedly. And we showed that these loads cause resource dependence, which is a fundamental different form of dependence than just a data dependence. And we also made a case that, okay, if you eliminate both these loads, like meaning mitigating both the data as well as resource dependence, you would have double the headroom than just simply eliminating the data dependence. Okay, and that's what Constable is. You have, we have decent performance benefit, improved resource efficiency, reduces dynamic power, as well as it also lowers the storage over it. And that's what Constable is. And unfortunately, we have not open sourced the implementation of this paper, but you can get something out of the paper by yourself. So there is a tool that we have open source. So this tool is called Load Inspector. You see Constable Inspector here. So what this tool does, it's you can literally use this tool to study global stable loads in your binaries that you are executing natively day by day in your daily life in x86 binary. Okay, so you can actually identify like how many of these global stable loads are there, what you can do, what sort of addressing that they are using, all sorts of information. And you can also study the effects that what we also did in this case, like how exactly if you increase the architectural register set, how exactly those loads changes at compile time itself. Okay, so yeah, with that said, that's what Constable is. And if I have any question from the audience, I can take it now, or I can just give it to Lenny.
Any burning questions?
Okay, thanks everyone for listening, and
Thanks
I'll
to
give it
you
to Lenny.
for
Yes,
excellent talk. Thank you.
thanks a lot.
Okay. For the next talk, we have Dr. Yu Liang, or we call her Lenny in our group. Lenny is a postdoc in the Safari Research Group at ETH Zurich, working under supervision of Professor Mutlu. Her broader research interests include the design and optimization of mobile operating systems and architectures, with a focus on enabling fast application launch and responsiveness, reducing energy consumption and extending device lifetime. So Lenny, thank you so much, and stage yours.
Thanks a lot, Mohammad. Is that available? On the Zoom? Oh, not share it. Okay, wait a minute.
You can see, but we cannot see.
Yeah. So maybe here. Okay. So let's maybe should have taken. Oh, maybe here. I don't want
I think we
this.
should share this.
Yes.
Just close this. Okay, and okay. Yeah. So on Zoom, things are okay. Okay, and you can see changes, and we can see here. So things are
Okay. Thank you so much.
okay.
Let me try it. Okay. Okay. We know that the previous talks today mainly focus on the PIM-based or the hardware-based solution to reduce the data movement and the power consumption. So now I will introduce a software-based solution to address these challenges. So my talk will only cover one paper, one HPC paper this year, Ariadne, hardness aware and size adaptive compressed swap technique for mobile devices. So before starting my talk, here's me. I'm a postdoc researcher in SaLWo group, and I will be a tenured research scientist in Whisper group at INRIA Paris. I am interested in hardware and software co-design, especially for mobile devices. So if you are interested in this direction, and if you want to be a PhD or master students, you can contact me. Now I will begin with some background information. As you may know, that available memory on mobile devices is usually scarce because both memory demands of individual mobile application and the number of concurrently running application increase. However, the DRAM capacity cannot be increased accordingly due to the constrained power budget for mobile devices. According to this survey in 2022, we can see that you can see the memory usage information from this figure, and it includes the free DRAM and the swap space used. The access is the smartphone status. It starts with reboot, and then we continue use multiple applications. So we observe that if we use 4 GB memory capacity, the free DRAM will be degraded quickly, and the system will start to use the swap space. Even we use 12 GB memory capacity, the same thing happens after we launching few applications. So we confirm that the available memory is usually insufficient on mobile devices to support multiple applications running concurrently. So what if the memory is insufficient? Actually, the system now, most of system usually swap the data from DRAM to the flash-based swap space. However, this swap out data could reduce the flash memory lifetime. And if the system want to read this data, they need to swap in them and thus prolong the read latency. So the modern mobile system usually adopt DRAM instead of swap scheme. With the DRAM scheme, the system compresses data and stores it in a specific area in DRAM, named as the pool. So if the system want to read this compressed data, they need to decompress them first. Since we don't need to swap out the data to the flash-based swap space, so this solution can increase the flash memory lifetime. And DRAM usually use LRU-based eviction policy and default compression algorithms LZO, but most of mobile system usually also support LZ4 compression algorithm. So now we know that the RAM increases flash memory lifetime and reduces read latency, since decompression latency is shorter than that data swap latency. Now we have this background knowledge, we'll move to the executive summary of this work. The problem is that we found that the RAM still prolongs application relaunch latency and wastes CPU usage because it does not differentiate data hardness levels and leverage different compression trunk size and data locality. So we really care about the application relaunch latency because this is quite important to the user experience. Imagine that you use the smartphone, you usually switch between different applications, right? So when you launch an application from the background, that means the relaunch. So relaunch latency is quite important, and the CPU usage also important for the user. The goal of this work is to design a new compressed swap scheme for mobile devices that can reduce application relaunch latency and CPU usage. To achieve this goal, we profile the mobile workloads and uncover 3 key insights. First, we show that the hard data is similar between 2 consecutive relaunches. Second, we found that a small size compression is fast, while large size compression provides a better compression ratio. And finally, we found there's a locality in data access during application relaunch. Based on these insights, we proposed Ariadne to leverage different compression trunk size based on the data hardness level, and also perform pre-decompression based on the data locality. And we evaluate our solution on a real smartphone, Google Pixel 7 with Android 14. The results show that compared to the RAM, Ariadne can reduce both application relaunch latency and the CPU usage of compression and decompression. So now I will move to the problem and motivation. As I mentioned before, the application relaunch latency is quite important. So we evaluated in 3 cases. First, non-swap. That means we disable the swap space so that the system reads all application data from the DRAM during a relaunch. The second case is the RAM. In this case, most application data is read from the pool after being decompressed. With swap, the system reads most of data from flash-based swap space. So based on these results, we found that the DRAM outperforms the traditional swap scheme, but still increase relaunch latency compared to non-swap. And another key metrics that impact the user experience is CPU usage. So we evaluated the CPU usage for memory reclaim in 3 cases when we use DRAM, this swap or non-swap. Since we evaluate this data based on a real smartphone, so we can only evaluate the CPU usage for a dedicated thread. So for the non-swap, we collect the CPU usage for writing file back the page to the flash memory. Because we disable the swap space for those anonymous pages, those program execution based data. So we only evaluate the file related pages. And for the DRAM, we also collect the CPU usage for the compressing data. And for swap, we evaluate the writing the swapped data to the flash memory. So for the swap case, we can see the CPU usage is quite small. This is because when we're writing back some pages, the CPU is usually yielded to the other processes. So based on these results, we can see that DRAM has significant CPU usage due to the compression and the decompression operations. So that's two key problems for this paper. Now we need to figure out what is the root reason for this problem, so that we profile the DRAM procedure, and we try to find what kind of data will be compressed first. So we examine the fraction of hot, warm, and cold data in each part of compressed data. And as you can see that we sort all compressed data in the order of compression and then divided into 10 equal parts as shown in x-axis. That means the data in part 0 is the first to be compressed, and that in part 9 is the last. So to minimize the compression operations, the code data should be compressed earlier, right? So the optimal case is that all blue for part 0 and 1. However, you can see there's still lots of hot and warm data in these two parts, right? So that means, and this change happened for all the evaluated application. So here's the takeaway that the RAM does not differentiate between the data hardness level, causing frequent compression and decompression. So our goal of this paper is to design a new compressed swap scheme for mobile devices that reduces application relaunch latency and CPU usage. Doing so requires reducing both frequency and latency of compression and decompression. We will move to our insights. To achieve our goal, we're trying to profile the mobile workloads, and we found some new insights. As I mentioned before, that we should keep the code data, we should separate the hard and code data, and first to compress those code data, right? So that we can reduce the compression and decompression frequency. However, the challenge is that how to identify this hard and cold data with low overhead. So to address this challenge, we examine the data reuse between two consecutive relaunches of each application. We check the hard data similarity which means the percentage of identical hard data between two consecutive relaunches. And we also check the reuse data, means the percentage of hard data from the first relaunch that is used in the later relaunch and the execution. Based on these results, we can see 70% data used in the first launch will be reused in the next relaunch. That means we can use the previous relaunch to predict the hard data for the next relaunch, right? And the fundamental reason behind this insight is that when we relaunch the same application, could trigger the same activities. So we got our insight one. The hard data that is used during application relaunch is usually similar between two consecutive relaunches. And based on this insight, we have a rough idea. We can identify the hard data based on only on the most recent relaunch to reduce the hardness identification overhead. So now, based on the first insight, we have the we can identify the hard and the cold data with a low overhead. Now, so that we can reduce the frequency of compression and decompression. Now we still need to reduce the compression decompression latency, right? According to recall our goal. So we examine the compression performance with different compression trunk size. We evaluate the compression latency, compression latency, decompression latency, and the compression ratio. And the x-axis represents the compression trunk size. We evaluate both LDO and LDO4 since they are both of them supported by the modern mobile devices. So our results show that large size compression provides a higher compression ratio. Actually, this is quite intuitive insight, but we can see another one. If we consider the compression latency, you can see here, we found that for those small size compression provides short compression and decompression latency. Actually, this is because the small size compression align with the data structure of the mobile workloads, because we also profile this on other workloads such as self-driving car workloads. We got totally different results. So now we got our insight two for the mobile workloads. The small size compression is much faster than large size, but has lower compression ratio. So we got this trade-off for our mobile workloads. We need to think about how to leverage this trade-off to get all the benefit and avoid the penalty, right? So now, do you still remember that we has already classified the hard data and the cold data in the previous insight, right? So there's a rough idea. We can use small size compression for the hard data for low latency, and use large size compression on the cold data for high compression ratio. because hard data usually used frequently, we can reduce the decompression latency, we can improve the performance, right? And the cold data is barely to be used again, so we can use it to save the memory usage. So until now, we can reduce the frequency of compression and decompression, and we can reduce both compression and decompression latency. However, we predict the hard data and cold data based on the previous relaunch. So we cannot 100% that we are correctly classify them, right? So there's still some chance that we need to decompress hard data. So we still need to improve the decompression latency further. So we profile the data locality in ZPU. We show the probability of accessing multiple consecutive pages in ZPU for each evaluated application. Based on these results, you can see the probability of accessing 2 consecutive pages together is quite high, right? So we got this insight 3. There's a data use locality in ZPU when decompressed data during application relaunch. So based on this insight, we can pre-decompress the next compressed data to hide the decompression latency during the application relaunch. So that's all 3 insights. Do you have any questions regarding the problem motivation or the insights? Okay, if no, I will move to our solution. So based on these 3 key insights, we propose Ariadne a hardness-aware and size-adaptive compressed swap scheme. The key idea is to reduce the frequency and the latency of compression and the decompression by leveraging different compression trunks based on the data hardness level and performing pre-decompression based on the data locality. So the Ariadne includes 3 key techniques. It quickly identifies the hardness of data based on the last relaunch. And it uses different compression trunk size based on the data hardness. That means it uses small compression for those hard and warm data, leading to faster decompression because of this data usually used frequently. And it uses large compression for cold data so that we can get higher compression ratio and save the memory capacity. Finally, it uses pre-decompression to further improve the read latency. Here's the overview of Ariadne. As you can see that we have 3 places to store the data, the DRAM, ZPU, and the flash-based swap space. When the data in the main memory, in DRAM, it will be reorganized according to the application and the data hardness. And when the main memory is insufficient, some code data, some background applications code data will be compressed first and stored in the ZPU with different compression chunk size. And when the Z pool is inefficient, the data will be swapped out to the flash-based swap space. For the common case, the data will be read in DRAM because we have done the data separation. We prioritize to keep hard data and warm data in the DRAM. In some rare case, they will be decompressed. They will be swapped in and decompressed from the flash space. So we still need a pre-decompression for that data so we can get better performance. So that's the overview of our solution. Do you have any question about this design or our previous insights? Okay, if no, I will move to evaluation part. So here's the evaluation methodology. We use a real smartphone, Google Pixel 7, with Android 14 to evaluate our solution. That we evaluate baseline, which is state-of-the-art, the RAM. It usually use LRU list data organization. That organization cannot classify or identify hard and cold data well. And it also adopts page size compression and no pre-decompression. This is because if you do not do the hard and cold data separation, you use a large compression, or if you use pre-decompression, you will introduce a huge overhead. So that's why the current system usually do not do that. And you can find our open source code on our GitHub. So now I will present two key results. One is application relaunch latency, another one is CPU usage, as both of them are quite important to the user experience. So we evaluate relaunch latency in 3 cases: the RAM non-swap and Ariadne with different configuration. There are so many configurations. I will not explain more details here because as you can see, all this configuration Ariadne can reduce the application relaunch latency compare with the state-of-the-art the RAM. Actually, this is because Ariadne maintain those hard data in the DRAM, and they also use maybe some data will be stored compressed in the pool, but they use small size decompression, so you can really fast to compress them, so you can get really good performance for the relaunch. I will also show the CPU usage. Now I will explain this configuration. Actually, all this highlight configuration for Ariadne has a common case. As a common case for Ariadne, that means the hard data is in the main memory. Actually, for those hidden configuration, we evaluate the extreme case. If you misclassify all this hard data, then you will get those performance. So in the common case, we can see Ariadne reduces CPU usage for compression and decompression over the state-of-art RAM. So there are still more in our paper. For example, the design details of Ariadne and Ariadne implementation, evaluation result, methodology details, and more evaluation results, including the compression, decompression latency, compression ratio, and hard data prediction accuracy and coverage. We also evaluate, we also have a sensitivity study with different parameters. You can check it in our paper. And we evaluated the overhead in terms of computation and the memory space. Both of them are quite small. And you can check our extended version on the archive. So now do you have any questions about the evaluation part? Maybe most students have the architecture background. Yeah. So now I will conclude the paper that Ariadne leverages different compression trunk size based on the hardness, the data hardness level, and performs pre-decompression based on the data locality. And our evaluation results on a real smartphone, Google Pixel 7 with Android 14, show that Ariadne reduces both application relaunch latency and CPU usage compared to the state-of-art DRAM. So that's all I have. I'd happy to take any questions. Yeah, please.
Thanks for the presentation, Lenny. My question was, let's say you have an application where each of the two consecutive application relaunches, they share, let's say, 70% hot data similarity.
Yes.
So I was wondering, what if you extended the history and, for instance, first relaunch to second relaunch, they share 70% data similarity, hot data similarity. First relaunch to third relaunch, now you have 49% hot data similarity, and so on. It reduces relative to first relaunch as you increase the number of relaunches. So I was wondering, what if you extended the scope from one relaunch to, let's say, 3 relaunches, you have less hot data similarity, and basically do your small chunk size compression and large chunk size compression according to that history length. Do you explore that?
Actually, there's one paper do the similar things. They profile 10 applications. They profile 10 consecutive application relaunch, and they can get more accuracy, but they have a huge overhead because you need to store lots of data. So we aim to achieve a lightweight methodology to predict our hard data. So that's why we choose this methodology. Yeah.
Okay, thanks.
Mm-hmm. Thanks. Yeah. Yes, yes, we need to modify the OS and we modify the memory management file, all these schemes. Yeah, we we usually do the experiments on the real smartphone, so we need to revise the OS and flash them into the real smartphone and evaluate it. Yeah.
Okay, thanks a lot, Lenny, for your excellent talk. And I think we have a coffee break until 4 p.m. and then we will be back. Thank you. Ivan. Hi, Ivan.
Hello, can you hear me?
Yes, we can hear you. Could you please share in the meantime?
Sure, I will prepare my slides. Give me a second.
Yeah.
Okay. Hopefully you can see the slides, right?
Yes, looks good.
Perfect.
Ivan, can you please also turn on your camera?
Oh, sure. I forgot to do so. Can you see me? I guess yes, right?
Yes.
Nice.
How are you doing?
Very good, very good. I'm excited to be here. What about you?
Okay. Okay, welcome back to the, I guess, the last session of the workshop. So for the first talk in the last session, we will have Ivan Fernandez. Ivan received his bachelor degrees in computer engineering and master degree in mechatronics engineering and his PhD degree from University of Malaga, Spain in 2017 and 2018 and 2023. During his PhD, he stayed for 10 months at Safari Research Group led by Professor Mutlu as an affiliated researcher and has co-authored top venue papers. In 2022, Ivan joined Barcelona Supercomputing Center, where he is involved in several international projects, such as the European Processor Initiative. His current research interests include processing memory, near data processing, RISC-V, and high-performance computing applied to time series analysis and bioinformatics applications. Ivan, thanks a lot for being here, and feel free to start whenever you're ready. Thank you.
Sounds good. So hello, everyone, and thank you, Mohammad, for the nice intro. And also thank you, Safari, for inviting me, because I think this is a very good opportunity to present NATSA and MATSA together. As you can imagine, they are very closely related projects. They just differ in a letter. So yes, this is a very good opportunity. And I will talk for a while about time series analysis and trying to perform this time series analysis closer to where the data is. So yes, I hope you get something interesting from here, and feel free to interrupt me whenever you want. So I had prepared a slide here about me, but well, Mohammad already introduced me, so I won't add much over here. Basically, these two works that I will present today, I was leading them while I was in Safari. So this is the only thing that I just wanted to mention here. Nice. So here you can see the outline of the presentation. I will start with some background, common background, let's say, to the two works I will present, and then some motivation. After that, I will present NATSA, which is about performing the time series analysis closer to the data with processing near memory. Then I will present MATSA, which is about performing time series analysis where the data is by using memory. And finally, I will close my presentation with some conclusions. Okay, so let's move to the background and motivation. And I would like to start with the first question, which is, what is a time series? So a time series is a collection of observations that are made sequentially in time. And in contrast to the numeric representation, time series enable visual inspections and intuitions. So for example, if I show you this set of numeric values, probably you don't understand anything from them, But if we represent this data, we can see how they belong to an electrocardiogram, and we can infer valuable information about the patient or something relevant that can be useful for further diagnosis. Now the question is, what is time series analysis? Time series analysis is basically a set of methods that that allows us to infer valuable information from the time series data. What time series analysis does is to usually slice this time series into subsequences, where the motif discovery focuses on the similar subsequences, and the discord discovery focuses on anomalous subsequences. Here you can see a real-world example of time series analysis following the electrocardiogram approach that I showed you in the previous slide. And basically, what we have here is an input time series, which is the actual electrocardiogram in red over here. And then below we have what is the output of our algorithm. And what basically tells us this output is that for those regions of the time series which are different, or yes, very different to the rest of the time series, we have high distance values for them and the surrounding area, which means that they are like anomalies. And for those that are very similar to the rest ones, like these parts over here, we get low values of distance, which means that there is nothing, let's say, out of the expected behavior over there. So the question now is, why this time series analysis matter if I didn't convince you so far? Well, because time series analysis has many applications, like climate change, medicine, economics, signal processing, even astronomy, and many more. Actually, there are other time series analysis applications that, for example, there are many types of data that are not true time series and can be fruitfully transformed into time series. Like, for example, DNA. Actually, there are many recent works that are exploring time series analysis for filtering DNA and these kind of things. Also, speech, textures, RC text, historical handwriting, and even things like you will never think about, like shapes. So as you can imagine, this fact greatly expands the applicability of the time series analysis. Nice. So far we have observed that time series analysis is widely applicable. So if we accelerate it, we can provide benefits in many fields. Based on that, the common goal of NATSA and MATSA is to characterize the state-of-the-art time series analysis algorithms in commodity architectures, and then, based on the bottlenecks that we find, propose software and hardware solutions to improve the performance and the energy efficiency of this time series analysis computation. Nice. So at this point, I will give you a very brief introduction to two time series analysis methods, because of course there are many other that I will not cover, but this is the ones that we are basing the works that I'm presenting today. First of all, let me introduce you the matrix profile. The matrix profile is a state-of-the-art set of algorithms and open source tools that are intended for both motif similarities and discord anomalies discovery. These tools are very easy to use because you only need to provide the subsequence length, and it doesn't matter the nature of the data. You don't need to tweak any other parameters. So from the user point of view, it's very simple. And here is a high-level representation on how this set of tools works. So let's spend a little bit of time on this and try to understand this. Basically, let's say we have an input time series like this one, and we want to understand whether there is any anomalous or very repetitive pattern within it. So what we will do is to slice it into different subsequences, as you can see here. And each subsequence has the index where it starts and M, which is the length of the window of this subsequence, which is usually the same for all the subsequences. Based on this, we build a matrix that looks like this. And each cell of this matrix represents the distance between two given subsequences of the time series. So we have all the subsequences over here and all the subsequences over here. So in the end, we are comparing every subsequence to the rest of possible subsequences of the time series. As you can imagine, these metrics can be huge for long time series. So what we actually do is to store the profile and the profile index. The profile contains for each row of these distance metrics, what is the minimum value that we found. This means that for every possible subsequence of the time series, we will know which one is the other subsequence that is closer in terms of similarity to the first one. We also store the index to know where this, let's call it, closest neighbor it is, and that's it. And we work with this structure, and we infer from here if we have very high values where that there is an anomaly or things like that. This is what I was showing you at the beginning as the output of the algorithm. Nice. So let me give you more concrete examples of how these motifs and this course thingy work. So here you can see a synthetic motif or similarity example where we have an input time series which has three very similar subsequences over here. And as you can imagine, for the parts that we have random values, the distance values are quite high. While for the surrounding area of the subsequences that are very similar to the other ones, the distance value decreases dramatically. And this is how we'll take those similarities. In contrast, we have the anomalies or the discovery, where we have here another input time series, which is quite regular overall, but it has a very different subsequence over here. Based on that, our algorithm will provide us low values for the areas that are very similar to the rest ones, and high values for the area that is very different to the rest one. The question now is, how do we calculate the distance? So there are two main approaches, or I will focus in two approaches for the matrix profile. The first one is the Euclidean distance, and the second one is the dynamic time warping. For the case of the Euclidean distance, what we are doing is to perform point-to-point comparison. So if we take the ith point of the first subsequence, we could compare it only to the ith point of the second subsequence. Because of that, subsequences need to be in sync, because if not, you will map points that belong to other areas, and it's very unlikely that you will get a meaningful result, or you will be able to detect any anomaly or things like that. The good thing is that this method has linear computational complexity, but yes, let's say the requirement is that they need to be in sync. On the other hand, we have the dynamic time warping, where what we do is point-to-point in plural comparison. This means that we take one point from one subsequence and compare to many points of the other one, trying to find which is the closest one. Because of that, this allows us to analyze subsequences that don't need to be, let's say, in sync. They don't need to be like so well mapped. But this comes at the cost of having quadratic computational complexity, if we don't apply, of course, any optimizations and these kind of things. Nice. So let's take a look about both methods. The first one, as I told you, was the Euclidean distance. And in this case, what we can do to calculate the similarity between two subsequences, we can use the set normalized Euclidean distance, which is defined with this formula. And in this formula, what we have is M, which is the length of the subsequences, then Q, which is the dot product between them. We have, again, M over here. And also we have the means and the standard deviations of those subsequences. The good thing is that those statistics, let's say, can be calculated in linear time. And in the end, in practice, they take negligible portion of the whole computation. On the other hand, we have the dynamic time warping. And in this case, what we want to find is what is the lowest cost warping between two time series subsequences. Because when we perform these point-to-point comparisons, we can take many different combinations of points, right? So in the end, what we want to understand is what is the lowest cost warping, and then decide if those sequences are similar enough to whatever we are evaluating. So in the end, what we do is to build a matrix which looks like this, and this is different from the matrix profile. This is another, let's say, that one is to handle the different distances, and this one is to find what is the lowest cost warping path. And this matrix is built using this recursive function that you can see over here that depends on 3 surrounding cells. And in the end, this is a dynamic programming algorithm that it should be very familiar to many of us because it is used in other domains with basically changing the cost function, right? And as I said, we want to minimize or find what is the minimum warping path over here. I like to show this 3D representation of this DTW matrix where we can see clearly or we can understand better how this is going on, what is going on here, because in the end, we can take whatever path over the matrix, but in the end, the one that we are interested in is the one which has the lowest cost. And as this is accumulating the cost over the path, the last cost that we get will tell us how similar are those subsequences in their best warping path. Just to finalize with the dynamic time warping, I will very quickly show you how is the algorithm. So there is a version of the dynamic time warping which is called the subsequent dynamic time warping. And in this version, it is possible to align subsequences of different lengths. So let's say that you have quite a long time series reference and you have small queries that you want to understand if they are part of node from that reference. So the kernel of this DTW without any, as I said before, without any heuristics and optimizations is very simple because basically what you need to do is to initialize the matrix with zeros and then initialize the first row. And then you iterate cell by cell, going through the rows and the columns, basically calculating the absolute difference between the query and the reference and taking into consideration the minimum of the surrounding cells. As I said before, what you return is the minimum of the last row of the warping matrix, and this will give you the distance, and you will understand how similar are the subsequences that you are analyzing. Good. So to finalize with this part, I would like to share with you a couple of takeaways. So the Euclidean distance is able to handle long sequence pairs because of its complexity, like millions of elements, at the cost of being based in complex arithmetic, because you will probably need to deal with floating point for sure, and it is restricted to in-sync data. On the other hand, we have the dynamic time warping, which is restricted for short sequence pairs because of its quadratic computational complexity, like several thousands of elements, but it is based on a simple algorithm. It doesn't involve like the square root and these kind of things, and it is able to handle non-sync data. Nice. So now that we have a little bit of background on time series analysis, I would like to share with you what is the motivation to the works I will present later. And here we will talk about improving the performance and finding the time series analysis bottlenecks. So when I started my thesis, the matrix profile was starting to be the state-of-the-art algorithm, and the matrix profile team was basically focusing on improving the algorithm from the algorithm point of view, not caring about the performance so much. And by that time, we had in our department, we had an intersection 5. This was in 2019. This was, of course, it was deprecated sometime later. And we thought that this was a very good, let's say, platform to perform the characterization, because apart from having a decent amount of cores by that time, it also combines the DDR4 memory with what they call the MCD-RAM, which is basically some type of HBM memory in the same architecture. So we wanted to play with these two memory technologies and understand what were the trade-offs there. So first of all, what we did was to exploit the parallelism, and there is nothing fancy here. I just wanted to make you understand that these algorithms are highly parallelizable because they don't have dependencies between the comparison that you are performing. So we basically implemented a privatization-based parallel version of Scrimp, which was the matrix profile implementation by that time. And yes, there is nothing fancy here, just to understand that there are no dependencies. We also, of course, try to optimize it as much as possible and well, added some techniques to make able to exploit the AVX 512 instructions that the SEM file has. So what we did, what we also did was to exploit the two memory technologies. So what we did was as follows. Remember that this was the matrix profile, and one thing that you have to keep in mind is that we usually compute the matrix profile in a diagonal manner, because in this way we are able to perform dot product utilization. So if we only move one step both subsequences, we can reuse the dot product from the previous distance and just add in a couple of multiplications. And this is a way of reducing dramatically the computation that is required. Apart from that, what we did was to distribute the data. So the less used data, which surprisingly is the input time series because it is read just once, is in the DDR4, and the final vectors also, while we put in the HBM what are the most used data structure, basically the thread private variables and the privatized vectors of the matrix profile. So with all of this, we got the results. And what I want you to see here is that when we use the DDR4 only, which are these two bars, the performance saturates after a certain amount of threads. And actually, we can know further than that this. But if we exploit also the HBM memory, we can also further improve performance up to 5 times. We also took a look to the memory bandwidth utilization, and we noticed that for most of the time, the DDR memory was being saturated. And when using HBM, we were able to reach a higher memory bandwidth utilization. So in the end, in a DDR4 platform, the matrix profile was completely bottlenecked. So I just want to share a couple of takeaways here. So the screen algorithm, which is intended to compute the matrix profile, had several parallelization opportunities that could be exploited in this kind of architectures, but it is memory bound in commodity platforms that are based on DDR4. I just want to remind you that by that time, the HBM memory was not so common. And yes, this was a proof that let's say the commodity DDR4 memories were not able to provide the bandwidth that is required for this kind of algorithms. So with this motivation, I will move to NATSA, and unless there is any question so far, I will get some water meanwhile. But if not, I will move to NATSA. So here you can see the paper. The paper was accepted at ICCD 2020. And yes, you can find it. And if you are curious about anything, just take a look. You will find more information there. So I will try to give you here an overview of what we did in this work. Okay, so here is the executive summary. The problem is that time series analysis is bottlenecked by data movement in conventional hardware platforms. So the goal of NATSA is to enable high performance and energy efficient time series analysis for a wide range of applications. And to do so, we contribute with the first near data processing accelerator for time series analysis, which is based on Euclidean distance and the matrix profiling algorithm. So overall, NATSA evaluations shows us that it provides up to more than 14 times higher performance and consumes up to more than 27 times less energy than a DDR4 platform with 8 out of order cores. And it also outperforms a general purpose HBM processing near memory platform that has 64 in order cores by more than 6 times, while consuming more than 10 times less energy. Okay, so let's go to the motivation. The motivation essentially is what I already told you. So by the time of this work, Screen was the state-of-the-art CPU matrix profile. And when we characterize it in the SEM5, we notice that the performance increases dramatically with the HBM, and it is bottleneck when we're using the DDR4. We also built the roofline model to understand what is the arithmetic intensity of these algorithms, and we found that it is very low. And actually, it was hitting the memory roof in this platform, even with the HBM bandwidth. And it was very, very far from the theoretical computing peak that it could provide. So overall, Scrimp is heavily bottlenecked by data movement. Based on that, NATSA's goal is to enable high performance and energy efficient time series analysis for a wide range of applications by actually minimizing the overheads of this data movement. And to this end, we propose NATSA, which is the first near data processing accelerator for time series analysis that exploits the 3D stack HBM memories and also specialized processing logic. Now, let me give you an overview of NATSA. NATSA is designed to fully exploit the memory bandwidth of an HBM cube and to employ the required amount of computing resources to provide a balanced solution. To do so, NATSA consists of multiple processing units, or PUs, and each PU includes energy-efficient floating point units and bitwise operators. Those PUs are designed to compute batches of diagonals of the distance metrics following a vectorized approach. So here you can see how NATSA is intended to be integrated in a system. We have an HBM memory cube over here, and NATSA, with its different PUs, is connected directly to it with a silicon interposer. So internally, NATSA PUs consist of 4 hardware components. We have a dot product unit that is in charge of computing the dot product of the first element of the diagonal that we are computing. We have a distance compute unit that essentially implements the Euclidean formula that we saw in the background. Then we have a dot product update unit because, as I told you, and if you compute the matrix profiling diagonals, you are able to reuse the dot product of the previous iteration by just adding a couple of multiplications, and we use a unit specialized for that. And then we have the profile update unit that, based on the distance that we have calculated, will decide whether if it makes sense to update the profile and the profile index accordingly. Finally, we have a small scratchpad memory per PU because we store there some of the statistics and constants that are required for the computation. Now, let me give you through the execution flow of an NATSA PU from a very high level perspective. So recap, Scrimp is calculating a diagonal scheme, so we can enable the dot product reutilization, as I told you, and as subsequently overlap, we save a lot of computation. So based on that, the execution flow through the hardware components goes through the following steps. We first perform the dot product computation of the first element of the diagonal in the dot product unit. Then we perform the Euclidean distance computation of the first element of the diagonal in the distance calculate unit. Then we perform the first profile update in the profile update unit. And we prepare the dot product for the next iteration of the diagonal in the dot product update unit. Then the second and successive Euclidean distance computation happen again in the distance computation unit, and accordingly the profile update unit will update them if required. So this process keeps until the end, and as you can see, the units are replicated. So in a way, we are like trying to implement a vectorized approach and having several diagonals at the same time. Something that is required to take into consideration is the workload scheduling scheme, because as you can imagine, as we are working with diagonals, they have different lengths, and we can end with PUs that are idle most of the time. So to ensure this load balancing among PUs, we use quite simple static partition scheduling, but yeah, it is necessary. So what we do is to assign pairs of diagonals to the PUs. In a way, the sum of the number of the cells that they need to compute is equal. So this is very easy to understand with this figure. We have two PUs, PU0 and PU1. So if we want them to compute the same number of cells, what we do is to assign to PU0 the first and the last diagonal, and to PU1 the second and the last one less to the last diagonal to the PU1 also. If you make the math, you will see how they compute the same amount of diagonals And in the end, they are the views are balanced, and they are working all the time. Nice. So talking about NATSA's programming interface. So first, the user is responsible for allocating the time series and also providing the subsequence length, which is the only parameter that it has to provide. And NATSA will provide the user the compute profile and profiling the vector as a result. So here you can see how NATSA API looks like, which is rather simple. It's just a function where we pass the parameters, and NATSA internally will pre-calculate the means and the standard deviations, allocate the private profiles. Then it will calculate the static diagonal scheduling. It will invoke the accelerator, and finally will perform a reduction to get or to provide the user the final profile and profile indexes. With this in mind, let's move to the evaluation, and I will talk a little bit about the hardware platforms that we consider. So we define several representative simulated hardware platforms for the evaluation that you can see in this table. So we have four general purpose platforms that are based on DDR4 and HBM, and also taking into consideration out of order cores and in order cores, just to also in the HBM part, like to mimic if we are having a processing near memory, a general purpose processing near memory with less powerful cores over here. And then we have NATSA that consists of 48 PUs. Well, this number is coming, of course, from a design space exploration that we did that I'm running at 1 GHz, and it has its own HBM memory cube. We also compare NATSA against real hardware from that time, of course. That was the 75 KNL, an NVIDIA Tesla K40C, and also an NVIDIA GTX 1050. In terms of simulation environments, so we used an in-house integration of setting and emulator, basically the move, to simulate the general purpose hardware platforms. Then we use MacPad to obtain the area and the power for the general purpose hardware platforms. And we use the integration of Aladdin and Gen 5 to obtain the performance, the power, and the area of NATSA. Finally, to calculate the memory side power consumption, we use the Micron power calculator. Nice. So moving to the results, we first compare the performance of NATSA with respect to the general purpose hardware platforms. And as you can see here, for different time series, which are random, they are synthetic, but as I told you at the beginning of the background, basically the nature of the time series doesn't affect the results because the only parameter that you have is the subsequence length. So what we see here is that the bigger is the time series, the higher the benefits, because caches help a bit on the general purpose platforms. And overall, NATSA outperforms the baseline by up to more than 14 times. And yes, this is the conclusion from there. So in terms of power consumption, I'm talking about instantaneous power consumption here. We compare it to the simulated and the real hardware platforms. And as you can see here, NATSA in the right is the one that requires the least amount of power instantaneously of VATs if we compare it to all the platforms that we consider. One observation here is apart from NATSA has the lowest power consumption, most of the power consumption is consumed by memory compared to the power consumption that is taken from the processing units, which is in yellow. Okay, so now what we did was to compare NATSA in terms of energy consumption, but in this case, taking into account the execution time. So this is like the power delay and things like that. So, and we compare it with respect to the simulated and real hardware platforms. And as you can see here, NATSA again is the one that requires the least amount of energy for a given execution, and all of them are executing the same time series with the same parameter. And it is still the one that requires the least amount of energy. Concretely, NATSA reduces the energy consumption by up to more than 27 times over the DDR4 out of order platform, by up to more than 10 times over the HBM in order, and by up to 1.7 over an NVIDIA Tesla K40C. Finally, we compare the area of NATSA with respect to the simulated and real hardware platforms. And as you can see in this figure, which is actually, it is made up to scale. So, I mean, the proportions are kept. NATSA is the one that requires the least amount of area. And something that we need to take into consideration is that NATSA, the area of NATSA was calculated using 45 nanometer technology node, which was let's say, the biggest one of the platforms that we're analyzing. And even with this, let's say, pessimistic technology node, requires the least amount of area. Once that we reach this point, I will share with you a couple of takeaways. So in this work, we introduced NATSA, the first near data processing accelerator for time series analysis. NATSA exploits the memory bandwidth of HBM, improves energy efficient and execution time by using a specialized low power arithmetic, which is placed close to the HBM memory, and also it provides an efficient workload scheduling scheme. But there is a key takeaway. Well, there are a couple of ones. This is the first one. The area required by the floating point operators is high. And also, most of the energy consumption still comes from the memory device, in this case, from the HBM cube. So with this in mind, we will move to the second work, which is MATSA. And if you have any questions at this point, meanwhile, I will take some water. Otherwise, we will continue. Okay. So here is the paper. MATSA was accepted at IEEE Access last year. This is a journal for those that don't know that. And it is completely open access, so you can take the paper very easily in case you are curious or want to know more info or something that I don't cover here. So let's go with the executive summary. The problem is that time series analysis is memory bound, as we know, in commodity platforms, but also processing near memory is limited by the size of the floating point arithmetic operator. And this size, in the end, in practice, limits the compute parallelism that we can exploit. So the goal of MATSA is to enable high performance and energy efficient time series analysis for a wide range of applications, in this case, using the dynamic time warping. As contribution, we propose MATSA, which is the first magnetoresistive based accelerator for time series analysis. MATSA leverages processing using memory with the aim to exploit the parallelism in the workload and also to minimize the data movement overheads. MATSA evaluations shows us that it significantly improves performance by up to more than 7 times, and also energy efficiency by up to more than 4 times over server class CPU, GPU, and also processing near memory platforms. Okay, so in terms of motivation, the motivation is common so far, the bottlenecks of SDTW. So as I told you in the background, the subsequent dynamic time warping is one of the most actually accurate distance calculation method for out of sync subsequences. So what we did was to characterize this SDTW using a many-core CPU, a GPU, an FPGA, and also a processing near memory platform, in this case, a general purpose one, which was UPMEM. Here you can see the roofline models for the CPU and the GPU. So for the case of the CPU, we are clearly on the roof of the memory, and also the arithmetic intensity. Well, arithmetic intensity is more or less the same always, but in this case, it is also quite low, and it falls into the memory bound side of the roofline. For the GPU, we also get low performance because of that, and also other reasons that are not related with memory, but still the performance is quite low. Then for the FPGA, we are also falling into the membound side, and for UPMEM, it is the opposite, because in the case of the processing near memory platform, what is limiting us is the compute power that it has as it is reaching the compute roof of this platform. Based on that, we conclude that SDTW is heavily bottlenecked by data movement in commodity platforms. And also, if we move to already available processing memory platforms that are general purpose, it doesn't scale very well because of the limited compute power that they have for this type of operations. With this in mind, the goal of MATSA is to enable high performance and energy efficient time series analysis for a wide range of applications, by minimizing the overheads of data movement and improving the compute power. To this end, we propose Matcha, which is the first NRAM-based accelerator for time series analysis that exploits non-volatile memories and processing using memory. So as I told you, Matcha is based on processing using memory. And what processing using memory does is to perform the operations in memory by using the memory cells and eventually also the sense amplifiers. So the main components of the processing using memory are the crossbar, which is composed, of course, of the memory cells and their word lines and bit lines. The actual memory cell, which in this case we choose the magnetoresistive technology because its properties in terms of endurance and also in terms of latency. And we also have the reconfigurable sense amplifier that can be optional, but in this case we need it because we are doing some, let's say, more complex operations that require some assistance from these sense amplifiers. Here you can see an example of how a simple operation can be done in these types of memory. Probably I'm not the biggest expert on this, but well, I will try to show you a very simple example of how this works. So let's say we want to perform an OR operation in situ in the memory. So for that, we have several inputs, of course, and we have an output which will be the result of this operation. As you may know, the truth table of the NOR operation says that it is one only and only if all the inputs are 0. And in other cases, if any of the inputs is 1, the truth table, the output value will be logical 0. How can we do this in memory? So what we do is to first initialize the output cell to logical 1. This means to put a low resistance state. And then what we do is to apply the erase voltage to the input cells, like you can see over here. And there are two possible scenarios. It can happen that if all the inputs are 0, the voltage that we are applying here won't have any effect on the output cell. So it won't switch from the state that we initialize it, and it will remain in a low resistance state, which means it is a logical 1. In contrast, if any of the inputs has a logical 1, so its resistance is low, the voltage that we apply over here will be able to pass, and it will make our output cell to switch to logical 0 or what is called a high resistance state. And as you can see here, we are implementing the truth table operation. With all inputs are 0, it won't change, it will remain 1, and otherwise it will move to 0. Now, let me give you an overview of Matcha. So Matcha is designed to perform the computation where the data resides, in this case, in the memory arrays, and to employ the required amount of computing resources to provide a balanced solution. To do so, Matcha consists of multiple compute-enabled crossbars, and each compute-enabled crossbar includes reconfigurable sense amplifiers that are able to perform the bitwise operations. Overall, these compute-enabled crossbars calculate the SDW distances following a pipeline and away from a computation scheme. Nice. So this figure shows you a high-level overview of Matcha's architecture, where we have the different memory banks, the different memory mats, the compute subarrays, and here we have the different subarrays that Matcha is compute about. Each compute subarray has several reconfigurable sense amplifiers that will assist the computation, as I told you before. So yes, this is a high-level data mapping, and what we have here and what we need to place in these memory cells is basically the reference elements over here. This is the long time series that we will compare to. And then we have the query elements that will be over here, and those are short pieces of time series that we will compare to actually this reference. Then we have the correctness vector. The correctness vector is one of the rows, or better to say, the current row of the DTW metrics that we are computing at a given moment. Then we have 3 temporal S vectors that contain the cells that we require to compute the distance at a given moment, and some auxiliary cells over here that will be required to perform some minimum calculations and so on, and we will use it for those purposes. So here you can see a closer view of the reconfigurable sense amplifiers of Matcha. In this case, they are designed with the goal to perform different operations, like the row copies and what we call the diagonal row copies, which allow to shift also the values, and this is required to move the data around the crossbar. Then it is able to perform also addition and subtraction calculations, and to do so there is also, well, we need a register to have the carry and so on. It is also, it can also perform the absolute calculations and the minimum calculations. So these are the operations that basically are required to perform the kernel that I showed you regarding the dynamic time warping. So now let me guide you through the execution flow of Matcha. So in this case, we follow a diagonal wavefront across the warping matrix because there are inter-cell dependencies in the DTW algorithm, because when we calculate one cell, we require 3 surrounding cells to be already calculated, and the usual way of tackling this is by computing a wavefront scheme, which is like this. So we assign to the processing elements the values to compute in an anti-diagonal manner. And apart from that, what we do is to pipeline queries. So while we are comparing one query, we start computing the next one. So all the processing elements that we have are doing some useful work at a given moment. In terms of what are the steps that we need to follow during this wavefront computation, we first need to calculate the distance between the query and the reference, which produces a partial result 1. Then we perform a minimum calculation of that involves the surrounding cells of the matrix, and this produces this one. And after this, what we do is to perform the addition of this minimum that we have obtained and the partial result from the first step. Once that we reach this point, we already have the distance. So what we need to do now is to prepare the crossbar for the next operation. So we need to perform a diagonal row copy to the S vector. We need to do another diagonal row copy of one of the auxiliary vectors. We need to do a row copy of the third auxiliary vectors. Then we need to do a diagonal row copy of the query to shift it by 1 position and increment the indices. Once we have done this, we go to step 1 and we continue until we process all the queries that a crossbar has assigned. Okay, at this point, let me move to the evaluation and talk about the hardware platforms. So for this work, we define several representative hardware platforms, which are a CPU ARM general purpose architecture with a small CPU. We have a CPU i7, which tries to mimic a desktop PC based on an Intel i7. We have a CPU Xeon, which tries to mimic an HPC server with Xeon Gold CPUs. We have a GPU, which is an NVIDIA Tesla V100. We have an FPGA, which is an Alveo U50. We have a MEM as a general purpose processing linear memory platform. And then we define 3 versions of Matcha. We define Matcha Embedded, which has 128 compute-enabled crossbar, and this is a very small version of Matcha that, as its name suggests, is intended to be in embedded device, working in embedded devices. Then we have Matcha Portable, which has 1024 compute-enabled crossbars. This one is slightly bigger, and it's intended to be like, if you remember the Intel Neural Compute Stick, this is something that you can plug into your laptop as a very small accelerator. And then we have Matcha HPC, which is intended to work in HPC environments and has a higher number of compute-enabled crossbars. In terms of execution environments, We gather results from the real machines for the Intel CPUs, for the GPU, the FPGA, and AVMEM, as we have them available. Then we use our in-house integration setting emulator, the move again, to simulate the ARM CPU hardware platform. And we use MapPad to obtain the area and power for the CPU simulated hardware platform. Then, and due to the lack of a cycle-accurate simulator for the NRAM-based accelerator, we implemented an in-house simulator for the NRAM-based processing using memory, and particularly DTW, based on the available timing parameters of the NRAM cells that we already knew from more electronics-specific work, let's say. Okay, so moving to the evaluation. First, I will show you some numbers about Matcha, Embedded, and Portable, and we compare them to their corresponding baseline platforms. So as you can see here, we have the CPU ARM, the CPU i7, and the FPGA, and we have Matcha Embedded and Matcha Portable in green. So you can see the execution time, also note that this is logarithmic scale. The execution time is for Matcha is the lowest for those for all the input data sets that we evaluated, that in this case are coming from real data. And also for the energy, it happens also the same. But well, something that you will notice is that the energy reduction for both versions is very similar, and this is explained because in the end, the difference between the two versions of Matcha is that we are increasing the number of compute-enabled crossbars. So their execution time is decreasing, let's say, proportionally. So in the end, when we calculate the energy, it is the reduction of the energy very, very similar. So in terms of numbers, Matcha Embedded provides more than 30 times lower execution time than the CPU ARM counterpart. Matcha Portable provides more than 10 times lower execution time than the CPU i7. And if we take a look to the energy, Matcha Embedded consumes more than 45 times less energy than the CPU ARM, and Matcha Portable consumes more than 10 times less energy than the CPU i7. Now let's take out to the Matcha HPC version, and in this case we compare it to its corresponding baseline platforms. That, to be fair, they are the CPU Xeon, the server class CPU, the GPU, and AVMEM. And as we can see here, Matcha, which is the one in dark green, is the one that provides the lowest execution time and also the energy. Overall, Matcha HPC provides more than 7 times lower execution time than CPU Xeon, more than 6 times lower execution time than the GPU, and more than 6 times lower execution time than AVMEM. In terms of energy, Matcha HPC consumes more than 11 less energy than the CPU Xeon, more than 4 times less energy than GPU, and more than 2.5 times energy than the AVMEM. So with this, I would like to conclude with Matcha with a couple of takeaways. So first, we introduced Matcha, which is the first NRAM-based accelerator for time series analysis. It provides some benefits like significantly higher parallelism because of the use of memory crossbars, exploiting these column-level bitwise operations, and also a reduction in the data movement overheads by leveraging processing using memory. So the key takeaway here is that Matcha improves the performance and the energy consumption over the CPU, the GPU, and the FPGA and AVMEM for those different Matcha versions that we evaluated. So if there are no questions at this point, I will go to the conclusions and we will finalize. Okay, so I won't repeat much. In this presentation, I share with you Natcha Matcha. Natcha is a processing near memory accelerator that is based on 3-stack DRAM and tries to reduce the memory boundness of the time series analysis by placing custom floating point compute units close to the memory stack, being able to exploit the bandwidth and also reducing the latency. On the other hand, we have Matcha, which is a processing using memory accelerator, in this case, based on non-volatile memory cells. That minimizes this data movement by performing the computation where the data is, so in the memory arrays. And overall, Matcha is the one that provides the highest performance and energy efficient solution. So far, better to say, by the time of writing this work for a wide range of time series applications. So yeah, just to finalize, these two papers are part of my PhD thesis, which is titled Accelerating Time Series Analysis via Near Data Processing Approaches. And they are part of what I call the asterisk TSA family, where we have FITSA, which was the characterization in the 7.5, NATSA, Matcha, and TRATSA, which I didn't cover in this presentation, and it's about reducing the number of bits in the floating point operations for the Euclidean distance approach and trying to improve performance and reduce energy consumption with this. So at this point, I think this is all what I have. So, I mean, thanks a lot for listening to me. And if you have any questions, I'll be happy to try to answer them.
Thanks a lot, Ivan. Are there any questions? I guess no. Thanks a lot again, Ivan, for your excellent talk, and we wish you all the best. Thank you.
Thank you very much. My pleasure. See you soon.
See you. Okay. Ataberk, are you online?
Yes.
Yes, we can see you.
Yeah. Hi. Can you hear me?
Yes, we can hear you.
Okay.
It's a bit, I don't know, far, you know.
How about this?
And there is also some echo going on. I'm not sure why, but
Is this better?
yeah, now it's better. Yeah.
Okay.
Okay.
And can you see my screen as well?
Yes.
Okay. When should I start? I think there's still some time until 5 p.m.
Yeah. I think we can start. I will introduce you, and then I guess we can get it started. Just I'm checking if we have your presentation on YouTube as well, which we have. Okay. So for the last talk today, Ataberk is going to present about his work, Sector DRAM. Ataberk Olgun is a fourth-year PhD student at ETH Zurich. His broad research interests include designing secure, high-performance, and energy-efficient memory systems. So Ataberk, feel free to start whenever you're ready.
All right. Thank you for the introduction, Mohammad. So I'll be presenting Sector DRAM, a practical, energy-efficient, and high-performance fine-grained DRAM architecture. So I'll start with an executive summary. DRAM-based systems today suffer from energy wasted by coarse-grained data transfer and coarse-grained DRAM row activation. And this is typically because applications use a relatively smaller fraction of all the data that they fetch from DRAM. And our goal in this work is to design a new, fine-grained, low-cost, and high-throughput DRAM substrate and mitigate the problem with coarse-grained DRAM systems. Our design has two key ideas. So with small modifications to the memory controller and the DRAM chip, we enable data transfers that are smaller than a cache block's size in a variable number of DRAM interface clock cycles. And again, with small changes, we enable activating small portions of a DRAM row. And these happen based on the workload's memory access pattern dynamically during runtime. The integration of Sector DRAM into a modern computing system provides significant energy savings and system performance improvement. Sector DRAM incurs a relatively small DRAM chip area overhead, and it performs within 11% of a high performance and high area overhead state-of-the-art fine-grained DRAM architecture, while consuming significantly smaller DRAM energy. This is the outline for this talk. I'll start with a brief background. Perhaps you've seen how we organize DRAM systems today, but this will be another recap of the DRAM system organization. So a processor's memory controller communicates with a set of DRAM chips within a module through a memory channel, and each chip contains multiple banks, and they share the common chip I/O interface. DRAM banks are organized into subarrays that consist of a set of word line drivers and sense amplifiers. Subarrays are partitioned in the DRAM mats, which are essentially collections of DRAM cells that are separated from each other by word line drivers. And DRAM cells are laid out onto a two-dimensional array of word lines and bit lines within each mat. And one row of DRAM cells is basically referred to as a DRAM row. This is a different and a more detailed view of the previous DRAM subarray, which we will look at to understand how DRAM row activate and DRAM read operations work. Probably Geraldo has walked you through these slides, but I'll help you remember. The global word line spans the whole subarray and controls the local word line drivers. The local sense amplifiers are connected to a global sense amplifier, and the global sense amplifiers are further connected to the I/O interface. So to access a DRAM row, the memory controller issues an activate command to DRAM, and on receiving an activate command, the global and the local row decoders enable the word line of the target row that's indicated with the red color here. That connects these DRAM cells to their bit lines, and then the sense amplifiers amplifies the deviation in the bit lines caused by the row activation and latches the data in the DRAM cells. So essentially, we have copied the DRAM row to the sense amplifiers. To read this data out from the sense amplifiers, the memory controller sends a read command with a column address, and the selected column is then transferred to outside the DRAM chip over the global sense amplifiers and the I/O interface. So that was inside a single subarray. Now we look at data transfers at the granularity of a DRAM module. Each chip receives 1 byte of data from its data interface, data signals, and 64 bytes make up what we call a cache block. This is the typical granularity of data transfer in modern systems. A DRAM chip receives multiple bytes of the cache block in a data transfer burst. The burst length for this transfer is 8 because each chip receives 8 bytes. So a chip receives 1 byte in each DRAM interface clock cycle, which is also referred to as a beat. So in the first beat, each chip receives its corresponding byte. In the second beat, the next 8 bytes, and so on until we transfer the last 8 bytes in the cache block. And inside each chip, the bits of a burst are eventually split across DRAM mats. Now, a key problem with this coarse-grained DRAM data transfer is that it wastes energy. Even if the processor wants to access only one word, for example, the second word in this cache block, the system retrieves the whole cache block of this word with the hope of exploiting spatial locality. But the processor only ends up accessing like 8 out of the 64 words it brings. So on average, across many workloads, the fraction of the used words are relatively low, like we show in this example. Coarse-grained activation of DRAM rows also cause energy waste. The DRAM chip activates all mats with every activate command to transfer all words of a cache block that are split across the mats in one data transfer burst. But activating all mats is not required because the processor does not use all of the words it receives from DRAM, and the unused words lead to activation energy waste as well. We investigate the potential energy savings a hypothetical fine-grained DRAM design can provide using 41 single-core workloads with an evaluation methodology that I will describe later on in the slides. The figure on the left shows you the energy benefits of enabling fine-grained DRAM access, and the one on the right shows you that of enabling fine-grained DRAM activation. Now, the particular design of such systems, we don't care at this point. This is like a hypothetical design. And we observe that fine-grained DRAM can provide substantial read-write and activation energy benefits. But enabling fine-grained DRAM access and fine-grained DRAM activation has 3 key challenges. We describe them here and provide a classification of only the relatively low area overhead prior fine-grained DRAM architectures. The first challenge is maintaining high DRAM data transfer throughput. Some fine-grained DRAM architectures reduce DRAM data transfer throughput by 8 times, which incurs prohibitive performance penalties. The second challenge is incurring a relatively low DRAM area overhead. We find that prior works that maintain DRAM throughput induce large area overheads. And the last challenge is to exploit fine-grained DRAM both for DRAM access and for DRAM activation. We observe that no prior work overcomes all 3 challenges, and therefore our goal is to develop a new fine-grained DRAM architecture that can mitigate the energy waste of coarse-grained DRAM while overcoming all 3 challenges of enabling fine-grained DRAM architectures. So let's now see how sector DRAM mitigates energy waste. By the way, feel free to stop me at any point to ask me questions. So sector DRAM has 2 key design components. First, we find that modern high-performance, high-yield DRAM architectures already split DRAM rows into physically isolated small fixed-size mats. Those are the DRAM mats that I've showed you earlier. And leveraging this observation, the first component, the sectored activation component, enables fine-grained DRAM activation at low cost. And second, we observe that the DRAM I/O circuitry already has a way of transmitting arbitrary words or bytes of a cache block in each data transfer beat. So we slightly modify the transmitted byte selection criteria to enable fine-grained DRAM data transfers at low cost using what we call variable burst length. We will start by looking at sectored activation in a bit more detail. So this is our example DRAM subarray from the earlier slides. We want to enable the first 2 mats and not enable the last 2 mats in this picture, for example. To do so, we first isolate the global word line from local word line drivers. We do that by adding isolation transistors that we call sector transistors between the global word line and the local word line drivers. Next, we need a way of controlling the sector transistor. So we add a new control signal that we call sector latch for each mat. And by doing so, we essentially have transformed the mats in our subarray into sectors, each of which can be individually activated. So we'll look at the second component now. We have 8 sectors in a DRAM bank. Each sector sends 8 bits with a read command to a buffer that we called the read FIFO. And a relatively small, simple circuitry selects 8 bits from this buffer to transfer over the DRAM chip's I/O with each beat of the data transfer burst. The selection process is controlled by a burst counter that gets incremented with every beat. And to enable variable burst length data transfers, we simply replace the burst counter with an encoder that selects data sent by only the open or activated sectors in the DRAM chip to the read FIFO. So, for example, if only the first and the last sectors were activated, that's highlighted with the color orange here, the encoder selects only these 2 sectors data to transmit over the chip interface. So sectored activation and variable burst length can be exposed to the memory controller with no DRAM interface modifications. And I invite you to read our paper for more details, but I'll be happy to discuss or answer questions about it also. I'll now describe how a modern DRAM-based computing system can effectively leverage sector DRAM. Effectively integrating sector DRAM into a system has 2 challenges. First, today's systems transfer data between components of the memory hierarchy in cache block granularity. However, we must enable sub-cache block granularity data transfers for sector DRAM to mitigate energy waste. We use sector caches, whereby we extend each cache block with 1 bit of metadata for each word. Each of these bits indicate if its corresponding word in the cache block is valid. So this way, data can be transferred between components of the memory hierarchy at word granularity instead of cache block granularity. Now, because we retrieve a word with each memory access and not the whole cache block that word belongs to, missing words in a cache block cause performance overheads as we induce additional memory accesses. Our solution to the second challenge is to develop two prediction techniques. The first one exploits the spatial locality in subsequent load store instructions word addresses. And the second one is a spatial pattern predictor that we tailor for predicting useful words in a cache block. I'll explain the first technique in a bit more detail. So we call this technique load store queue look ahead. One load or store instruction typically references or accesses one word in main memory. And our key idea is to collect memory references from younger load store instructions in the load store queue and put the collected references in the oldest load store instruction. And then we expect that when a load store instruction executes, it will retrieve all the words in its cache block that will be used by other load store instructions in the near future. Thereby, we expect to eliminate some of the additional memory accesses from sector misses. However, load store queue look ahead suffers from two key drawbacks, which in summary prevent it from identifying all useful words in a cache block. We developed sector predictor to complement load store queue look ahead and minimize sector misses. The key idea of sector predictor is to maintain cache block signatures that describe which words are likely to be useful based on current word use characteristics in the L1 cache. That's the word use history in the L1 cache. Then we basically reuse these signatures when a cache block misses in the L1 cache to retrieve all potentially useful words from lower levels in the memory hierarchy. So now I'll switch gears and move on to the evaluation of sector DRAM. I'll pause for 3-4 seconds to take questions. Cool. So we use a variety of simulation frameworks to evaluate the performance and energy efficiency of sector DRAM. This is the baseline system configuration that we use. We compare sector DRAM to 3 state-of-the-art fine-grained DRAM mechanisms, namely half DRAM, fine-grained activation, and partial row activation. We simulate 41 1 to 16 core multi-program workloads from major benchmark suites. We investigate the activate and DRAM activate and DRAM read power improvements of sector DRAM first. Write power improvements closely resemble that of read power, so we exclude it from this slide. The x-axis shows you the number of activated or read sectors, and the y-axis shows power in milliwatts. Here's the power consumption broken down to DRAM array power, that's the light shade color, and the DRAM periphery power, that's the darker color, for activating or reading 8 sectors, and this is the rest of the plot. We make 2 key observations. First, reading or activating 1 sector can greatly reduce the power consumption compared to reading or activating all 8 sectors, which is what we expected to see. And second, we observe that activate power is dominated by periphery power, which is marginally affected by the number of sectors activated. So the most power reduction, power savings we expect to get from, proportionally speaking, read power reduction. Then we look at the performance of our sector prediction techniques. We show different sector DRAM configurations and the number of their last level cache misses averaged across 41 evaluated single core workloads. The basic configuration here has no prediction, and there are different LSQ load store queue look ahead configurations as it introduces many sector misses basically. However, we see that the load store queue look ahead mechanism with 128 entries looked ahead in the load store queue combined with a sector predictor with a history table size of 512, can minimize the loss level cache misses caused by sector misses. We now show the distribution of speed up end-to-end speed up across all tested workloads, categorized according to their number of to the number of their loss level cache misses. That's high MPKI, so very memory intensive, medium MPKI, moderately memory intensive, and low MPKI. The boxes on the left, the visible boxes on the left of each subplot show the performance of baseline, and the boxes on the right, this one, for example, and this one, those boxes show the performance of sector DRAM. The x-axis shows the number of cores, and the y-axis is parallel speed up normalized to the baseline system executing the same workload on a single core. So the higher a point in this plot, the better the performance for that workload. And these are the speed ups provided for dual core homogeneous multi-programmed workloads. And this is the full plot. We observe that sector DRAM provides significant speed ups for highly memory intensive workloads when core count is higher than 2. That is, for workloads that create high contention in the memory system. Second, sector DRAM provides smaller parallel speed up than baseline for non-memory intensive workloads because the higher rate of activation commands that we can send due to the power reductions that we enable cannot amortize the overheads of additional memory accesses due to sector misses. However, we have a way of alleviating the performance degradation for those non-memory intensive workloads. Our key idea is to fetch all sectors of a cache block, that is, disable sector DRAM, for workloads with access patterns that do not favor sector DRAM. At a very high level, we measure the average number of requests in the memory controller's read and write request queues as a proxy to indicate the memory intensiveness of the workload. And if the occupancy is higher than a certain threshold, we enable sector DRAM. So we show the weighted speed up for heterogeneous workload mixes for 3 memory intensity categories using sector DRAM and the dynamic policy that I just described. We observe that the dynamic policy overcomes the performance degradation in non-memory intensive workloads. We look at sector DRAM's energy benefits. This plot shows you the normalized system energy on y-axis. So a smaller value here is better. And similar to the speed up results, sector DRAM provides significant energy savings for highly memory intensive workloads at core count greater than 2. We also compare sector DRAM's performance to the three state-of-the-art techniques for highly memory intensive 16 workload mixes shown on the x-axis. Across these mixes, sector DRAM provides 17% average speed up. And it greatly outperforms the basic fine-grained DRAM mechanisms because it does not reduce DRAM throughput. It outperforms partial row activation by 10% because sector DRAM leverages fine-grained DRAM for read accesses as well as write accesses. And sector DRAM performs within 11% of half DRAM. Now, this is because half DRAM does not incur any additional memory accesses due to sector misses, and half DRAM benefits from a higher rate of activation commands like sector DRAM. We compare sector DRAM's energy savings to those prior state-of-the-art works as well. Sector DRAM outperforms all 3 techniques in energy savings because it enables finer grained data transfer and activation than half DRAM. It reduces background energy consumption by reducing workload runtimes over partial row activation and fine-grained DRAM. Finally, we estimate sector DRAM and processor area overheads. We find that sector DRAM components take up 1.7% of a DDR4 chip's area, and the sector caches and the sector predictor in the processor chip take up 1.2% of a modern 8-core processor's area. We have more details in the paper, such as a micro benchmark performance evaluation study that shows that sector DRAM greatly improves random access workload performance. We have sensitivity studies on the effects of the number of DRAM channels and prefetching. We don't observe something surprising here. With more number of channels in your system, you have better benefits coming from sector DRAM. And with prefetching, you can improve sector DRAM's performance. We also discuss how we can support finer grained sectors. That's, for example, having more than 8 sectors in a DRAM chip. And we discuss sector DRAM's compatibility with DRAM error correcting codes. It's compatible with error correcting codes, basically. I invite you to read our paper for those details. Now I'll conclude my talk. In this work, we designed a fine-grained, low-cost, and high-throughput DRAM substrate to mitigate the excessive energy consumption of coarse-grained DRAM. With small modifications to the memory controller and the DRAM chip, we enabled variable-sized data transfer bursts and enabled activating smaller-sized regions in DRAM chips. Our results show that an effective system integration of sector DRAM provides significant energy savings and performance improvements at low DRAM chip area cost. This work was published in ACM TACO. We have an extended version of that journal publication on arXiv, and sector DRAM's all code and data we used in the paper is open source. And that brings me to the end of my talk. I'll be happy to take your questions.
Thank you so much, Ataberk. I have one quick question.
Sure.
So can we use the sector DRAM to combine sub rows, across different rows of the DRAM?
You mean like, okay, maybe I'll show you a picture and I'll ask you to clarify. Sub rows meaning like the part of a row that belongs in one mat?
Yes, exactly. Yeah.
Yeah, so with sector DRAM, you don't have to retrieve 1 byte at a time. You can activate as many as 8 sectors at once if you want to access the full row, or you can activate as few as 1 sector at a time if you want to access only 8 bytes, let's say, of a cache block. And you can activate any number of mats in between or sectors in between.
Yeah. So basically, the row that you are accessing in each mat, these rows can be also not aligned, right?
Now I understand. Okay, now I understand your question. Okay. So basically, you're talking about subarray level parallelism. Unfortunately, I don't have a good slide to pictorially depict what's going on.
Yeah, something similar to subarray.
Exactly.
Level parallelism, but can be also in intra subarray. What I'm also talking about.
Yeah, so I think you could do that. We don't do it in this paper. We don't evaluate it. And I think the main benefits over subarray level parallelism could be that you sustain a higher rate of activation. So if you really have a very, very random access workload, like the ones we have today, and very memory intensive workload, you can sustain a higher rate of activation commands because with one activate command, you're not activating the whole row anymore. So that takes less power. And that means you can spend that power on activating maybe another mat in another subarray at around the same time as this one.
Yeah, exactly.
So,
yeah, specifically, I was thinking about some, GPU workloads. I remember basically it was, so the row heat was quite poor, when we were running GPU workloads. But at the same time, we could see relatively good heat rate if we just, bring data to the row from different rows of the DRAM. So that's why I'm asking this.
Yeah. I think one other way to look at the benefits of such an implementation would be that without actually adding many more DRAM banks, you're kind of making it like that you're adding many more DRAM banks that can be accessed in parallel.
Yeah.
Without having so disruptive changes to the DRAM architecture, let's say. That allows you to better utilize, hopefully, your DRAM chip area.
Yeah, makes sense. Thank you.
Yeah.
Any other questions? No? Okay, then thanks a lot. Thanks a lot, Ataberk, for your excellent talk.
Thank you.
And I think that brings us to the end of the session and also the end of our workshop. So thank you everyone for attending the workshop, and also thanks a lot to the presenters. And I think we learned a lot during all these talks and discussions that we had. It was really informative. So thank you all, and I hope to see you in the next venue, which I don't know when, but yeah, let's see.
Thank you, Mohammad. Goodbye.
Bye-bye.